Observations in Monsoon Region with a special focus on recent field campaigns. And this session is chaired by Dr. Bernd Henoit, Tropos, Germany, and co-chaired by Dr. Padma Kumari from IITM Pune. So I request now the chairs and co-chairs to kindly proceed with this session. Thank you.
Yeah, so thank you very much for the nice introduction. And yeah, so maybe first of all, let me thank the hosts and the organizers for this very nice dinner that we had yesterday in the evening. It was very nice, very enjoyed it. I guess the others too. So then maybe let's get started with our third session. Again, we have a couple of invited speakers to actually, and then before or until the coffee break, we have 3 more regular talks. And yeah, I would like to, before we start, remind the speakers to keep the time. So we have 20 minutes for the invited talks, plus 5 minutes for the discussions and questions. And then the regular talks are 10 minutes plus 2 minutes for questions and discussions. And I will try to remind you. So then let's keep on going. And with the first speaker, with the first invited speaker of this session, it's Dr. Venkat Ratnam from the NARL here in India. And he will speak about unraveling the dynamics of the Indian summer monsoon circulation, insights into asthma variability, aerosol distribution, and pollution transport. So please, this stage is yours.
Thank you. Thank you very much. First of all, I'd like to thank Dr. Suvarna Fadnavis for inviting me for this to deliver this talk. So myself, Venkat Ratnam, I'm from National Atmospheric Research Laboratory, and I'll be talking about dynamics of Indian summer monsoon circulations, and I'll be touching more about the asthma variability and aerosol and trace gas distribution within this asthma. And my co-authors are Ghosh Basha, our students, Ghosh Basha, Hemant Kumar, Akhil Raj, and Ravindra Babu. And some of the results we have done close collaboration with NASA, and Dr. Jane Paul was leading that. And some of these experiments we conducted from TFR balloon facility, BHU, and some of the analysis we have done from PRL. Now, this is my overview of the talk. I'll be talking about Indian summer monsoon circulation and its source and sinks. Then I'll be quickly touching about asthma and its variability. And I'll be touching about different modes and effect of monsoon activity and why we need to consider different monsoon activity conditions. Very, very important, because that is going to dictate the asthma or any circulation changes in the monsoon time. And in turn, we could expect that similar variability in the air, trace gas and aerosols. And then I'll touch upon trace gas distribution within asthma. And I'll be interested more in the vertical variability in asthma during different modes of asthma. Then finally, aerosol distribution within asthma, and I'll be touching on more on spatial asymmetry, optical, physical, and chemical properties. Then convective transport pathways for lower atmospheric pollution to the utilized region, and I'll be bringing out the new results we got from Kolkata Camp Observatory we established at Kolkata and summary and future scope. So we all know that Indian summer monsoon circulation, it acts as a source and sink for the pollutants. And during this time, particularly from June to September, we'll be having a very strong low-level jet at 850 Pascal to 700 hectopascal, and it can be a source for several pollutants which can bring from the Arabian Sea through from South African continent towards India. This is between 850 to 700 hectopascal. And at the same time, at 100 hectopascal, there will be a tropical slit jet. And this can also be a strong long-range transport coming from the north part of India, including China, and it can get it into this Indian region, because this will be persisting almost like 3 months over Indian region. And at the same time, at the head of Bay of Bengal, you can see that cloud, deep convection cloud will be persisting. So whatever the sources, either low-level jet or in situ generated over Indian region or through long-range transport from the tropical jet or low jet. Once it's entered into this Indian region, this vertical transport will be taking up, and this can take into the asthma region. And once it is entered in the asthma region, it will be confined for 2 to 3 months. So sources can be anywhere. Though anticyclone is persisting over Indian region, it doesn't mean that all the pollutants are coming from down, because long-range transport is equally important for this one. So once this, what I want to say that dynamics plays an important role in the asthma variability, and it's related to the pollutants in the asthma. So once it's entered, there is only redistribution of aerosol and trace gas will happen only through this water circulation, and it is not that strong during this time. And so that is the reason why it has been confined to more than 3 months during this time. So what happened then? As a result, within the asthma, you can see that this is the long-term climatology from MLS data. This is carbon monoxide is shown in 100 hectopascal and water vapor. You can see the tropospheric air, you can see that confinement in the asthma region, including the aerosol. And another reason, what is the reason for the tropospheric air to say that, because ozone concentration is very less. So this tells that there is a possibility of tropospheric air entering into the asthma region, and we can see the cloud fraction is very high. But this will not be persistent for all the 3 months. It has a variability. As the asthma varies, these kind of pollutants also will vary. And different modes in the asthma has different, the different effect of these pollutants, and also role of monsoon activity. This is very, very important, because in the monsoon season, it is not that 3 months is going to happen the active season, active monsoon. There are some weak monsoon. There are some strong monsoon years. There are El Nino, La Nino. It has a lot of effect on this kind of variability. So first and foremost, we want to investigate the variability within the asthma. And this is the climatological mean from the NCEP analysis. They are showing the geopotential height at 100 hectopascal. You can see that from 16.75 to 16.9 geopotential height, it will represent the asthma region. And mostly you can see that very center there are 2 modes of this asthma, the Tibetan and Iranian thing. And when we apply for the trends, you can see that the center of the asthma, we doesn't show any big trend, but you can see that edges. There is a huge variability in the last 50 years. So this is, and it can have very big impact on the pollutants reaching into the asthma region. And when we try to see that the wind difference, but strength of the asthma, we calculated by measuring the anomaly between 30 to 40 degree north and 10 to 20 degree north. And you see that strength of the asthma is increasing in the recent decade. So it has a lot of impact, because anything entering into that, it has this kind of consequences. Now, I will show that how that activity of monsoon is very important for the asthma. What we did, we separated the days with active and weak monsoon. In fact, every 1 week to 2 weeks will be active monsoon, and after that, a break monsoon will be there. And sometimes the good monsoon will be there, sometimes very bad monsoon, that year-wise if we take it. And ENSO has a very strong effect on our Indian summer monsoon circulation. So when we separated this one, you can see that the active is shown in the red, and break is shown in the blue line. In the active part, you can see that extent of the asthma is increasing. And at the same thing, we've shown the strong monsoon, La Nina years have the extent of asthma will be larger when compared to the counterparts like weak monsoon or break days or El Nino. And you can see the significant warming in the northeast part of India during this time. This is from radio occultation data. And all this will be providing a favorable condition, particularly during the strong monsoon and active monsoon, and also La Nina events, to bring most of these pollutants to in the asthma region. Then I will show that how the pollutants will vary within this one, and this is the difference between strong and weak monsoon years. This water vapor, carbon monoxide attenuated scatter ratio. You can see that during the strong monsoon or active monsoon, it will be the difference. You see that it will be very high. Means most of the pollutants are reaching to the asthma region only during the strong monsoon or active monsoon season and La Nina conditions. And at the same time, you see that this is the convection is deep convection is put in this red circle, and the active convection will be more during the strong monsoon and also the active monsoon. And that vertical velocities, you can. This is very important parameter. Any pollutants in the happening in the boundary layer or in troposphere, this vertical wind can take to the lower stratosphere, and you can see this will be very active during the strong monsoon and also the active monsoon season. And again, if you see that El Nino conditions, it's quite different. You can see that the strongest El Nino in 2015, in that how that asthma will be disturbed during the El Nino event. And the anomalies we calculate between 2015 to 2014, we removed and showed alarming here. So it is no more, it is a single asthma in the El Nino year. It has been split into two. And such variability, again, we have seen in the trace gas distribution. But surprisingly, earlier we thought that tropospheric air is there because carbon monoxide water vapor is high in the asthma region, whereas low ozone. But to our surprise, during the El Nino event, the ozone concentration has increased, whereas the water vapor and carbon monoxide has decreased. So you can see that it's the background dynamic conditions has very strong impact on this asthma and their pollutants entering into the asthma region. So we need to consider these things when we are calculating particularly the radiative hosting due to these asthma pollutants. Then we try to investigate the different modes of asthma. As you saw, several investigations have shown that, particularly Jang et al., they have shown that the bimodal distribution of this asthma. And we try to get these details from the ridgeline minimum value in the horizontal wind. And center of asthma we located from maximum GPS along the ridgeline. So these are some of the statistics. I'll come back to again this one. And you can see that those days, if this is the climatological mean, June, July, August, and it has a 3 mode. One is Iranian plateau mode, Tibetan plateau mode, and elongated mode. So it is not at center, always center at this one. So it will try to move from east to west and sometimes throughout this elongated mode. And as a result, in fact, it is not the same among the reanalysis. So this is one of the important aspects which I want to show you that we cannot believe the one reanalysis data set. So as in the S3 news, Dr. Matsumoto Fujiwara, he was mentioning that single reanalysis data set is not sufficient to get any of these kind of background things. So we try to include that ERA5 and MERA2. NCEP is a very coarse region, 2.5 degree latitude longitude, but here is 0.25 by 0.25. You can see that bimodal distribution is again reproduced very well in the ERA5, but MERA doesn't have those kind of things. So we have seen a lot of difference in the monsoon activity, and none of these reanalysis data set could able to simulate all the monsoon features what we observed using the in situ measurements or the radio sound measurements or Indian region. So we should take a lot of care in while interpreting these kind of variability in the UTLS region or in asthma region. So, but keeping this aside, as I mentioned, that IP mode and TP mode was there very clear. And then we separated that carbon monoxide O3 and water vapor. As per this mode, we separated. Then you can see that in the IP mode or TP mode, in electric mode, those trace gas distributions are equally distributed as per the background dynamics. So background dynamics plays an important role. It's not that whatever it is entering in asthma, it is throughout persists for 3 months. It has long variability. And when we are calculating the radiative forcing due to these pollutants, we should take a lot of care. Then coming back to the third part of my talk, this is the spatial estimate in the aerosol distribution. And this is the GPH again I am showing, but now we are divided into 4 parts within the asthma: southeast and northeast part, and northwest and southwest part. And this is the deep convection area, put it in this pink color. And this is the aerosol extension, the mean of 16 to 18 kilometer. And to our surprise, it is not covered throughout the asthma region, aerosol distribution. It has a lot of spatial asymmetry. And it is more over the eastern part when compared to the western part. Then we try to see that what is the mechanism for that, why we have seen only this kind of thing. Then because we have the tropospheric parts and stratospheric parts separately, then we try to look in the tropospheric part or this asthma region. You can see that southeast and northeast part, it can go to even to 5 to 6 kilometer in the troposphere. But if you come to the low stratospheric region from 16 to 18, you can see that southeast and northeast part has a lot of concentration of aerosol, but not in the rest of. Then we try to investigate what is the reason for this. Then we use that OLR as a proxy for deep convection. Then vertical wind also, because deep convection means vertical velocity will be upward and no convection means downward. Then when we try to see that different parts of this northeast and southwest, and we segregated the vertical wind, including cloud fraction. And in the northeast or in the southeast and northeast part, you can see that this pressure vertical velocity means downward, negative means it's upward. You see very significant upward velocities you can see only in the southeast and northeast part, but not in the other part. So much of the convection which is happening in the head Bay of Bengal can pull these kind of pollutants and keep into the southeast and northeast, but it is not equally distributed. You have seen the lot of spatial asymmetry. We have used the cloud fraction also from the cloud side to differentiate that cloud up to what altitude that deep convection can do. Deep convection go even to 12 kilometers. Since the background vertical velocity is always upward, any pollutants reaching to 10 kilometers, that background wind will take care, and it can go to the UTLS region or in the asthma region. Then we have seen that because long-term data is available from the Calypso, we separated those observations from within the boundary layer, because we want to see that in the changing climate or changing the global warming scenario, what is the fate of these long-term trends in the aerosol distribution. In the below boundary layer, we are separated, and we calculate the AOD in all those 4 regions. Then within the mid-troposphere and in the lower stratosphere, you can see that in the boundary layer and mid-troposphere, the aerosol concentration is decreasing. But again, in the lower stratosphere, that is particularly in the southeast part of in the asthma region, there is an increasing trend in the aerosol concentration. And this is supported by the cloud fraction, which is increasing trend, and also vertical velocity is increasing in the mid-troposphere to lower stratosphere. So this is supporting results. So it tells that in future, more and more aerosols we can see in the asthma region when compared to mid-troposphere or in the boundary layer. Then yesterday there was somebody was asking that why sulfate was not seen in the asthma region. Then we try to put in this in concept in this one. So what makes the difference? What makes the separation between atoll and the well-known Jungi layer, the stratospheric aerosol layer? And you can see that this is from Jean Paul, 15 to 18 kilometer average the scattering ratio, and between 15 to 45 degree north, if you put the vertical structure, you can see that this atoll region is separated, well separated when compared to Jungi layer, which is the stratospheric well-known thing. So if our balloon flights are in the, if you get the air sample from the Jungi layer, we'll be having more sulfate, but much of our interest was here. So that's what we could see, the different chemical composition of the aerosol concept. So what makes this separation? Using the stability criteria, which is developed by Sunil Kumar. He is sitting here and he'll be talking after my talk. Then he has defined that the LMAX, which is the top of the TTL layer. Unlike earlier, we thought the convective fluid level to cold point tropos is the TTL layer, but we redefined using our observations up to LMAX will be the top of the TTL layer, and this LMAX is nicely give the top of the atoll layer. So beyond that, atoll will never exist, and once that will again Jungi layer will come into picture from 20 to 21 kilometer. So well-defined separation is there between Jungi layer and atoll layer. Then we try to see from the battle campaigns we conducted from Gadanki, Hyderabad, and Varanasi. We could see that again that the atoll layer is well separated, and always it is matching with the maximum stability in the temperature profile. So we could explain that what makes the difference between the atoll layer and the well-known Jungi layer using the static stability criteria. So this we could explain. That's why that the air in the atoll region is quite different. Sometimes maybe there's the sulfate, but not always it's possible. So coming back to the chemical composition, this I taken from our battle campaigns from Vernier et al. And we conducted the campaigns from this Gadanke from our center and Hyderabad and also Varanasi. And we have used that long duration balloon flights, almost like 2 to 3 hours. We try to put it in 16 to 18 kilometer. And we draw the air and we have the offline ICGC analysis. And it's very interesting to see that. And before putting into the balloon, the ground observation says that sodium chloride and sulfate are very dominant in the ground. But if you go to the 16 to 18 kilometer from these kind of flights, you can see that nitrates are very dominant. And we had one winter campaign to see the background. You see monsoon season, how it is different in the winter season. We could see that we could never see that nitrate, but as usual, like sulfate and other sodium chloride, those kind of things are dominant. So it tells that nitrates are very dominant. Now the question is, there are 3 different mechanisms for the nitrate to generate. One is the conveyed transfer of precursor gas from lower atmosphere or to gas to particles conversion, mostly that agricultural activity, ammonium nitrate, which is heavily used, that can have a source, and that if at all any conversion is that can go to the lower stratosphere. And second thing is lightning activity, and third is the aircraft contrails. Then we try to look into the first part, and because our Gadanki is well at the edge of the atoll, we could not get much information from the surface. Then we have established one observatory at Kolkata, Camp Observatory, and these are the several instruments we have put it there. And I'll be talking about these 2 instruments right now. So there are several different objectives for this one. Because wanting of time, I'm not going to detail. But what we collected from this campaign, which is located well within the atoll region, we try to get the air samples, both rainwater and the filter tape samples from the surface. So we want to establish what is the surface concentration, surface chemical composition before going to the atoll region or that region. So we collected some 41 rainwater samples during 21 to 22. And this shows that ICGC analysis, both anions, cations. And very interesting to see that the sulfate and nitrates and calcium ammonia is very dominant, both in the monsoon and post-monsoon season. And this is from the rainwater analysis, and this is from the aerosol PM2 chemical titration. Both show the same thing. In fact, these 2 has 2 different things. One is the air sample at a given time in situ, and those on the filter tape, then we went for ICGC. And another thing is rainwater sample, because these chemical compositions are anions or cations already there in the rainwater, and both show the same thing. So it means that it is well distributed, not at the point, even means throughout the Indian region, this is more or less will be same, particularly in the central part of India and within the asthma region. So this tells that ammonium nitrate is a very dominant in the surface also. I mean, in the in situ, both rainwater and in surface. Then we try to see this air's ammonium volume mixing ratio. And yesterday, Hafner was mentioning that he has shown that to see that ammonium nitrate very is coming. In fact, though it is more concentrated on the Pakistan through the IGP, and it comes to the Kolkata campus where it is located here. And this is at 945 hectopascal, and this is around 500 hectopascal. You see that still, even if you go to higher altitude, you can still see that in our Pakistan it's still very high, but the transport from Pakistan will not happen. Though that figure tells that that location was batteries that end up there, but what we happen see here is the deep convection is always present in the head bay of Bengal, and vertical velocities will be there. And if you go to this side 20 to 30, where this one, you can see the downward propagation. There is no upward propagation. So maximum though they're generated throughout this IGP belt, but the transport will happen from this region only. So we should be more concentrating on this one. And even in the post-monsoon season, you can see that still Kolkata has that, but we have not seen because there is no background conditions are not favorable to take these pollutants to the utilized region. So background dynamics plays an again important role. Any transport of these pollutants to the from lower troposphere to the utilized region. Then to summarize this one, see, we have used this both rainwater and the filter tape analysis and we could see that nitrates are dominant. And even if the spatial distribution says that IGP region, including from Pakistan to IGP to Kolkata region, it has a strong thing, but strong abducts can take this to this one. But one thing that important we are missing is the natural process like lightning and thunderstorm has a very big source of nitrate. So before going to that, agriculture is one of the source, but definitely. But in absence of lightning, thunderstorm, definitely agricultural source will be dominant, but lightning is much more dominant, and this has to be characterized first. So if you see that lightning flash rate from the trim measurements, you can from the similar to that what we see in this one, you can see exactly that the lightning activity will be very high over this Pakistan region through the IGP region to the Kolkata. So what we have to establish is that now we have the National Remote Sensing Agency of our center has established this lightning detection network, and we are going to use this to separate the contribution from the lightning or thunderstorm activity and also the agricultural thing. And more important, that aircraft controls is another important aspect which need to be considered. And for this, we want to conduct a simulation, because that COVID lockdown is one of the greatest the natural laboratory condition it has offered, where no flights were flying. I think July, August, if we can do some of the simulations where we can rule out that aircraft control means contribution to this atoll region. So that will be very good experiment we can do by to pinpoint the three activities, either convey to transport or through the lightning activity or through the aircraft controls. And finally, once we get all these things, we try to utilize to see the radiative forcing estimates. And because nitrates were dominant, and some of the literature says that sulfate is also dominant, and we try to get from all the battle campaigns, we try to get the radiative forcing estimates. And to our surprise, there is no big difference between radiative forcing between both either sulfate or nitrate. And heating rate we calculated, though heating rates are very high over the center of the asthma, that over Varanasi when compared to Hyderabad and edge of the atoll at Gadanki. But these two have the same radiative forcing, both have same thing. Perhaps what we have to get is that a 2.58 micrometer is very strong nitrate line is there, and those measurements are missing in our observations. So we need to have the broader measurements in future campaigns. And to summarize, we have conducted a long balloon data set, almost like 92 flights from during the battle campaign, and we got very good, interesting results. But because now new challenges have arrived, for example, volcanic eruptions are more and wildfires are coming into picture, then we continued that battle campaign from 23 to 27. And next month we are going to come, we have the battle campaign from Hyderabad, July 17 to August 17. And we want to continue this one, but more important, we have collected several instrument data, for example, Strateral 2 and Eclipse campaign and Stratoclim So all this synergy of measurements is very, very important to pinpoint for particularly the radiative forcing estimates, because we need huge number of observations for those kind of things. And also you can see the Stratal 2 is a similar payloads. Of course, it is away from this Atoll region, but if we can summarize, means what is happening in the Atoll region through this in the central part of India, in the Indian Ocean, that will be very good contribution. And this, from all the presentation I made from these papers published from our group, and if somebody can go in detail. And to summarize, large variability and asthma is seen, and it is well noticed that activity of the monsoon is very, very important to consider for any variability in the asthma. And similar variability is reflected in the trace gas and aerosol, and large spatial asymmetries are seen in the aerosol distribution particularly, and is more in the southeast part of asthma when compared to this one. And now chemical properties is still long way to go, because these are all not robust. Several limitations are there, and we need to concentrate more on that. And of course, new challenges like wildfires and volcanic eruptions are throwing a new challenges. And I think the next campaign our bill will be bring a lot of can throw some of the light on these kind of things. And as I mentioned, there should be a synergy between different campaigns. And if we can bring all data together and people together, I think this can be attempted in better way. And the relative roles of vertical transport and long-run transport need to be quantified. And hope model simulations are very much required to help for this to quantification. And radiative acoustic estimation due to these pollutants are still not that robust. But to see the impact of weather and climate, these are all very much important. So with this, I conclude my talk, and thank you very much for your attendance.
Yeah, so thank you very much, Dr. Ratnam, for this very interesting overview. And is there any question? Yeah, in the back. Get a microphone there.
Hello, sir. It is very good talk. I want to know, you show that aerosol concentration and convection pattern over the eastern side of Tibetan plateau. So is that observed the both mode of asthma, means Iranian mode and Tibetan mode?
See, actually, that vertical velocity we have not separated according to the mode. But in general, only when we are talking about the particle matter like aerosol, then that convection has, because if you want to talk the trace gas, it has different the gas to particle formation. It will be quite little different when if more water vapor is there or less water vapor is there. So those separation we did only for the aerosol, not for the trace gas.
Okay. Thank you.
So there was another question in the back.
Morning, sir. Nice talk. Sir, how did you define the active and break? How did you choose it? Is just a El Nino and La Nina year days, or you have any criteria to define the active and break? And which part you have defined?
See, active and break days we used from IMD definition. Okay, we have taken from that definition. Strong and weak monsoon years also we are taken from IMD. El Nino we have taken because that was the only that El Nino was there 2015. Once where we have observation, we have straight away taken that year.
So, I mean, like when you define an active break days, you didn't categorize the event length, duration, like
duration will be considered.
Like, short duration, and you combined all the short duration and extended range.
Wherever that IMD has declared that these are the active days and these are weak days.
So just combined all the
combined all those observations.
So, but then my follow-up question is then extended, if you take the spell, extended break or extended active has a different remote response of the heating rather than the short.
You're right.
So then how do you, have you looked at remote responses like, South Asian monsoon is interaction between remote responses like tropical West Pacific convection, maritime convection. So that changes with respect to the spell duration and the mechanism is different. So how do you cope with that? I mean, you consider all the things.
So in this study, we have not considered it, but this is a good point, and we'll try to look into that. Suppose there is an extended, in fact, that is very, very good question. If an extended break is there, none of these mechanisms will work actually. Yeah. So it's a good point. We'll try to look into that.
And another question. So when you say that reanalysis, whatever the list of the reanalysis that you showed has a discrepancies among them, what do you think that why it is coming? Is it because of the omega in the vertical velocity profiles in the reanalysis that is giving the differences, or any other?
No, if I recall the test strip news by Fujiwara, in fact, he was mentioning that each model has its own advantages and disadvantages because they want to concentrate on some of the aspects and they will give much preference to that. But if you want to get a wide general idea, no single model will be used. For example, if I want to use I'm interested in utility region, one model may give better result, but other models may be interested right from surface to the lower stratosphere. So depending upon that model configuration, that has been done.
Yeah.
But if you want to have only that asthma region, none of these models are going together. In fact, when we compare it with radio Sunday, not even that tropical jet is being reproduced well. So if that kind of discrepancy is there, then related to that dynamics, how it is reproducing, that is a big question. So what is suggestion made by the TESRIP news is that at least to take 3 models and see that same phenomena, so that you will get some idea which model to consider for that kind of main parameter.
All the models should be use the same convective parameterization or some it should have. And one more final question.
Yeah.
You have shown
Sorry,
the heating
sorry.
rate.
I don't know. Maybe those
Yeah,
are
maybe we
very
can discuss-
detailed
yeah.
questions. Then maybe you can just do that in the coffee break. I've seen another hand over here.
A very interesting talk. I'm interested in the Asian monsoon anticyclone. You showed that the strength is increasing. You have a trend over the years. And if I understand it right, you have no trend in the area of the Asian monsoon anticyclone, so in the size, and also not in the position. Is it right?
So in the center of the anticyclone, there is no big change.
Yeah.
But at the edges of the anticyclone, there is large decadable variability.
Yeah.
Okay, and when we take in the 10 to 20 degree where the tropical jet will be stronger. The difference between this and asthma, because that center we have considered the total that 16.75 to 16.9 GPH altitude. We consider that as the asthma region. Then we remove that the zonal wind, the difference if you want to see, then that is increasing. That is increased mainly because that tropical jet strength is strengthening, but asthma is weakening.
Okay. Asthma is weakening and the strength is increasing.
Yes.
Okay, thank you.
Okay, then I think we should move on with our next speaker, who is Dr. Ren Smith from the NCAR in the US. And he will speak about transport by Asian monsoon convection to the upper troposphere and lower stratosphere during the 2022 ECLIP campaign.
Okay. Hello, everybody. My name is Ren Smith. I'm a project scientist at the National Center for Atmospheric Research in the USA. I'm going to talk today about some results from the recent 2022 ECLIP field campaign and sort of the transport emphasis there as well. Before I move on, I, of course, want to acknowledge my co-authors as well as the meeting organizers for the opportunity. So I don't have to introduce the fact that the monsoon deep convection lofts pollutants into the UTLS layer because it's been done quite a bit in the meeting so far. But instead, I will show a visualization of this in a 3-dimensional space. So this is a sort of an advertisement for our NCAR Musica model. Oh boy. Okay. This happened to me earlier. Actually, the animation likes to stop. That's fun. It's supposed to go through 2022, but anyway, this is a 3-dimensional rendering from the NCAR Musica model. So we're looking at CO as a tracer of tropospheric air. I'm just gonna let that. I'm just gonna not try to fight with that, but it's supposed to play through September. But anyway, there's a link actually if you want to scan that and look at the full animation. But anyway, so what this shows actually is, if you can imagine, there's a connection between the pollution over the boundary layer over East and South Asia, and you can see intermittent deep convection lofting that into the UTLS layer. Through this convection. And then you can see sort of the influence of the anticyclone swirling around in the UTLS layer as well. And you can see the connection of that with sort of the broader area as well in the broader surroundings. So that's the motivation for the problem that we're addressing here with the ECLIP campaign. So let me try to move on here. So I'm going to go right to introducing the ACLIP campaign so I can talk about it for the rest of the presentation. But the ACLIP campaign was the Asian Summer Monsoon Chemical and Climate Impact Project, which took place in 2022. I'm going to talk next about how we accomplished these goals, but I'm starting just with sort of the high-level goals. The primary goal of the campaign was to investigate the impacts of Asian gas and aerosol emissions on global chemistry and climate via the linkage of the Asian monsoon convection and associated large-scale dynamics, and specifically subpoints transport pathways, chemical content, aerosol information, as well as water vapor distribution as well. I'm going to be talking mostly about transport pathways and chemical content, although there's a number of research projects being done on the other areas as well. So this is sort of the tools that were used for the ACLIP campaign to accomplish these goals. We employed two research aircraft for this campaign. First was the NSF NCAR Gulfstream 5 or the G5 aircraft as well, and we had the NASA WB-57, and both of these aircraft were outfitted with comprehensive chemical and aerosol sampling payloads. And although I won't talk about it in this presentation, we heard a little bit about some ground-based measurements in the previous talk, but there was also an extensive ground-based contribution from the various regions over the Western Pacific where the campaign took place. And so a bit of an operational highlight from the campaign, sort of to orient you for where these campaign results took place. These are the flight tracks from the campaign. You can see that the NASA WB-57 is colored in blue. The G5 is covered in sort of light blue or cyan. There were a total of 29 research flights between those two aircraft, and there were also a handful of flights from local Korean teams with actually in the light green that you can see there over the yellow sea as well. And the reason why we employed two research aircraft for this is clear on the right panel, where we actually have you can see the different altitude sampling primarily from the two different aircraft. So the G5 actually has a much larger span in terms of how long it can fly. And so the G5 is able to cover more of a broader region horizontally, but the WB-57 has the higher altitude capability. And so they were able to sample the sort of vertical gradients across the tropopause as well. And I can't move on without showing the obligatory group photo that we took during the field campaign. This is from Osan Air Force Base in South Korea. And so there were a number of people that contributed to the campaign, and actually this is probably only something like a half or a third of the total people that really contributed to the campaign. There's a number of people who are remote and not pictured here as well. So it's certainly a large sort of coming together of a lot of different minds to put something like this together. Okay, so let's move on to some science here. Probably the biggest and sort of highest level highlight from the ACLIP campaign is shown on the left. This is a carbon monoxide distribution and with altitude from the whole campaign here. Again, the WB-57 is in blue, the G5 is in the cyan color. And you can see that, I know I have written here unprecedented. I don't know if that's maybe the best word or if there's a better word, but nonetheless, you can see in the upper troposphere, there are CO observations in excess of 300 parts per billion, which I think is quite large and quite surprising. And I think all of us were very impressed or to see that in, as far as the raw sort of magnitude of that. And the part of the reason for this, or I guess maybe the primary reason for this, is actually then shown on the right. We're looking at MLS CO for 2005 through 2021 in the bottom panel, and then you can see the difference in 2022 compared to this maybe a short climatology from 2005 to 2021. This anomalous sort of extension of the anticyclone towards the east and towards then, of course, where we were sampling, as well as higher CO mixing ratios. Although I'll note from the color bar that the CO sort of mixing ratios that are shown from the observations in satellite are far less than what we observe by aircraft. So that's giving us a reason why these targeted airborne observations are really helpful. And I would say that the scientists and the instrument teams in the field were not the only thing that was surprised by this magnitude of CO observations, but our modeling forecasts were also quite surprised, I would say, by seeing these magnitudes here as well. So I've done the same plot essentially on the right now. All the observations are in black, but the red and blue lines are two different in-field model forecasts, one from the Musica model, that's that animation I showed at the beginning, and then also the GEOS model from NASA that's in the field. And so I would say overall the models are actually doing a pretty good job, but there is this sort of highest pollution signatures in the UT, this in excess of 300 ppb that's just missing from the models as well. So this sort of prompts and motivates the need for some sort of transport analysis to try to understand what's the origin, what's the sort of reason why we're seeing these observations. And so for this, we've done some transport analysis, essentially launching backward trajectories from the aircraft at 60-second intervals. And integrating them backwards for 30 days using analysis winds. And we trace these trajectories through a field of satellite-derived convective cloud top altitudes. Those are derived from rainfall rates as well as brightness temperatures from satellite. And what we're interested in is for a given aircraft observation, tracing backwards in time, the first, that would be the most recent influence with convection, where we have an altitude of the trajectory that's lower than the top of the convective cloud that's co-located with it as well. And so this can give us some window into sort of the transport origins contributing to the campaign. So here are some results from that transport calculation, and I can keep the discussion of the different different analysis products going here actually as a result of this slide here. But what we're looking at here is relative frequency distributions of this most recent convective contribution to the ACLIP campaign for the full campaign's sampling. On top is a calculation from the Global Forecasting System, or GFS, and what we used that for was we used that for in-field forecasting, actually in-field transport forecasting, as well as post-flight target verification when we were in the field. But since the campaign, a couple months later, when these higher resolution reanalysis fields become available, we've redone the analysis, and I think the comparison is interesting because I would say qualitatively the story is relatively the same, but quantitatively there are certainly some differences. So the things that sort of pop out here, two primary regions of convective contribution to our ACLIP sampling in 2022. The first one is Southern Asia, Northern India, sort of the southern flank of the Tibetan Plateau. And that's been talked about in a number of talks, but I'll say again here that that's typically regarded as the primary sort of uplift region. Is this Southern Asian source is typically regarded as the primary region of feeding the anticyclone. But because of our sampling location in the Western Pacific, we were then also able to capture another primary sort of convective outflow region, and that was along the East Asian subtropical front, sort of more local, or sorry, closer upstream to our measurement locations. These plots here that popped up are transit time distributions. So this is the amount of time it takes for the transport calculation to go from the aircraft to the most recent convective influence. And I've broken this down by aircraft, still color-coded here. And I think what pops out from this is that the G5, again, that's in cyan, is considerably enhanced convective contribution and faster transport to convection, or faster transport, more recent sense convection, I should say. And that's primarily due to the different sampling altitudes for these two different aircraft. I showed earlier the WB-57 at much higher altitude, so it makes sense that it would take longer for convective outflow to reach those altitudes as well. I've marked here also in the legend the percentages of 30-day, of the percentages of convective influence within 30 days, and these are quite a bit different actually between the analysis products here as well. There's considerably larger convective contribution from ERA5, and we think that that's mostly to do with the higher spatial and temporal resolution, especially when convection is an important process. The ERA5 is available hourly, and so that gives us probably some better information. And in an effort to avoid the rest of this presentation being about the analysis products, I'm just mentioning, I think it's an interesting thing to mention here, but I'm going to stick with the ERA5 for the rest of the way here. What else can we do with this product? So this figure here shows the transit time to convective influence as a function of aircraft sampling altitude. So for the very large swath of aircraft altitude that was covered during the campaign, what's sort of the distribution of transit times at the different sampling altitudes. And so I think what pops out from this here is that throughout the free troposphere, and maybe up to 14 or 15 kilometers, the mean time for convective outflow to reach the aircraft observations is maybe about a week, but more or less constant throughout this layer in general. But after you reach that point at about 15 kilometers or so, the time since convection gradually increases, maybe by about 5 days per kilometer. And so that's giving some influence of sort of where the large scale transport by the monsoon anticyclone is taking over. And obviously, the whole reason we launched these trajectories from the aircraft rather than just everywhere over the Western Pacific is because we want to actually compare against the aircraft observations. So here's an attempt to do that. On the x-axis here is the time to convection from the aircraft, and on the y-axis is observations of CO taken along the flight tracks. And so again, we're comparing back to that previous figure I showed of the CO versus altitude, and you can see that all of those very high, I used the word unprecedented before, all of those very high mixing ratios of CO were associated with very rapid or very fresh convective outflow. And this makes physical sense. It's nice to see that the trajectory calculation is giving a reasonable answer. I also have a couple of dotted lines and dashed lines on here, looking at different sort of loss rates of CO, theoretical CO loss rates, and really highlighting that CO tends to be lost relatively quickly since convection over the first few days or so. And this is probably due to mixing and dilution, and also a combination of mixing, dilution, and enhanced OH concentrations probably in these convective plumes as well that would cause CO to attenuate faster. But after maybe a week or so, the sort of expected 60-day lifetime tends to be the what's followed by CO. And then sort of a preliminary analysis, expanding this actually to try to address the impact of dilution, or maybe back out the impact of dilution. We're working with some of the other instrument teams on hydrocarbon ratios and trying to use that as a sort of a clock to understand how the trajectory results compare to the actual chemical clock, if you will. And so this is an example of sort of the same thing you see on the left, except for it's the ratio between propane and ethane. And you can see that this sort of theoretical loss rate, the dashed line based on the documented lifetimes of these species, is somewhat overall representative, but we still have a lot to do with that as well. Another thing that we can do with these trajectory statistics is we can actually look at individual sampling for specific flights and sort of interesting sampling events. We can actually target these more closely with the transport statistics. I showed the whole flights or the whole campaign before, but these are examples specifically for August 6th and August 7th. And I show these, I think that they're relatively representative of the sort of diversity of different gradients that we sampled during this campaign. On August 6th, both the G5 and the WB57 flew. And so you can see on the top right panel there, the altitude coverage there, as well as they're colored by CO observation. And on the bottom row here is August 7th, the G5 was able to fly consecutive days and get an idea of sort of the temporal gradient. How is this air mass aging? And there's two primary regions of a convective contribution on this particular day. There's this convective complex in very far northeastern China, as well as the more distant source of this Southern Asia, sort of southern flank of the Tibetan Plateau type of outflow. And so I'm using those boxes to very kind of crudely break down and do some analysis here to understand sort of the different contributions of those to these flights. This is transit time distributions for the two different flights from the two different regions of convective contribution. And so you see a pretty night and day difference between the transit time from convection to the aircraft for the two different sources. The August 6th sampling was 1 to 2 days removed from convection. The August 7th was 2 to 3 days. So again, makes sense waiting a day between sampling. But the Southern Asia source is on the order of weeks to a month or something like that. And so that gives you some idea of the very different sort of contrasting air masses that were sampled on this day. So then a natural question then is, how did the the chemical observations sort of respond to that or behave in response to that? And so this is the same, color coded the same, but this is the CO distributions. And so you see certainly a much higher CO mixing ratios for this very fresh outflow from Northeastern Asia. I think it's interesting to point out as well that on the sampling on consecutive days, the CO attenuated by maybe 20 parts per billion or something in just a single day of sampling. So that's kind of consistent with the previous arguments of faster loss right away in these. And I also want to mention something about the aircraft altitude as well, and what sort of controls what was being sampled at a given point. So this is the same sort of analysis, but color coded by aircraft altitude. So where were we sampling these different sort of convective outflow regions? And this, I think it's worth pointing out that the Northeastern Asia source, the one that was the most nearby, was really only sampleable between about 11 and 15 kilometers. And as the aircraft were to rise above that point, the only sort of convective source available is the more distant Southern Asia source. And so that gives you an idea of the sort of top of this the Northeastern Asia convective event had a sort of a discrete top, and above that point is where you sample the broader sort of anticyclone with its primary source in Southern Asia. And so here's kind of a crude schematic that I worked with some scientists at ACOM or at NCAR to put together. And so this idea that we have this Southern Asian convective outflow that we expect to see, but because of our sampling region at the lower altitude, I don't want to say lower altitudes, but up to maybe the 14 or 15 kilometers or so, this South Asian outflow source was sort of obscured by this this fresher and very potent pollution signatures from Eastern Asia as well. And I should emphasize too, I put the level of zero radiative heating on this plot here as well to really emphasize that air masses will preferentially continue to rise at these altitudes. And so this is sort of the importance of this mechanism in mixing with the global atmosphere. And here's one final sort of analysis slide on looking at that in the forward sense. So actually this plot on the left looks exactly like a figure you've already seen, but I've switched it up. This is actually dichloromethane. So this is a source of short-lived chlorinated species that are important for ozone chemistry. And on the right is a distribution from forward trajectories, actually, running from the troposphere and until it reaches the tropopause and crosses into the stratosphere. And so you can see that these very high observations of dichloromethane in excess of 200, 400, 600 even parts per trillion are indeed having a future in crossing the tropopause, and where they can certainly have more global impacts as a result of this transport mechanism. Okay. So just moving on and summarizing here, I hope I've showed you all that the 2022 ACLIP campaign has provided a unique data set to investigate the role of the Asian monsoon in impacting global composition and climate. I failed to mention earlier, I will mention now, that the airborne data for ACLIP is available and publicly. So if anyone is interested in taking a look at this data set for your own research, I'm happy to set you up with the link to do so. From this talk and this transport overview, we've see deep convective outflow from two sort of primary monsoon subsystems that contributed to our sampling. We had the East Asian subtropical front with the enhanced pollution in a fresh outflow, and South Asian monsoon, which is again typically regarded as the primary source, but we can see that at a higher altitude, extending to a higher altitude. I didn't talk too much about this, but I think it's worth noting that the impact of Asian monsoon convective outflow on the composition of the UTLS may be underestimated by satellite observations, as well as coarse grid global models. And so I think that these targeted airborne observations give us that sort of a lens with which to view that. And then finally, just maybe more broadly, the transport statistics that I've shown here as an example can provide a valuable context for airborne measurements. And I'll just throw out a final note that the science applications will probably benefit from higher resolution analysis wind fields if convection is an important process that we want to consider. So here's my acknowledgement slide. Thank you again to the organizers for having me. And I have a QR code here. There were some figures that I snagged from Laura Pan's recent ACLIP science highlight paper that was recently published a month or two ago in PNAS for anyone who wants more information. So I'll stop there. Thank you.
Thank you very much for this very interesting insight and this interesting case study. We have time for a couple of questions. Are there any? Yeah.
Yeah, great talk. Question about, you showed that the CO, the large CO values came mainly from East Asia. And can you say something about the aerosols? Is it the same for the aerosols, or do they come mainly from the South Asia?
I think you could I think from memory, there were a lot of new particle formation events that we sampled during that had sort of a co-location with the highest CO values. And so I think that that's one very interesting part of this. From the aerosol point of view, we also were able to sample sort of the bottom, at least on the G5, we were able to sample sort of the bottom of the ATAL layer from the ERICA instrument was on board the G5 also, and they flew, of course, during stratoclim. And so I think that the aerosols, I haven't looked too closely at the aerosols myself, but I think there's an interesting story that one could tell. And I know that the ERICA team is working with some of these transport statistics as well to try to break down the contribution from different regions.
May I another one? Okay, just another. You said that the difference between ERA 5 and the other model was due to the different resolution. But I thought the places where convection occurring is not from the models, but is you deduced it from the satellite measurements. So why is it then so different between the two models?
Yeah, I think so. Yes, the convection is from a satellite-based data set, but I think that the trajectories respond to the presence of real convection that's assimilated into these reanalysis products. And so especially with an hourly temporal output, which we think is probably the most critical for that difference, you get some certain convective features that don't get smoothed out between, six hourly time steps. So I think the observations of convection themselves are included or at least factored into the reanalysis models, and it just is able to sort of manifest or be come forward a little bit more in those higher resolution products.
Very interesting talk.
Thank you.
So I got fascinated by your slide where you show higher convective height over the South Asia compared to East Asia. So it is sampled by the aircraft measurement, or how you derive that?
It's sample. Could you say the last part again?
You have shown that outflow from South Asia and East Asia, one figure, where you show outflow from South Asia is at a higher altitude compared to East Asia. So this is just a schematic, or this is from the aircraft observation?
This is from the aircraft observations and the integration with the transport statistics. So we have, there's an example. I gave this example here for the case study. We've shown this to be the case for really the whole campaign as well, where the Eastern Asia sort of has a discrete top to it that we were able to sort of sample different gradients across that. And there were a few times actually this day included where we were able to change altitude over a very narrow vertical layer, and you would see a drastic change in the pollution signatures over that layer. And so the transport statistics indicate that the difference is really because you've got outflow from one of these regions or the other.
Interesting.
Thank you.
Okay, any other question?
Hello. Yeah, very interesting talks. It's very nice to see the convective contribution in this the pollution transport. We have brought out a very interesting result. So I have just some relationship. When we see the satellite product, so this convective strength, and mostly it is satellite products and convective strength and this pollution. It's not all the time it is linearly it is implementing. This means like a convective strength increases how this transport is. We generally expect that it is increases with linearly. It has to the pollution has to transport to the UTLS, but in satellite mostly it is likely to be inhomogeneous. Not all the things is contributing. So in this flight campaign, how you have seen something like the relationship between like the strength between the convective strength and the transport to the UTLS, because you have seen some large values in the CO I have seen in your plot. So is it any relation you have brought out something like that?
So you're asking if there's a relationship between the strength of convection itself as well and the pollution observations?
Yes, it is a linear, or it is like a.
Interesting. I think one other important aspect of it though too is also the emissions values beneath the convection as well. So it's not just necessarily the strength of convection and how much mass, if you will, of air is being wafted up. That's also the starting point value from below that also then would contribute to that as well. But I'm not sure if it's a linear relationship or if it's more exponential. I think maybe there's some mass flux calculations or something that we should look into to try to sort of separate that a little bit better.
Thank you for that.
Yeah.
So also thank you for the questions, and thank you, Ren, for the presentation. I think we move on with the regular talks. Next speaker is Dr. Amit Kumar Pandit from the NIA in the US as well. And he will speak about in situ and satellite observations of tropopause cirrus clouds during the Asian summer monsoon results from the Betel campaign. The mic is not working.
Good morning, everyone. My name is Amit Kumar Pandit, and I'm from National Institute of Aerospace in Hampton, Virginia, USA, and I work with Dr. John Paul Vernier. Before I begin, I would like to thank everybody, thank the organizing committee of this wonderful workshop and EPARC for providing me travel support and giving me opportunity to present my work here in this workshop. So as you are aware that we had balloon campaigns in India at different locations starting in 2014 to 2019. And we studied the physical and chemical properties of the Asian tropopause aerosol layers. During the same campaign, we also conducted balloon flights for measuring ice crystals near the tropopause region. And I'm going to present some of those results in this talk. So this is the outline of my talk. I will briefly explain what are cirrus clouds and how they are associated with the Asian summer monsoon and the motivation and objectives of this study, followed by instruments we used during the Betal campaign to measure ice crystals. And I will present a case of tropopause cirrus cloud layer observed from Hyderabad on 23rd August, where we estimated microphysical properties and also investigated the formation mechanism of the tropopause cirrus cloud. Finally, I will summarize my talk. So cirrus clouds are thin, wispy, cold, high-altitude clouds, predominantly consisting of ice crystals. They form from mainly two different mechanisms. One is by deep convective clouds, from where you get anvil cirrus, and the other mechanism is through in situ formation, where ice nucleates on some ice nuclei aerosol particles, and they are also formed due to homogeneous nucleation of aqueous solutions, and they are formed near the tropopause. They are very thin, mostly subvisible, and most of them are related to gravity wave activities in the TTL region. And I'm going to talk about those type of clouds in this talk. And the microphysical properties of cirrus clouds depend the number concentration, size distribution. These are microphysical properties, and the radiative impact. The net radiative impact of these clouds is positive, unlike other clouds types. However, there is large uncertainty in the magnitude of this warming because of large variability observed in number, concentration, size, and shape distributions of ice crystals, especially in those clouds where you have smaller ice crystals, smaller than 100 microns. And the satellite estimates of number concentration is not that accurate. So we need to have balloon bond measurements. There is a nice animation provided by Dr. Chris Bedka from yeah, so it shows the diurnal variation of anvil clouds over Asian monsoon region, and you can see that it peaks. Then anvil cloud peaks in the late afternoon and early evening hours, and this region is Bay of Bengal and the east coast of India, where we see these deep convective clouds and the anvil formation, and they move by the tropical easterly jets toward Hyderabad. So if you look at the temperature over the Asian monsoon region at 100 hectopascal, this is 10-year mean from era 5. You can see colder region in this latitude band and temperature reaching about 80 degrees Celsius. Even we have observed further colder temperatures. And there is a tropical easterly jet which brings anvil cirrus towards our location. So TIFR balloon facility, from where we did this balloon campaign, is the right location to study these kind of clouds. And these clouds near the tropopause are well correlated with the negative temperature anomaly as seen from this plot, which is homolar diagram. And you can see the negative contours are negative temperature, sorry, blue contours are negative temperature anomaly, while the red ones are warm temperature anomaly. And you can see the blue and red dots are cloud observations above 16 kilometer altitude from Calliope and CATS LiDAR. And you can see a good correlation between the negative temperature anomaly and these cirrus clouds. The formation of these cirrus clouds near the tropopause leads to dehydration, as you can see from the mean water vapor mixing ratio profile for the month of June, July, August for the entire SAGE observations from 2017 to 2013 over this region. And you can see near the tropopause very small concentration of water vapor, mainly due to the presence of these thin cirrus clouds, which dehydrates the tropopause. And there are few campaigns like StratoClim, Eclipse, and some balloon campaigns in China, SWAP, and Betal, but still we need more in situ data for ice measurements. And this is the objective of this study. So these are the instruments which we use during the balloon campaign. And this is backscatter zone, cobalt, which provides backscatter ratio at 2 wavelengths. And from those ratio, you can derive color ratio. We also use an optical particle counter, which provides particle concentration at 6 size channels, starting from 5 micron to 100 micron. And then we used a miniaturized version of payload, which was used during the NASA ATREX mission to find out the size and shape distributions of ice crystals. So this provides size and shape distribution of particles using 3 different sensors, one providing size distribution from 1 to 50 micron and others from 25 to few mm. And there is a particle imager which provides you particle images in those clouds. So this is a this is the occurrence frequency of cirrus clouds obtained from cobalt backscatter zone. And you can see there is a high occurrence frequency of cirrus clouds near the tropopause. And some of those flights had the boulder counter in, also we used boulder counter and the CPI simultaneously to see the particle concentration and shape of those ice crystals. And we can see that most of the time in those clouds, particles were smaller than 100 microns, and they were quasi-spheroid in shape. Coming to the case study of tropopause cirrus cloud on 23rd August from TIFR balloon facility. This is a vertical profile of backscatter ratio at 2 wavelengths, red and blue, and the black one is the color ratio by taking the ratio of these 2 backscatter ratios. So you can see that there is a color ratio approaching 1, which means these layers are cloud layers. And interestingly, there is a cloud layers near the cold point tropopause, and the tropopause temperature was very cold. It was about -86.4 degrees Celsius, and simultaneous measurements from boulder counter suggested that the ice crystals in this cloud were smaller than 50 microns in diameter. Our measurements were also corroborated by the CATS measurement, which is a spaceborne LiDAR, which was a spaceborne LiDAR on International Space Station. So this is the balloon flight track from TIFR balloon facility, and this is the location of tropopause cirrus clouds during ascent, and this is during the descent. This is the overpass few hours later of ISS, where CATS observed cloud at similar altitude, and these are the profiles during the ascent and descent, which look similar to the CATS observations. And the depolarization ratio between 0.4 to 0.5 suggests that these are basically ice crystals. And we also looked at water vapor from ERA 5 and temperature to derive relative humidity with respect to ice, and we see high supersaturation near the tropopause. And we looked at the microphysical properties for this case study by fitting a log normal distribution to this particle concentration, and we derived effective radius, effective diameter, extinction coefficient, ice water content, and these are listed in this table at different altitudes. And one interesting thing to note that we have simultaneous measurement from backscatter zone and extinction from particle size distribution, which can be used to derive LiDAR ratio, which is important quantity for cirrus clouds. And we have done it for different altitudes. That is really unique. And coming to the formation mechanism of this tropopause cirrus cloud, so we initialize back trajectories from the location of cirrus clouds. You can see these back trajectories, which are 5 days back trajectory from the initialized altitude between 16 to 19 kilometer. And when you look at the altitude altitude cross section of this trajectory, you can see that there is these air parcels are coming from altitudes below 15 kilometer, which suggests that it is coming from the lower altitudes. And you can also see at the same altitude there is some kind of circular motion. When we looked at Himawari 8 brightness temperature data, we found that there was a typhoon developed over South China Sea, and which hit Macau and Hong Kong area on 23rd August. And this was the main reason for this air parcels coming from the bottom. And there was a Calypso overpass on 20th August 2017, which went across this typhoon, and it observed overshoot from that typhoon, and that I'm going to show in the next slide. So this is the developing typhoon on 20th August, and you can see the Calypso overpass, and there was simultaneous measurement from MLS, and this profile shows the overshoot here, as we can see from backscatter ratio of at 532 nanometer at different LiDAR footprints. And simultaneous measurement from MLS shows enhanced water vapor near 83 hectopascal, which suggests some hydration patch due to this overshoot. And that is clearly seen in the ERA 5 water vapor mixing ratio at 70 hectopascal on 22nd August 2017 at 9 UTC, when the overshoots were at their peak. And you can see this hydration patch. And due to the tropical easterly jet, this moved towards Hyderabad and might have led to the formation of tropopause cirrus clouds. And you can see these are the trajectories in near 70 hectopascal level, and this is the mean of water vapor for the 22nd and 23rd August. And this is the Hove-Moeller plot for water vapor mixing ratio anomaly for the month of August, so longitude versus time. And this is you can see a positive anomaly moving towards Hyderabad longitude, shown by horizontal dashed line. And this is the typhoon track. And the dots, magenta dots, are MLS observations. So this hydration patch was moving towards Hyderabad longitude, and you can see it reached on 23rd and 24th night. And this enhanced water vapor, you can see from 20th August to 21st August and reaching towards Hyderabad, and it reduces in time. So this water vapor could be the source of cirrus clouds along the back trajectory, and for that we see the temperature along the back trajectory, and you can see quasi-periodic cold temperature in this, and simultaneous during the same time co-located observations, near co-located observations from Cobalt, CATS, and the Calliope LiDAR showed the tropopause cirrus clouds in these cold temperature anomaly regions. And these black dots are the overshoot from obtained from Himawari 8 data. And when we looked at the, there is one more slide. So when we looked at the updraft from along the back trajectory, we can see that these cold temperature anomalies are associated with updraft, which means they might have lifted the air parcels and which cooled and led to the formation of cirrus clouds. And there is a quasi-periodic structures which could be associated with gravity waves. And for that, we did this anomaly in temperature, zonal and meridional wind, and we can see different structures which are related to gravity waves. So finally, I would like to conclude. We did balloon measurements of ice crystals during the Betal campaign, and we found ice crystals were quasi-spheroid and smaller than 100 micron. And we also studied a case of tropopause cirrus clouds, and the formation mechanism was investigated, and its influence was linked to a category 3 typhoon due to hydration and gravity waves. Thank you very much for your kind attention.
So thank you. Okay, it's working. So thank you very much for your talk. I guess it's a bit unfortunate that we used up the time, so there won't be questions, but maybe you can discuss the results and further discuss this during coffee break then. I would then urge to move on with our next speaker. This is an online presentation by Siddharth Shankar Das from VSSC here in India. And he will speak about the network of ST and MST radars, balloon-borne measurement campaigns of the Asian summer monsoon anticyclone initial results. So,
Good morning. Can you hear me?
I can see him already. So,
Good morning. Can you hear me?
yeah, we can hear you very well. So, could you
Yeah,
put up
I
your
need to
slides?
share the screen. Host has to allow me to share the screen.
No, he's gone.
Host has disabled the sharing screen. It has to be allowed.
Okay, so it's okay. You've got permission. You could share your slides.
No, host has disabled the screen sharing, so I am not able to share the screen.
Okay, can we fix that? Yeah, it should be fixed. You get the sign. It should be fixed.
Yeah,
So
now
it
it's
should
okay. Fine. Yeah.
Right. And just, yeah. All right. Okay, you see it very well. So get started, please.
Okay. Yeah. Good morning to one and all. Hope my slide is visible there. First of all, I would like to thanks to the organizer for providing me this opportunity to present online, because I was about to come physically, but somehow I could not make it. So just a minute. Yeah. So my presentation will be on the network of ST and MST radar and the balloon-borne measurement campaign of the Asian summer monsoon anticyclone. This is a NetRad ASMA campaign we have conducted. This is the first phase of the results which I will be presenting over here. And myself is Siddharth from Space Physics Laboratory of Vikram Sarabhai Space Center, Trivandrum. And you can see there are a lot of people who are involved in this campaign, starting from your IITM is also there, NARL, then Kochi universities, Calcutta universities, many people are there. So many center has participated in this campaign. So my outline will be like introduction. First, what exactly I wanted to do that one, and the network of the ST and MST radar over the India. And background, the motivation, few results which I will present from the long-term measurement which has been done over the Gadanki MST radar. Nearly 2 decades of experiment were conducted from last 1995 onwards. Then the present experiment and the campaign, and I will present some preliminary results which I got from the first phase 1 experiment and what we are planning for the future. So as you know, there are the different processes happening, because like a lot of my previous speaker has already presented, there are the stratosphere which is a ozone ridge, and the troposphere which is just, yeah. So you can see the stratosphere is the ozone ridge, and humidity is very less, but that humidity play an important role in the climate and weather system of the weather system in the atmosphere. Whereas in the troposphere is highly humid, and when once the water vapor pump into the stratosphere, there will be the distraction of ozone, and these type of things are mostly happening over the tropics as well as the subtropics. So overshooting convection, stratospheric intrusion, that is ozone intrusion, atmospheric gravity wave, instability, atmospheric circulation, that is a BDC, because ozone produced over the tropics and gives to move toward the pole, Walker circulation, and extreme weather condition like tropical cyclone, and both have a radiative impact on the global atmosphere. As I said, if you see the tropics, that is equator, where the most of the convection are taking place over this location, and we have a subtropic. So India is fascinated having these both tropic and subtropics, and we have a network of the radar, which I will be presenting in my next slide. And this is the what actually ASMA says, that most of the pumping is happening from the other pollution or the water vapor or the minor constituent from the lower atmosphere to the stratosphere. As you know, these are the different parameters which we require for our atmospheric dynamic study. That is the zonal wind, meridional wind, vertical wind, temperature, ozone partial pressure, and water vapor apart from other minor constituents, like my previous speaker was showing many other minor constituents we can measure, but these are the basic main parameter. Out of this main parameter, we can measure all those information from the different sondes or satellite measurement. But if you see the vertical velocity measurement, this is only which profiling can be given by the radar. So radar is the most essential, and vertical velocity, you know what are the importance of the vertical velocity in the transport process. So this is where my area where I will be focusing on that. Because of this vertical velocity, only the radar can give, no other measurement is giving. Even aircraft give that indirect measurement, reanalysis give also indirect measurement, but direct measurement from the radar. And if you see the Indian summer and Asian summer monsoon cyclone, if you see the first panel is the ozone, how it changes from the month to month, and you can see there is a transport of the subtropics ozone to the Indian Peninsula region, where the high ozone concentration is observed. Whereas the water vapor, most of the pumping is occurring over the Asian summer monsoon anticyclone. Inside the anticyclone, most of the pumping is occurring. That is actually the water world of the atmosphere. And we are fortunate to have this radar network, which we can have different zonal, meridional, and vertical wind velocity, as well as the turbulence parameter, because the mixing process takes place in terms of the turbulence. So you can see, starting from the Nainital, which is the subtropics, then we are having a Calcutta, that is the second one, second radar. Then we have a Guwahati, Calcutta, Guwahati. Then we are having over the Gadanki, and we are having a Cochin University. So these are the 5 radars at the different location of the Asma region in the eastern coast, as well as in the northern part of the India. As a past result, I will just present some few past results, because which motivated me to conduct this experiment in terms of the network. So if you see, during the passage of a tropical cyclone, we can see the stratospheric intrusion, means stratospheric air coming from the stratosphere to the troposphere. Earlier, we used to have a measurement with the like ozone sonde measurement can give the ozone concentration, or this stratospheric air can come down to the atmosphere, which was measured by the ozone sonde. But if you see, using the signal to noise ratio of the radar, we can have this like a stratospheric intrusion, and you can see the turbulence, the intensity of turbulence. This is the height scale, and this is the time scale. You can see as the time progresses, the stratospheric air come to the troposphere. Then there are the tropopause weakening, because radio sonde can give you a perfect measurement of the tropopause, but whether the tropopause is weakening, because the tropopause is a stable layer, and whether it is weakening or not, that can be perfectly measured by the radar continuous measurement temporal variability. You can see when the tropopause weakening is occurring, because this is the tropopause height, and you can see the signal to noise ratio as propagating downward. So you can see there is a propagation of the stratospheric air to the troposphere. So this is what we measure. And you can see there is a vertical velocity. The blue color is the downdraft in my measurement. And you can see the downdraft also follow the same as the signal to noise ratio. We can estimate the mass flux, the indirect measurement, like the perturbation in the vertical velocity multiplied by the density. You can give the mass flux, how much mass exchange is taking place across the tropopause. So this is the measurement during the mesoscale convective system from the radar. And you can see there are when the tropical cyclone passed, that Gadanki radar, we have observed like a stratospheric intrusion, the weakening of the tropopause was there. This is the Calypso data, where you can see the tall cloud, the cumulonimbus cloud penetrate up to the tropopause. It got much above the tropopause. The water vapor is pumped. And this was the ozone sonde measurement. You can see the ozone enhancement started taking place, and it is reached to the ground level. This was measured by the ozone sonde and simultaneous radar. So I mean to say that the radar independently we can measure the stratospheric intrusion, the exchange processes happening over the tropics as well as the subtropics. And earlier we observed, so I have shown the one figure that the mid latitude, the ozone from the mid latitude comes to the Indian Peninsula region, where we observed during the June, July, August along the tropical easterly jet, we observed the enhanced ozone over the Gadanki region. And this observation we made it from the radar. If you see the signal to noise ratio, and this is the tropopause high from the radio sonde measurement, and you can see the enhancement of the signal to noise ratio exactly occurred during the June, July, August, when the tropical easterly jet is very high. And you can see the spectral width measurement from the radar, which shows the intensity of the turbulence. So you can see the lower atmosphere during June, July, August, it is expected to have a more turbulence. But if you see near the tropopause, which is considered to be a stable layer, but you observe a very strong turbulence occurring over that location. So this is the mixing processes happening because of the tropical easterly jet, and you can have a shear instability occurring near to the tropopause. Then another observation, because now all the radars are in the active aperture mode, means you can tilt the beam plus or minus 20 degree, as well as you can scan like 360 degree in azimuth. It is work almost like a Doppler of the radar. You can steer your beam. So in that we observe that a stable layer occurring during the passage of the tropical cyclone. When there is a non-convective system, such type of layer structures are not observed. So this layer structure shows that there is a well mixing taking place over that location, which may be because of your shear instability. So mass exchange is taking place near to the tropopause. So this is the Kelvin-Helmholtz instability, a very peculiar case of Kelvin-Helmholtz instability. You can see the bulb structure and you can see the inclined structure, two different cases of the Kelvin-Helmholtz instability. And now most of the people, even including me also, I used to use the reanalysis data for our vertical velocity, because that give a omega, that Pascal per second, we convert into the meter per second. But when we try to compare with the direct measurement of the vertical velocity, it never match. The reanalysis, none of the reanalysis never match, because we have done with ERA 5, ERA interim reanalysis, because the vertical velocity, what we measure from the radar, is highly localized and which is not been captured by the which is not been captured by any reanalysis or other measurement. So this radar give you see there is a, like for example, if I will say there is a very strong updraft which we can see from the radar, but where the reanalysis shows all downdraft. So this is an average picture we are getting. So that's why we should have a measurement of the radar. Now, because of the network of radar, we will be able to do. Now, the few campaign results, what we did with the radar. These are the different radio sondi and ozone sondi launched from the different 7 stations, like Balasore, Gadanki, Bhopal, Pune, Trivandrum, Nainital, Cochin, over all the Asian Southern Monsoon region. And we have launched some places ozone sondi also to capture what exactly happening. Then we have the 4 radar was operated, except the Guwahati, all other radar was operated. So this is the radio sondi station over the Balasore. Recently we made it, and this will be a long-term measurement of ozone measurement will be there from the ISRO side. And we will measure continuously over the Balasore. So this is just a lab setup we did, and we started launching the balloon. And if you see, during the month of February, we did the experiment, and most of the balloon which was launched at Balasore is traveling nearly 120 to 140 kilometer apart from the Balasore. So the measurement which we are taking is over the head Bay of Bengal, that is Gangasagar Island, and you can see the balloon was launched here, but it tracked over here. So what we observe, we have a strong westerlies over that location. That's why that balloon drift was very, very high. It was nearly 60 meters per second. And very peculiar feature, this is an ozone sondi profile. This is what actually I was telling you. See, there is a enhancement of the ozone which was observed nearly 20 kilometers. Very strong enhancement. When first we did the launch, we thought that there may be a spurious data or there may be some error in the measurement. So immediately after the 6 hours of the experiment, again we got the approval from the airport authority, because we have to launch the very high altitude balloon. We require the ATC clearance. So once immediately we launch the ATC, launch the ozone sondi, you see the enhancement is still there. So what we observe in this is at the 3 o'clock, this is at 9 o'clock. So you see the enhancement was there. This was next day 3 o'clock. The still enhancement of the ozone was observed. Very layer structure. Then once after 3 days, we do not have any such type of layer structure which we observe over that location. Then we launched simultaneously over the other location from the Trivandrum as well as from the Gadanki and Nainital. We never observed this type of structure. This structure was observed only over the head Bay of Bengal. Then we have fortunate to have.
Dr. Das,
Yeah?
please come to the end. Please come to the end.
Yeah. I'm just
up.
2 slides there. So then you can see there is a MLS pass. We observe the same enhancement of the ozone observation from the MLS. Then we conducted the radar measurement. The most important part is that the Calcutta radar, when it was observed, you see most of the turbulence activity was taking place on the lower atmosphere, which is one of the like a wave generated and deposit its energy in the atmosphere. Cochin do not show such observations like instability. Nainital have that instability because it is near to the north, more stable. What is that spectral which was observed? So this we have proposed. That the enhancement was because of the horizontal transport, that is change in the circulation. It is related to the BDC, or there is some in situ observation, or atmospheric breathing. That is like a compression of the air or relaxation. So which made the enhancement of the ozone. And since this is a phase 1 experiment, so we cannot conclude the fully that because of what reason it happened. Now we are conducting this phase 2 experiment during the monsoon time. So thank you very much.
Yeah, so thank you very much, Dr. Das, for this very interesting presentation. In the interest of time, I don't know, I would really try to keep on here going with the talks. Thank you very much, Dr. Dust,
Yeah,
for
thank you.
for your presentation, for this insight. And I would say we continue with our last talk for this session, which is by Dr. Sanit Kumar, also from the VSSC here in India. And he will talk about insights from the tropical tropopause dynamics experiments under Garnett's program over the Indian monsoon region. So please, Dr. Kumar.
Yeah. Good morning to all. Myself, Sunil Kumar from Space Physics Laboratory, Vikram Sarabhai Space Center, ISRO. So I'll be giving some of the glimpses of the balloon sounding experiments carried out as part of the tropical tropopause dynamics experiment under the Garnett's program. That is GPS-aided network experiments for troposphere stratospheric studies. So this program has started 10 years before in 2014. And we would like to address the turbulence, convection, radiation, the large-scale transport, cloud microphysics, tropical waves, as well as chemistry, the key TTL processes. In this objective, we have carried out several experiments over the Indian region. The uniqueness of the Indian region is large-scale annual variation in the ITCZ, and the unique feature is the monsoon dynamics. That is the anticyclonic circulation situated over the Indian region and associated with the tropical easterly jet. And it is the major source of the water vapor is over the head Bay of Bengal, which is pumping a lot of water vapor to in this region. And the figure which shows here is the frequency of deep convection with the clouds greater than 12 kilometers using Kalpana observations. You can clearly see that during December, January, February, it is devoid of the clouds, whereas in March, April, May, you can see the enhancement in clouds over this region, and the white line shows the overshooting convection, whereas during June, July, August, the deepest clouds over the region, the whole tropical region is at this location, along with the overshooting convection. And so we have selected the focus of the study at the hotspots regions, the Calcutta region near Haringata and Kharagpur, and the closest to the deepest convection is Hyderabad, and much away from the deepest convection is Trivandrum. So these are the 4 locations what we selected for our study, and more focused campaigns has been conducted. And these are the details of the campaign. So mostly we carried out the in situ measurements of water vapor, ozone, temperature, and winds at finer vertical resolution using the balloon-borne sensors. And these are the details of the balloon experiments carried out. And we have some small stations close to Trivandrum also. We have carried out observations at Mahendragiri, Coimbatore, Cochin, and the more focused the CFH observations, ozone sonde, and observations were carried out from regular monthly campaigns. Systematic campaigns in all the months has been carried out at Trivandrum as well as in Hyderabad. And the more focused campaign during the monsoon months and the pre-monsoon months has been carried out over the head Bay of Bengal near the Kolkata region. So these are the statistics what we shown. It's the number of the flights around more than about 150 CFH flights has been carried out for the last 10 years, and we have ample of ozone sonde observations, and we have brought out some interesting results. So these are some of the activities. So mostly we do the experiments combining both the GPS, ozone sonde, and the hygrometer together as a payload in most of the campaigns. And based on the TTD campaigns during the COSAS as well as in the Garnett's program, we have derived a new perspective of the TTL based on the static stability criteria, and we defined the boundaries. And we have come out with the redefining the upper boundary of the TTL, and it's defined as the level of the maximum stability, where Ratnam has shown where the other layer above the CPT, which is matching with the definition of this redefined boundary, which the upper, that means the TTL top is not at the tropopause CPT, it is just about close to 1 kilometer above the CPT. So it is not only from the radius on the observations, it is confirmed the TTL base, which is identified from the stability criteria, is matching exactly with the divergence profile obtained from the radar measurements. So that is the top of the TTL base is considered as the top of all major convective outflows. So the typical profile shown here is shown here from the CFH observations and the ozone sonde observations. And so here also we can see just between the CPT and the top layer, TTL top, you can see the layer type of the relative humidity profile, which is matching with the other layer. So some of the, also we had observations over the Indian Ocean during 2018, some of the typical profiles I'm showing here, which shows interesting, within a 14-degree north to equator and 2 degrees south, we have carried out seven experiments during January 2018. Where the temperature shows much variation, and accordingly we can see the variation in the cold point tropopause region. What is the water vapor mixing ratio? It shows the freezing much below, several times when the temperature is going below 185 Kelvin, the mixing ratio is going down, which indicates the freeze drying mechanism over the equatorial region. So so next, using the different, we have made an intercomparison between the CFH and the MLS derived water vapor measurements, which showed that the MLS derived mean difference is, or MLS is overestimating at the lower altitude below 50 hectopascal, whereas it is another way in the higher altitude. And this figure shows the difference between the CFH minus MLS versus CFH measurements. It shows beautifully, clearly, it's clearly seen that though most of the points, this is the lower stratospheric water vapor from above the CPT up to 25 kilometer. And we can see most of the points are falling around zero. It's very close to agreement, but within most of the points are within plus or minus 2 difference is seen. And the inference is the MLS overestimates. We can see that the MLS overestimates whenever the CFH measured water vapor is less than 2 ppmv, and underestimates, the MLS underestimates when CFH measured the water vapor mixing ratio greater than 6 ppmv. And for the different months, we have estimated the measured. This is the seasonal variation of the CFH measured water vapor in the Utilis region. And this figure shows the frequency of deep convection from the Kalpana data. And it is clearly seen that during the June, July, August months, in all the stations, the influence of monsoon, the influence of deep convection up to 16 kilometer, and that influence is clearly seen in the water vapor mixing ratio also in all the stations. But however, if you go from Trivandrum to Hyderabad and to Kolkata to the deepest location, the abundance amount of water vapor has been entered into the upper troposphere, and we have tried to quantify how much amount of water has been entered into the stratosphere, upper troposphere, as well as in the lower stratosphere during the monsoon. So what we did is we took the difference between the previous season, that is pre-monsoon season, March, April, May, and see how much is the difference in water vapor mixing ratio and the temperature difference. So this plot shows that the difference in temperature between the two seasons shows that there is a warmer upper troposphere and cooler tropopause, and the upper troposphere sees the abundance of water vapor in the upper troposphere, where at Trivandrum we can see about 40 to 60% of enhancement in water vapor compared to the previous season, whereas in Hyderabad, when the cloud influence of convection is larger than the southern location, we can see the 150 to 200% increase in water vapor, whereas in Hyderabad it is around about 200 to 300% times higher than the previous season. So coming to the stratosphere, if you see, there is an increase of 0.5 to 2 ppmv increase, that is 10 to 40% increase in the lower stratospheric water vapor, which is mostly transported across the tropopause and reach the stratosphere, which has much implications. So, so the seasonal variations, we can see the beautiful tape recorder effect from the in-situ measurements, right at Hyderabad as well as in Trivandrum, and the hygropause is found to be slightly higher than the CPT altitude during the summer monsoon period in both the stations, and CPT shows clear variation and lowest during the monsoon months. Trivandrum is the deepest, where we can see it is going up to 16 kilometer CPT.
It's unfortunate. Yeah. Dr. Kumar, I mean, your time was almost up already. Maybe can you conclude
Yeah,
with
yes,
your
yes.
own words, maybe?
Yes, 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 yes.
Um,
Yeah, I
yeah,
can
so,
conclude. So we
we can
have
fix it.
examined the effect of tropopause, and we have determined the turbulence parameters from the radius on day using this data, and yeah. So you can see here we have estimated the turbulence detection from the radius on day data, and which is very important for the small scale turbulence, which is conducive for the formation of cirrus clouds. And our study shows that the small scale turbulence, the turbulent length scale is very small in the upper troposphere, and the occurrence frequency is very high close in the TTL region, which is very conducive for making conducive for the formation of the cirrus. And different stations we have calculated this, and I will go first. And we have the interesting results on the ozone. We can see the pre-monsoon increase in the upper troposphere, and the low value of ozone value in the stratosphere, sorry, during the monsoon months. And the variability, what we see here is the variability is determined from the RSD, that is the relative standard deviation by the mean, which we can see a sharp peak in the variability across the tropopause, which is closely associated with the temperature variations. Also, we feel that this could be due to the associated shear-induced turbulence, and the variability is found to be very large during the summer monsoon period, which is close about 50%. And we have examined the variability of ozone, the ETLS across the Asian summer monsoon from the
Yeah. We are trying our best. So again, excuse us for the power fluctuations. We hope that it will not happen again. So yeah, with this, we will now break for tea and we will resume here back at 11:25. Thank you.
Yeah, we continue with the session. Yeah. So- Really perfect. So people are prepared so much more and then it's a bit of a pity.
I think we should cut short that the question and answer.
Some battery are low.
Oh, that is already down.
Huh.
Yes, sorry.
Thank you.
Battery.
working on those topics. And coming today, it's quite amazing to see how much progress has been made and how many field campaigns took place over the past 10 years. Aircraft campaigns from Tibet and India, from Korea, and a number of balloon activities took place also in which I was involved. Today, I'm not going to talk about balloon. I'm going to talk about satellite observations. The balloon work that has been presented a couple of times already, so I thought I would just change and show some of the new results and also some interesting publications which appeared recently, challenging some of the results and some of the publication we had a couple of years ago. So the outline of the talk is I'm gonna give you a little bit of science background about the Asian tropopause aerosol layer. I will also present some results from Kloss et al. 2024, with challenging some of previous work we have been doing. So unfortunately, Corina Kloss, I don't think she's not here presently. She's not here online. So the talk was a little bit to address some of her conclusions of her paper. I think we'll have other occasions to discuss about it. So I will have a look at really look at the et al. In 2003, which was an important year for that was addressed in our paper. So mainly the talk will be divided into two parts. One part during which I will address some of the conclusions that Kloss et al. Had in their paper and some of the new findings we found by updating the analysis that we published a couple of years ago. I wanted to start this presentation with a paper by Hoffman et al. In 2009, published in GRL, where he showed integrated aerosol backscatter between 20 and 25 kilometers derived from Mauna Loa observations. And at that time, after removing from the data seasonal variations, the main conclusion of the paper was to the fact that there was a trend in stratospheric aerosol back in 2008. The positive trend was seen between 2000 and 2010. And so one of the main conclusions of this paper was to connect growth in Asian pollution and emission of sulfur dioxide and kind of connect and make some conclusions that Asian pollution growth would be responsible of the observed trend. So that's something we kind of discussed in a paper in 2011, where actually we found that volcanic eruptions at that time already had a very large influence on the stratospheric aerosol layer in the tropics. And the trend was most likely attributed by a series of eruptions in the tropics, which from a small eruption to a larger eruption that would have created an apparent trend that was probably not coming directly from Asian pollution. And I think during this presentation, we are going back to the same, we'll go back to the same topic, is how do we differentiate what's coming from Asian monsoon and other sources of aerosol? For that, I'll be using two sets of satellite observations. The stratospheric aerosol and gas experiment that was the first series of SAGE was launched in 1979. And there have been a legacy of SAGE measurements since that time until nowadays, with a gap of a few years between 2005 and 2007-06. SAGE is a solar occultation satellite instrument. So looking at the sunset and sunrise, the technique allows to retrieve aerosol and gas concentrations in the atmosphere. I'll be also using the Calypso spaceborne LiDAR. It's a LiDAR that was put in space back in 2006, which lasted more than expected for 17 years. And we're using especially the backscatter scattering ratio, which is the ratio between molecular plus particulate backscatter divided by the molecular backscatter, and the depolarization to differentiate especially in the UTLS region where you have a lot of ice clouds. How do you differentiate ice and aerosol? And the depolarization is a very important parameter for that purpose. So we published a number of papers looking at the Asian tropopause aerosol layer. Really the idea at that time, back in 2018 and 2015, was again, when is the best period to locate the étal feature? So here is a climatology between 2006 and 2018 of scattering ratio after removing the clouds, which is a very essential part of the algorithm. And we see this residual of scattering ratio enhancement between 14 and 18 kilometers during the monsoon in July, August. So we have removed years affected by volcanic eruption, 2006 Soufrière Hills and 2009 Sarychev, as well as 2011 during the Nabro eruption. So what we see year after year, when you look at the bottom plot, you see a feature, a seasonal feature happening every summertime. Cannot obviously be a volcanic eruption. There is no eruption occurring on a seasonal basis, as far as I know. So it was obvious that that there was some connection with the monsoon. We had a number of field campaigns during that time, but I will really focus on the satellite part. So we study the étal trend back in a paper in 2015 by trying to assemble SAGE and Calypso observations. So on the right side is the extinction ratio at 525 nanometers between summertime and wintertime. It's derived from SAGE between 1996 and 2003 and Calypso from 2006 to 2013. So the idea here was to try to contrast summertime aerosol loading in the Asian monsoon region compared to the wintertime to see if there was any anomaly. And we found indeed that the summertime creates an anomaly in extinction, in the extinction ratio. And the anomaly, when we look at the profile, was kind of relatively small in 1996 and increasing, apparently increasing with time until Calypso picked up in 2006. This is the dashed line and up to 2013. So there was some sort of an apparent trend in aerosol. And the trend was seen also when we start looking at the aerosol optical depth after integrating the extinction between 13 and 18 kilometers, there was an apparent trend. And in this case, we looked at a region because the cloud screening process is a very important process. We're trying to remove the influence of potential maybe misclassified clouds. So looking at the Eastern Mediterranean Sea was a way to do that. However, recently, Klaus et al. Just a few months ago challenged those findings and found that maybe there may not be a trend in the étal feature. And so the main findings of the paper was to say that that seasonal average solar occultation measurements from SAGE cannot or can neither be used to exclude the existence of the étal or study its trend. So in other words, SAGE is not fully suited to study the étal, which was kind of contradicting or challenging some of our results back in 2013 and 2015 when we use SAGE data to show the existence of the étal. So in this presentation, I will try to revisit this particular conclusion. And also, one of the conclusions made in this paper was that SAGE-3 was also not able to detect the étal, but there was a previous paper by Klaus et al. In 2017 where basically we could see this feature on SAGE-3. So here is this is an extinction. This is a diffusion diagram between extinction ratio between 525 and 1020 nanometers versus aerosol extinction. Where we see basically is that an average between 13 and 18 kilometers. So we see a long tail of points with an extinction ratio near 1, which is, according to the meteor, a clear signature of ice cloud. And as we go toward the lower extinction and higher extinction ratio, we see this population of points, which are kind of associated with the étale feature. So that's the way we differentiate aerosol, that the way that they differentiated aerosol and clouds, and that's the way we did it also, was to simply delineate an extinction ratio of 2 to separate clouds here and aerosol here. So after that, the extinction profile average relative to the tropopause was derived in red for July-August 2013. And so what we could see on this profile is that there was indeed an increase of aerosol between -3 kilometers below the tropopause to 3 kilometers above the tropopause. So the argument used in Klaus et al. Was to say that there was also a similar feature that was observed outside the Asian monsoon region. So whatever is there inside the monsoon region may not be unusual, because they would see something else outside the monsoon region. And so that was the claim is, when you look at the left plot, the right plot here, which is also a diffusion diagram, you see this enhancement of those points here with enhanced extinction coefficient and high extinction ratio, which actually are an indication that there would be aerosol outside the AMA region, also picked up by SAGE. So now when we did the analysis and compare the results by looking at the difference between July-August in blue in extinction and November-December in orange, we found indeed that in the AMA region, there is an increase in aerosol extinction that we consider to be the étale feature. And when we looked at outside now, the AMA region over the Northern Atlantic and the North America, there is a double peak here. So indeed, there was increase of aerosol extinction outside the AMA, but really with a structure that is different from what we see. We see the étale as a continuous increase kind of layer, and this has some sort of a double peak. I was kind of not very consistent with the étale. So what we did is we tried to investigate the origin of the higher extinction value by looking at some AIRS data. So the atmospheric infrared sounder was used to look at the potential influence of wildfires in 2003 at 500 hectopascal. And we indeed found that level of CO in the mid-troposphere was quite high in July 2003. So there was definitely fires that injected CO and smoke, at least in the mid-troposphere here. Looking at aerosol index from terms, we found that the aerosol index, which is usually a proxy for the presence of aerosol, aerosol with absorption properties like black carbon, increased during the month of July, especially over the Russian region. So there was some evidence that in 2003, there was some influence of wildfires that could have impacted UTLS aerosol outside the AMA region. We did not pick up the exact or find out the exact pyro-CBs that might be involved in injecting the smoke in the stratosphere. That's something that we'll continue looking. So, so the first point is using 2003 to say that even if there is an enhancement of aerosol in the AMA region, and as well as outside, may not be the best argument to contradict the fact that the étale is seen by SAGE. So was another paper in 2017 by Klaus et al., where they studied the Canadian wildfire and they found an étale feature. They found increase of aerosol extinction due to the wildfire arriving in the étale region back in 2017, but there was also some increase of aerosol relative to the background. So the argument was here that even if the étale was reported in the 2017 paper, it was reported by doing average over 5 days period, while it may not be visible on a seasonal basis. So the bottom line here is to say that aerosol variability in the UTLS region is very complex. And if you look at the global stratospheric aerosol database, the GLOSAC database, between 0 and 60 degree north, so integrated between above the tropopause, you see a lot of volcanic eruptions and fires which affected the stratospheric aerosol loadings back, obviously, during the Stage 2 period with the large eruption of El Chichon and Pinatubo, but also a lot of smaller eruption between 2006 and 2011. And again, since 2017, there was a lot of volcanic events affecting the stratosphere. So it's really critical when we start looking at UTLS aerosol over the Asian monsoon region to know what are the potential other sources of aerosol. And Calypso has been a very important system for doing that. So this is a Calypso evolution of the scattering ratio profiles average within the Asian monsoon area. And if you look at the time series of Calypso between 2006 and 2023, you see, as I said before, a lot of implications, a lot of influences of volcanic eruptions and wildfires. And now if you zoom over this times period where there was less influence, you kind of see again the étale feature. And so when we looked at those data and really were very careful in removing regions and times influenced by volcanic eruptions and wildfires, we saw a clear signature of the étale between 15 degree north to 45 degree north, where other visible features were also seen, like the Younger layer here, an increase in the northern hemisphere, probably due to the broad absent circulation, and maybe some smoke in the northern hemisphere in summertime. So we continue by analyzing SAGE and Calypso together. The point here was to say that if SAGE sometimes have some limitations in detecting the étale, at least in we have overlapping periods to do that. So we look at the mean extinction profiles between 10 and 22 kilometers from SAGE, mean and median, for 2 different periods. We looked also at the Calypso backscatter, aerosol backscatter during those the same time. And we also calculate the LiDAR ratio, which is simply the ratio between the extinction and the backscatter. And we found, if we look above 18 kilometers, we find that the LiDAR ratio around 50 is quite compatible with what we know about stratospheric aerosol, sulfate aerosol, and to have a LiDAR ratio that was already shown near 50. However, when we look down below 18, the LiDAR ratio appears quite low, between 20 and 30, which might be an indication either that there is an issue because we would expect a much larger LiDAR ratio. So we kind of compare SAGE and Calypso together between 2016 and 2023. And we found indeed that Calypso and SAGE don't match perfectly. And we believe that it's really coming from the fact that Calypso and SAGE have different sampling. So when you look at the sampling from Calypso, it has overpasses on a daily basis crossing the Asian monsoon region. If you look at SAGE sampling, it's making sampling over the same latitude band during each day and moving down. So the sampling could be really a major issue between SAGE and Calypso to consider. So now looking back at the time series that we started looking earlier, but not focusing only during the summertime, but looking at wintertime, we found really that we have assembled SAGE 2 in red, SAGE and Calypso in green, and SAGE 3. We found a few interesting things, and I will stop here because my time is running. So the period number 1 is influenced by volcanic eruption. We see a relaxing time from El Chichon. And at that time, the summertime aerosol is actually lower than the wintertime. And it's kind of counterintuitive here if we think that there was a surplus of aerosol from the Asian monsoon, in the fact that the aerosol was decreasing monotonically why would an increase of source would actually have the contrary effect? And so maybe several explanations for that, linked to the aerosol size. So if you already have background aerosol, maybe the precursors injected during the monsoon may lead to increase in aerosol size rather than forming new particles. So that could be an explanation. For the period number 2, what was interesting is we found during the month of August in 1999, 2001, and 2003, maximum of aerosol, which was kind of expected because that was what we published 15 years ago. But we also found that period number 3 between 2006 and 2012, sorry, and 2017 was the ideal period to study the ETAL. There were some minor influences of volcanic eruptions or wildfires. So the comparison between Sage 3 and Calypso is still challenging, and we're still working on trying to understand the observed differences. So I will conclude my talk by saying that what is very important when we study interannual variability of the ETAL is to consider the influences of volcanic eruption and wildfires. They occur on a very frequently, and trying to infer any trend analysis without removing those periods is a little bit dangerous. I would say that based on this analysis, we kind of are confident that Sage 2 and Sage 3 observation can be used to study the ETAL, but careful screenings is required. We also see that there are some challenges between Sage 3 and Calypso that we need to overcome. And the long-term analysis is still something that we are working on to really understand what's the best way to separate volcanic eruptions, wildfires, and the Asian summer monsoon. And I will thank you for your attention.
Thank you. Thank you so much. Very interesting, and we didn't want to stop you in between. So maybe we can take up the questions we can discuss during lunchtime, as we are already running out of time. Thank you once again.
Yeah.
So now we'll move on to the next lead talk by Dr. Mark Hope from Jülich, Germany. He'll be presenting on strategy for more ground-based observations to constrain the lower boundary conditions in atmospheric models.
Okay. Okay. Yeah, thank you for the organizers to give me the opportunity to give this presentation. Maybe it's a bit surprising that I talk about ground-based observations here. I can tell you a little bit about the motivation. We had the Phileas campaign in Alaska looking at outflow from Asia over the Pacific. And when we had a meeting in January, we showed all our preliminary results of observations we made with a German Halo aircraft at like 14, 15 kilometers altitude. And then the modelers, they started to run their simulations, compare the results of the simulations to the observations. But they said it's difficult really to test the model here because the lower boundary condition of the model, like what you put in the source regions, there's a large uncertainty because we just don't know what the concentration of some of these trace gases we measured up there on the aircraft is in China, in India, in Asia, where the air was coming from. And so I thought, well, it's not so difficult to measure some of these gases on the ground if we can do it on aircraft or even on balloons. And so that's kind of the motivation for this talk. And the co-author team from my institute, I want to acknowledge here as well. They all helped me a lot with getting this presentation together. So why are we interested in the stratosphere? It's of course because there are trace gases, greenhouse gases also in the stratosphere. And there, even though the pressure is low, they can have strong radiative effects. And in this paper from Martin Riese et al. In 2012, he showed that some of the changes in the stratosphere, they can have a large relative impact on the radiative forcing, especially here for water vapor, but also methane in the upper troposphere. And so the representation of these processes and the composition in this region in climate models is very important. And also some gases, if we find them in the stratosphere, they can tell us a lot about the history of the air mass and transport timescales. Like CO2, a colleague, Johannes Laube, is very much into age of air, where if you measure CO2 in the stratosphere, you can tell how long the air mass needed from the troposphere to be transported to that point. And from that, you can infer, for example, from measurements, the velocity of the Brewer-Dobson circulation, just as an example. Okay, ground-based observations, just a few trace gases here. I don't think I need to go into detail. The main greenhouse gases, CO2, also an age of air tracer, as I just explained, methane, N2O. CO is a often used tracer for anthropogenic impacts, pollution, also fire. And some of the halogenated species, CFCs, HFCs, there's a whole zoo of them around. And some of them are of natural origin, some halogenated species, not CFCs and HFCs, from the ocean, others from certain regions in the world. So if you measure 10, 20 of those in the stratosphere, you could use that almost as a fingerprint for where the air is coming from. And so some of these are not that difficult to measure, so it should be possible to measure them from the ground. And they are measured in many parts of the world from the ground. There are several observational networks. I will just show the largest three here very briefly from the NOAA Global Monitoring Laboratory. They have a big program, predecessor started in 1972, where they measure greenhouse gases and also halogenated species in the HATS network. And some of the sites are equipped with in situ instruments measuring the air right there, but they also collect flask samples very carefully and transport them back to the big laboratory in Boulder to be analyzed very carefully there. And this is just maybe the most famous observatory. And I think we've seen the Mauna Loa curve already in a few presentations here. That's just a picture of the site. The next network is the A-Gauge network. There you can see a photo of a Mace Head station in Europe, also very famous station off the coast of Ireland. A-Gauge, it's the Advanced Global Atmospheric Gases Experiment, and that started in 1978 and is supported by a consortium of multinational institutions and organizations. And they measure discrete samples typically on site, either by taking samples and measuring them in the lab, or also by some in situ instrument by optical methods, N2O, methane, also many halogenated species. And then yesterday in Greg's talk, we already been introduced to the GAW network, the Global Atmosphere Watch Program by the WMO, maybe the biggest of these, the most comprehensive, but maybe slightly more inhomogeneous than the two I just showed, where the stations are equipped very similarly. That operates in its present form, I think, since 1989, but it goes back to some earlier measurement programs as well. And it's to coordinate high quality measurements between different stations. And there are about 100 countries already participating in that program. And here I put a map together with some of the most important GAW stations and also A-Gauge and the NOAA stations. And as you've seen in Greg's talk yesterday, there's quite an accumulation of stations. So you don't have too few measurements in North America and in Europe. In Europe, you also have an ICOS, an integrated carbon observatory network, which adds to stations. But you have quite a few areas where the density of stations is low. And that's mainly over the ocean. But there, better coverage is really difficult, because to put an instrument on the ocean, you need a small island. You could do it with a buoy, but that's very tricky and complicated. So I think the ocean is one region where it's very difficult and to do something about it. But if you look at Asia, Africa, and South America, I think better coverage should be quite easy to do. But first of all, why is it critical that we don't have enough stations in these regions? And for that, I just show you a little study that we've done, and that goes back to some papers by Bärbel Vogel, who's also here, who started about 10 years ago to use surface origin tracer in our CLUMS model that we run at the Institute for Transport. So she would initialize an ideal tracer and release it in the model in certain regions, and then carry it in transport up to higher levels, to the upper troposphere, to the stratosphere, and then see how much of that origin tracer would arrive in certain measurement locations. And she divided the Earth's surface up in different geographical regions. Some other people have done similar studies where they use a more regular grid. But we start with the grid that Bärbel used in her papers. And then we took the CLUMS model, initialized it in May, I think, with this particular run. And then after 1 year, looked at the percentage of emissions from these different regions reaching the 100 hectopascal level in altitude. And there you can see that a few regions really stick out, while a few other regions, there's hardly anything that you would see out the ground there arriving at these high altitudes. Now you may think, okay, we've seen the map here, and there were some really large regions that are much more in terms of size, and some small regions. So maybe is it the small regions that only make a small contribution, and then the large regions making the large contribution? But that's not really the case. If you divide these bars by the surface area of these regional tagging, then it's even more focused on one particular region. So you have 5 bars really here that stick out a lot, and they are all located in Asia. I show you that on the map. So if you take all the regions here from the first bar plot, you basically cover the tropics, and that's no surprise. I mean, that's where the air rises up and you transport it to higher altitude, mainly by convective updraft. And if you look at the second bar chart with these regions where really a lot of material per surface area gets up, then that is really focused here on the Indian subcontinent, Northern India, Tibetan Plateau, and South Asia. So this is really the region where much of the air that we find in the lower stratosphere and the upper troposphere is coming from. So it's all the more important to characterize well what is going up there. And now if we compare that to the network map, we see that there are very few points here in the center in the Tibetan Plateau. There's one station, and that's pretty much it. And incidentally, the same regions have currently the highest emission rates for many anthropogenic pollutants, aerosol particles, aerosol precursors. So if you want to study the impact of anthropogenic activity on the stratosphere, you really need to know what's happening here in Asia. So what can we do about it? Well, at first I thought, well, we really have to do more measurements. But in the last few months, after I wrote the abstract for this conference, when I did a little bit of research, talked to people, I found out there are actually measurements available that just not in any of these networks, and some of them are hard to find or invisible. At least when I would do a Google search, greenhouse gas measurements in India, I wouldn't find anything. But Bärbel told me that she, for a recent paper on CO2, she has actually had some contact to people who measure data and greenhouse gases in Nainital, and that's available. There's also the original paper where these data are first mentioned by Nomura et al. They are in a Japanese database, and they are available, but I couldn't come up with a search strategy to really find these data. And even during the last 2 days here, there were some people talking to me about making measurements, and they made trace gas measurements even here very close to Pune on some mountaintop, and say, yeah, we do. We measure methane, we measure CO2. And I really look forward to get into contact and see these data, because it would be great if we could use them to tune our models to define the lower boundary there. So I think many of these observations, I'm sure there are even many more, they should be better advertised, and we should really get into closer contact. One important thing is that you definitely need metadata. I will show that on the next slides to accompany just the greenhouse gas measurements, so you can put them more into context. And some of the measurements may not be carried out over long time periods and at the necessary frequency, but that's probably something that's not too difficult to do. So I think we should really try to encourage making your measurements more visible here from India, from Asia, and support the continuous operation and the archiving and publication of these data sets where the whole world community can find them. So this is a plot from the internet, from the GORE network. And this is focused in on India. And if you just look at the front page, you find, okay, there are quite a few stations, but then the blue color actually means that many of these stations are non-reporting. That means at some point they're registered as a GORE station, but then there are no data coming in. And also many of them are regional or local stations, and they focus, and for good reasons, on local pollution, local emissions, particles, ozone, which is of course societally very relevant here. And if you just take stations that would measure greenhouse gases, then it's much fewer. But maybe we can use the existing infrastructure where possible and where the station and the location is suitable to also establish trace gas measurements. If you already have a station and you just need to put in another instrument, it's much easier than to start up something completely new somewhere. And I think that's something we have to consider in Europe, in the US, and in the big network and international projects. How can we support local scientists here to engage them in these networks and support their measurements and making them visible? So I talked about location requirements. So something that you would use is tall towers. This is not a very tall tower. This is a tower we actually have in Jülich on our campus, and I've made some greenhouse gas measurements myself there for 10 years now. Some other groups are making these measurements, and it's an official ICOS network station. Then here, Nainital would also be a good location, because that's at some elevation and you have no local emitters, no factories close by. And what you need in any case is some auxiliary meteorological measurements. So with this tower, when I did the observations in Jülich, there's a power plant, a brown coal burning power plant nearby. And often you could see CO2 peaks and you have to remove them. If you get wind data, the wind direction, you can filter that easily and it becomes representative. The picture on the right-hand side, that's actually a station on Bola Island in Bangladesh, where one of my instruments was deployed in 2016 for a few weeks by the Alfred Wegener Institute. They made measurements there. And when I tried to do science with the measurements, I said, well, can I have maybe some temperature, some wind data? And they hadn't made it. And so I had to use wind data from stations that were 20, 30, 40 kilometers away. And it turned out that it's really difficult to interpret these data, because if you have wind from the south, you get it directly from the sea. If you have wind from the north, you get it from the land, from the city of Dhaka. And you can imagine that like CO2, CO looks very different for these locations. And there's another example how definitely not to do it. It's another deployment also of one of my instruments by the RV. They put it on Palau Island, and we wanted to make some representative measurements for the Western Pacific. And they said, well, we have this container, quite high elevation, you can see it. And then they do FTIR studies, which is not so critical because that just looks with a beam up in the atmosphere. And so you have here the container, this is the white roof, and there this rod sticking out is our inlet. And what I only learned after I saw the first few weeks of data, and I said, what's all these spikes? So the container is positioned right next to a bus stop and a petrol station. So that's not very representative. So that's definitely not how you should plan a measurement station. So instruments and sensitivity, these two pictures are from our lab, from my colleague Johannes Laube, who has a Picaro there on the left-hand side and a big GCMS on the right-hand side, where he analyzes samples also from stations that are sent to him and sometimes from aircraft and balloons. So this is basically state-of-the-art instruments like you would also use at NOAA and NCAR. And the data quality and precision accuracy is top level of these instruments, but they are very difficult to maintain. They need a lot of room, especially the GCMS, as you can see here, and they are not exactly cheap. So equipping like 20 stations in India with instruments like that may not be so easy. And so maybe if you do trend analyses for the global greenhouse gas trends, you of course need the best precision accuracy you can get. You need to be able that data from one station to another are 100% compatible and there are no biases. But for some model initialization and some of the other uses, just a little bit less ambitious precision and accuracy can help offering you much more possibilities for instruments to deploy. So the picture on the left here that shows on the Bola Island station, my Los Gatos instrument that I placed there. It's this black box on the left-hand side. And that's just a $30,000-$40,000 instrument. And it can actually operate without calibration for quite a few days to weeks. So that was fairly easy. And then on the right-hand side here, you see a small sensor in front of a pen. I'm trying to develop an instrument for deployment on small balloons, like like a radio sonde, then try to do a greenhouse gas sonde. And this is a sensor by a Swedish company, really small, really compact. It cost $500. And it makes surprisingly good measurements. I'm just in the process of validating and testing this. And something like that deployed on a tower that can also get you a long way. Of course, you still need to do regular calibrations, and some consistency with international scales should be ensured. But I think there are ways to do that. And of course, just buying instruments in the US, in Europe, and shipping them here, there are all kinds of obstacles. They are expensive. Also, if you ever try to put an instrument in other countries and have filled in dual use forms, you know that this is not always so easy. Also, at least in Germany, to find funding and political support, it's easier if I work together with German companies than from other countries. So politics is always close to economics. And I found that in India, there are actually companies who build instruments to measure gases, CO2. There are just 3 examples here from one company in Delhi, one in Mumbai, and I think Sarvesh Analytics, which are focusing on process analysis. They're actually sitting here in Pune. So you have these manufacturers, and maybe they are off-the-shelf instruments are not exactly what you would need for a station, but if you talk to them and you get into projects with them together, maybe that's also something to look into. It would save cost. And it would also ensure quick and even on-site support. Like if you buy a Picaro and then whenever you have a problem with it, you need someone from California to travel to your site. That's not so easy. So the last slide, just a few ideas. I think we should make much better efforts to take stock of available data and infrastructure and use that for the global atmospheric science community. In my opinion, we should start simple and with minimal resources to come up with new measurements, new stations, using readily available instrumentation. And if you have a station running well, you can always upgrade later and try to do better and make the scientific use more wide for these data. I think organizations, projects like WCRP, APAC can hopefully support continuity and long-term support and hopefully help you to make your efforts visible. And so in APAC, we just started with the new implementation style and an outreach advisory board of which I happen to be the chairman. And it's a lot about training. And I've heard we had a beautiful training session here on Sunday, but I think just do the training and then go back home and do nothing. That doesn't get us very far, but really to engage scientists, making measurements, not only modeling studies, that would be great. And I think from the APAC office, we can hopefully support you with data access points, with spreading the word that these measurements are available and provide further support and training. So please do contact us if you think this could be something for you. If you say, hey, starting a measurement here is great, or I already have 10 years of data, just let us know. And we try to make that more visible. And I'm sure if you would think about becoming a GAW station, I'm sure if you talk to Greg, he will not be unhappy about that. So with that, I close and thank you very much.
Thank you. Thank you so much for giving us insightful thoughts. Very interesting presentation. Yeah. Maybe any questions and answers, I think, maybe quickly. Okay.
I'm just curious, how do you scale up from point measurements of greenhouse gases to the grid box?
Well, I mean, you can't scale up from one measurement easily. So in an ideal world, you have as many measurements in a grid box as possible. In Europe and in North America, that's not so difficult. You've seen how many stations there are. And here you will, of course, need more stations. And if you have stations on like a mountain peak or on a very tall tower that are not too close, then you can probably average and get close to the average of that grid box. If you would just measure CO2 at 2 points in Delhi city center and Mumbai city center, it will probably not be representative for the Indian subcontinent. That's pretty clear.
You know, I'm the co-chair of GWAX.
Yes.
Looks like this could be an interesting topic for collaboration between APAC and GWAX.
Yes. Yes, I mean, that's from the outreach committee, we try to get all the activities in. And if you have ideas how to do this even better than I'm currently thinking of, I'm very happy if you come and join the next meeting or write me an email. Yes, please.
Yeah, thank you. We'll move on.
Yeah, thanks. Very nice presentation. And certainly the message is, I think, very important. And I think from a GAO perspective and from the atmospheric composition community, I think your message is strong. I think one thing we need to do is coordinate better about the messages so that we're speaking in common language and kind of point people to where they can go. I think from the research perspective that you're talking about here, you mentioned one of the big challenges, there is a lot of research-based short-term and sometimes long-term observations that are hard to discover.
Yes.
And so I think we have to work on that. That's different from a network long-term operational component.
That's clear.
But I think in that regard, I don't know if people are aware, there is some a recent paper that's been published. It's called the system is GHOST. It's a global harmonized data set of surface atmospheric composition measurements. And it's a really, really outstanding methodology to go out and extract data that all of us modelers do on our own. But this has been done systematically, and it's a growing database. And I really encourage people to look at that, embrace it. And that's a sort of a framework that individual stations can identify themselves and be discovered in this.
Yes.
And so it's a really, really great step forward in terms of discovering dispersed data sets.
Yes, absolutely.
Yeah, thank you. Thank you. Now we'll next move on to the next lead talk by Dr. Manish Naja, Aries Nainital. So he will present on variability in the tropospheric ozone in Asian summer monsoon region, ozone sondes observations from Aries Nainital.
Yeah, hello, good morning, good afternoon, sorry. Yeah, so here I will be presenting the observations made from the Nainital site, which is in Himalayan region. And I will say thanks to Mark Bonhob, who already introduced this site slightly on several occasions. So we have the observations of the balloon-borne ozones and on the meteorological parameter. And apart from that, we have the extensive observations of surface, trace gases, and aerosols from this site. And before I continue, I would like to acknowledge the contribution from my PhD students from this long series of observation. And here you can see the site which is in the Himalayan region, and this is on the mountain top is our institute. Yeah, so before I continue on this region and to fulfill or complete the story, I would like to point out the importance of this region. Of course, we are aware. And the important point is like we see our institute is located here in the northern part of India in the base of the Himalayan region. And ITCGs comes to this region in the monsoon time, particularly in July, and which is in January goes to here. And one important point, this I am trying to show the wind observations from the balloon-borne observation, and trying to show the distribution from winter, spring, summer, and the autumn time. And you can see very clearly the presence of the jet, and when wind speed goes to up to 80 meter per second. An important point, you can see the period in the summer monsoon time, and which is also we can say the asthma period when it's active, the wind speed of the jet is almost disappeared. So they are in the like month of June and July and August, they are not present. Now, of course, we are aware the convective uplifting over this from this part of the South Asia. And apart from the convective uplifting, this is also the close proximity when you have the frequent tropopause break. So you have the downward transport of the ozone-rich air mass. So these are the two different processes like convective uplifting and downward transport of the air. Now, so here, when we talk on the tropopause break, here I would like to give a very brief summary. This work done by this Karlek, and he tried to show with the reanalyzed data from 1979 to 2012, like region when you have the probability of the shallow, deep, or medium the tropopause break. When I say the shallow means like in the altitude of around 50 to 200 hectopascal. And if we show in this plot, like here, this is more frequent in the winter and also in the spring. This is for the company shown in the summer monsoon time. Now, I would like to draw your attention here in when you say the shallow tropopause fold event, and you can see in the winter and springtime, they are the more frequent and around you can say the 25 to 30 north region. So they are more intense in the winter and also in the springtime. But in summer monsoon time or in autumn, they are much weaker. So this is the basically time to focus this. Now, of course, this is also well-known thing, but I would like to just point out here, like there are several model studies have shown the convective uplifting, like this is using the CO tracer model, and you can see the uplifting of the air mass up to around 200 hectopascal, and this is, you can see with the simulation showing from the East Asia to almost going to the African region. So with this, okay, yeah, this is the another work done by the Bhupen, who is in IITM, like showing the again the distribution of water vapor and with the climatological data from 2005 to 2016. And you can see also the water vapor. Of course, these are the known thing, but I would like to point out what are the things happening in this region. And here the two modes were identified, like the mode A and mode B. If you do the analysis for the May, June, July, and August, and then June, July, August. So these are the time you can say the high water vapor is seen in the month of June and July. So with this, like until now, we are seeing these things which is happening in the upper troposphere and middle troposphere. But what are the process of things are happening at the lower tropospheric region? And to see, like this is the northern part of India. You have the air mass coming from different air, like marine air mass is coming in the June, July. Then in the winter time, you have the long range transport coming from the northern part of Africa or southern Europe. And like in the springtime or autumn time, you have the contribution from the local emissions. So that is you can see how the different air mass is contributing in this region. And also you can see this is the distribution in the northern part of India for the modest fire count. And you can see in the forest fire in this region in the northern part of India is more dominant in the spring, like March, April, and May. Of course, in the autumn you can see some fire, but they are not prominent. And this is the composite diagram showing how dynamics is. Like our observation site, Nainital is located here in the Himalayan region. So you can see from the continental side, whatever the polluted air mass lifted up, they goes to this side and well mixed with the region. So here, I'm trying to show the observation site. Our office is here in the Nainital, this region. And of course, this you can see more closely the mountain top. And this is the altitude is around 2000 meter. And in the very close proximity around, you can see 30 kilometer, we have the source region. This is town called Haldwani. So the altitude is around the 500 meter. So you can see within 300 kilometer, 30 kilometer distance, the altitude varies from 500 meter to almost 2000 meter. And here we have the another site called Devasthal. This altitude is around 2005 meter. Here we have a lot of surface observations, and this is the famous astronomical site. And another site is the Haldwani as base station I was telling. So we have this surface observation at this site and about different trace gases and aerosol. And we fly the balloon from this Nainital and doing since late 2010. And here I will be presenting data from 2011. So here to give us just idea how the balloon drift. So here you can see in the different season from winter, spring, autumn, and summer, the drift in the balloon, and with the color code you can see the ozone level also in that particular altitude. So you can see the most of the time the balloon goes to in the eastern direction, but only in the summer monsoon this is basically within that region or towards the western side. And here in the autumn it is mixed kind of thing. And of course, you can see this is the border. So many times you can see balloon is going to the Nepalese region also. And but this is happening in the altitude of around, you can say 20 kilometer and further up. Now, to give an idea about the tropopause, how the tropopause changing in this region, you can see most of the time, you can throw the year tropopause is around 100 hectopascal. But you can see in the winter or the early spring, it comes to the almost the 300 hectopascal. And same thing is you can see in the late autumn and winter time. Now, this is on the vertical profile to give an idea on the surface, what is happening on the surface. I would like to draw your attention here. This is the diurnal pattern in the ozone at three sites like Nainital, Devasthal, and Haldwani. So represent, you can see the blue color, which is in Haldwani. That is typically showing because daytime ozone enhancement is seen. So you can see the air is highly polluted. Whereas in this red color or black color, we are not seeing any daytime production. But this is true only in you can see in the January or in July. But in the March, you can see enhancement even in the mountain side. So that means some contribution is coming from the source region, even at the mountain side. But here you have to see this is happening in the spring, not in the monsoon time. Now to further explore, I am trying to show the other trace gases. So this is the seasonal variation for different trace gases observed from the Nainital mountain side. And you can see again the CO and ozone and NO by, they are showing high level only in the springtime, but in summer monsoon, the levels are pretty low. And you can see the levels of NO is almost, you can see up to average level is around the 300 to 400 ppt. And the NOI level is also, you can say that around 2 ppb or 2000 ppt. So the site is more or less, you can say, yes, except in the springtime, the site is rather clean. This is to further move on the surface hydrocarbon observation. Just I think we need not to see in the different species, but I would like to draw main attention, like the high level of the hydrocarbon level is still not seen in the summer monsoon time, like this term. So high level is basically on the either winter or springtime. So this is the period in the surface these things are seen. So this is for hydrocarbon, and then some of the BTX species also show the same thing. And apart from these gases, you can see the same feature is also seen in the aerosol. So this is for the organic carbon, elemental carbon, or the black carbon, carbon monoxide. The high levels are not seen in the June, July, August. And so this is summer months. And the levels are basically high in the winter, spring time. So you can see in the source region or in the plain altitude, the levels are very low in the June, July, or in the August, which is the, we can say, the summer time or the monsoon time. Now here I will come to the on the vertical profiling after completing the information on surface. So here is showing the composite picture on the 4 season for the ozone sonde observations in the from surface level. The altitude is around 2000 meter up to 18 kilometer, and you can see the different color code are average profile for the each year. So from 2011 to 2024. Now here I would like to draw your attention, like you see in the winter time or in the springtime, there is large variability in the middle troposphere, in the upper troposphere. But in the lower troposphere, variability is not much high in the winter or spring. And but in the, you can see variability wise, in the lower part of the troposphere, it is much more in the summer or monsoon time. Okay, so this is very different than the upper the part of the region. Another point, you can see the lower part of the troposphere, the levels are much higher in the springtime. Like level is touching to or going to more than average level, this annual average level touching to more than 90 or 100 ppb. So this is happening on in the springtime. But variability is less in the lower part of the troposphere. Now, to see this in slightly in the clear way, here is the average picture in the 4 season for the entire 14 years of data. And the black line is showing the average of entire data set. And this is grouped in the 4 season. So again, you can see in the middle troposphere, in the upper troposphere, the level of high level of ozone is seen only in the winter and spring. Okay, but you can see this in summer or autumn, the levels are much lower. And if you come in the lower tropospheric part or in the lower part of the middle troposphere, the story becomes different. Like the winter or springtime, the levels are not very high, but in the summer monsoon times, levels are much low. So to explore this thing further in the detail, and each for the each profile wise, like here I'm trying to show this one movie, the animation for the different months for the from January to December. You can see now this April, and these are the case we identify when we saw the ozone levels on each profile is higher than the average of the 3 sigma. So those cases were identified, and here you can see very clearly, like the enhancement is seen variability in the like December, now January, and the February you can see high variability, and the March, and from April onwards it start decreasing. Now this, and then May you can see the variability is much less. And if you focus in the middle and upper troposphere. So this is the time you can see the variability is much lower in this part. Now to see this further, I am trying to show some of the individual cases. So here one typical example I am trying to show for the February 1 profile. And here on the left hand side, the profile from the balloon data, and the red color is showing the ozone distribution. And these are the result obtained from the MIRA. And on the bottom side, we are trying to show the MIRA spatial distribution for the ozone and the potential bodicity. Now here you can see the around the 250 or 200 hectopascal the enhancement in the ozone. Okay, now same you can see in the mirage distribution, the high level of the ozone is seen around 200 and 250 hectopascal or 200, which is slightly lower. The such high level are not seen in the high altitude. And this is also very much supported with the potential vorticity. So indicating that the influence of the downward transport of ozone. Now, the another event I'm trying to show, which is in the further deep influence, and the coming down to enhancement in ozone around the 300 hectopascal. This you can see this one. And this is also same reflected in the spatial distribution around the 250 to 300 hectopascal and very clearly supported by the potential vorticity distribution. Now, yeah, another thing is this is the one the case which we have the balloon experiment, and also in our institute we have installed a wind profiler. So that can give the wind information up to, you can say, the 20-kilometer height. So here is the one example I'm trying to show when a high level of ozone is seen in the around, you can say, the 14 to the 18 kilometer. And this is the potential vorticity, which is also showing the influence of the downward transport. Now, this is very well supported with the vertical wind distribution, which we have the observation from our wind profiler, we call the ST radar. And here you can see the event was on 21st April, and you can see this is the one event on top in the 20th April, which is showing the radar observations, not any specific event, but you can see in the balloon was launched around the 11 o'clock local time, and you can see the change in the wind direction and with very high wind speed. And very well, it also reflected in the vertical wind. Like here, you can see this is the downward, like negative wind of the wind speed is going up to 0.4 or 0.5 meter per second in the same time zone. And this event had occurred only for a few hours. So this is very clear indication that the downward transport of ozone is happening, or ozone-rich air mass is happening in this part. Yeah, so apart from this, there was the influence of the dynamics, and we also try to explore how the surface, the activity or the biomass burning influencing the ozone in the lower part of the troposphere. And here we try to group the ozone, the data, and the low fire activity and high fire activity. And with that grouping, I'm trying to show here, this is the profile, like the ozone vertical distribution when you have the low fire activity in blue color, and in the pink color, you can see the high ozone activity. So this is basically happening in the springtime. And you can see the enhancement in ozone from surface level to up to 4 or 5 kilometer is seen by around 20 ppb, 20 to 25 ppb. So this is also supported by the surface ozone observation. That is, you can see the high ozone levels is seen in this period. Yeah, okay, this is. And now to again support this, like this is the event of the biomass burning, we also have the hydrocarbon observation, and we try to simulate and make the correlation analysis for the ethane and carbon monoxide and acetylene. And you can see very clear the indication, like in spring and autumn, the correlation is much higher, more than 0.7. And that is also indicating that biomass burning is influencing in the springtime and autumn time. Yeah, so by seeing this, now this is the composite analysis made and comparing with the ozone sounding data and then from vertical profile from the EIRS. So we identified two events like the influence of the downward transport and the biomass burning. So here you can see on the influence of the downward transport, and here you can see the enhancement because of the downward transport is almost as high as 30%. And this is we compare with the ozone sound day and the EIR satellite data. But in case of the biomass burning, this enhancement is seen up close by 10 to 20%, and up to this is seen up to the 6 kilometer altitude region. So this is, you can see, the local effect versus the dynamical influence in this part. So, and again, we wanted to see how the performance of the EIRS is doing over for this region, and we made the comparison on the different from January to December part. So here you can see this is the correlation plot, and you can see the comparison made for the tropospheric column, and then you can see the UTLS region, and you can see the EIRS data is like in UTLS region. You can see this is almost the positive bias throughout the region. But in case of tropospheric column, at the lower levels, it is the positive bias, but in the higher level, it is has been negative bias. And that is also reflecting, you can see in the monthly distribution. from January to December, like for total column of ozone and then UTLS ozone distribution in the tropospheric ozone column. So if you focus on the aspect like how AIRS is performing on this Himalayan region, so they are basically having the higher value in the total column ozone. But interestingly, you can see the dip in the July time. So we are still struggling to find the reason, and probably whether it is the water vapor effect and what is there, that we have to find out. And what you can see the contribution from where it is coming, we can see the again in UTLS region, the AIRS is still showing much higher value. So whatever the positive or higher value it is, we are feeling that it's contributing from the lower stratospheric region. Because if you can see the total tropospheric column, the levels are almost in the agreement with the ozone sounding, and the seasonal variation is almost more or less is agreement. So with this, like looks like the AIRS is having some positive bias over this region, and the seasonal variation is also not reflecting. So with this, I would like to conclude my talk, and I would like to just give a message like this Himalayan region is a natural observatory where you can have the photochemical and the dynamical influence in the natural lab. And you can see the importance of this region. And here I am just trying to show one campaign which for the support of the stratoclim will be conducted in collaboration with IITM and also with the Zurich group for the extensive observation in 2016 and 17. So thank you very much.
Thank you.
Yeah.
Thank you very much. So maybe if there are any questions, you can discuss during lunchtime.
Yeah.
Thank you, sir.
Yeah.
So now we'll move on to the next oral presentation by VN Santosh from NARL India. His presentation is on quantifying the radiative impact of Asian tropopause aerosol layer using the balloon-borne field campaign measurements. So Santosh, you have 10 minutes.
Okay, hope I am audible. Good afternoon, everybody. Myself, Santosh from NARL. Today, I would like to briefly explain you what we have done in quantifying the radiative impacts of Asian tropopause aerosol layer using balloon-borne field campaign measurements. So as we all aware, we know the ASMA region is known for trapping the air mass and the aerosols during the boreal summer over the Indian region, and in the UTLS region, 13 to 18 kilometer approximately. So which is known as the Asian tropopause aerosol layer. And the UTLS region is very important, as we all know, because any changes, small changes in the structural or chemical composition of this region can result in large changes in the radiative forcing of the atmosphere. So we need to accurately know what is actually happening there. But we have the limitations exist with respect to the remote sensing measurements for accurately probing this region. And moreover, regarding the entire vertical structure of the aerosols, we also aware that there exist elevated aerosol layers in the free troposphere altitude also to increase the complexity of the aerosols during this particular summer monsoon season. So we have to rely on more accurate and vertically resolved balloon-based measurements to accurately quantify the radiative impacts of Asian tropopause aerosol layer. So to come to our preliminary objective is to quantify the shortwave direct radiative impacts of UTLS aerosols in terms of radiative forcing and heating rates using the balloon data we obtained from the battle campaign. So the battle campaign is a balloon-based campaign that is carried out during 2014 to 2019 period from 3 different locations from all over the India, namely Gadangi, Hyderabad, and Varanasi. And we have used the following period of data for our study. And we will see what actually we have found in the subsequent slides. So come to the methodology. For the quantification of the radiative impacts, we need altitude resolved profiles of the atmospheric profiles, namely pressure, temperature, water vapor density, and ozone density, along with the aerosol properties. Regarding the aerosol properties, we need the extinction coefficient profiles and scattering properties. Scattering properties is nothing but SSA and the phase function moments for the scattering phase function. So for that, what we have done is that we have the cobalt measurements at a 2 wavelength channels, 455 and 940 nanometer channels. And we have well-established screening criterion for UTLS aerosols from the previous literature. And we have followed them to screen out the clouds from the given cobalt data. And below UTLS also, we have done some analysis based on the relative humidity thresholds. So because we have identified some moist layers below the UTLS, and based on some thresholds, we have identified them as the cloud layers. Then we screened out whatever the cobalt profiles giving in there, so that we will get a complete vertical profile of the aerosol from all the way from surface to the top of the atmosphere. And now we have the simultaneous soundings of pressure and temperature from the radio sonde, and we can use it for the molecular contribution so that we can convert these cobalt-based backscatter to the extension profiles that we can input into some radiative transfer scheme. We have used the SB dot model here, and other ancillary data sets like surface albedo also we have inputted to get the upwelling and downwelling fluxes at the top of the atmosphere and surface and in the UTLS boundaries. We have taken from 12 to 20 kilometer. So what now we have to assume is what is the dominant contribution in the UTLS, so that I will get some scattering and scattering properties in the UTLS region. For that, we have relied on the previous literature so that we can consider some dominant scenarios and we can attribute something out of it. So several studies in the beginning, the thought was about the sulfate. But later, the first ever offline chemical analysis from the battle campaign itself revealed that there exists a dominant contribution of the nitrate. And more recently, it is established by another study by Vernier et al. And they found that the nitrate is the dominant contribution. And it is also supported by several other observation campaigns like Stratoclimb and all, that the nitrates are dominant in the UTLS region. But at the same time, we cannot ignore the presence of sulfates and some sort of anthropogenic absorbing kind of aerosols that has actually provided by some modeling simulations and all. So in that, keeping view of all of this, we have considered 3 idealized scenarios where 3 different types of aerosols are dominant in the UTLS. Namely sulfate. Sulfate is of natural origin and it is also equivalent to whatever we have found in the stratosphere as background. So then comes the nitrate, as I already explained. Then comes the anthropogenic part. For the anthropogenic part, what we have done is we kept the absorption minimum so that anything beyond that, we can assume that it is a baseline for the absorption in the UTLS, so that any absorption beyond that, we can expect to be more. So that for that, we have used the continental clean model as described in Hess et al. 1998, which can also, we can simulate using the opaque software. And these are the assumptions we made to get the complete profile of the aerosol properties for this particular quantification. And now here's, you can see the backscatter profiles over 3 different locations. So as we know, the Gadangi and Hyderabad is located more closely towards the edge of the Atal region, whereas the Varanasi is more close to the center of the Atal region. So we can see more complexity in the profiles of backscatter ratios as we are going different locations into the Atal region itself. So let us see, is there any impact of this particular observation in our actual estimates. So here comes the estimated columnar forcing. So you can see the top of the atmosphere and the atmosphere and the surface contribution. So concurrent with the several observations, we also found that there exists the negative forcing in the top of the atmosphere as well as the surface, whereas we observed warming in the atmosphere. So this magnitude was actually, Gadangi was lesser magnitude in forcing, but we have found Hyderabad and Varanasi more forcing values, probably because it is highly urbanized region. So it has that warming impact, obviously. And what you can see here is that these three panels are representing whatever the scenarios we have considered from the earlier in the previous study I have described. So this is the anthropogenic dominant scenario in the UTLS, and this is the nitrate dominant scenario, and this is in the sulfate dominant scenario. So you will see a slight difference in each of these dominant scenarios that we are looking into closer in the subsequent slides. So we can clearly say that differences are observed in the forcing values due to the dominant contributions in the UTLS. So these are the difference. So as I told, we can take the sulfate as the background. So it can be used as our reference for the quantification. So we can see there is a difference in the anthropogenic minus sulfate forcing, and this is nitrate minus sulfate forcing. So anthropogenic type are more absorbing type. So you can see that there exists more warming due to the anthropogenic aerosols in the surface as well as the atmospheric column, whereas it is enhancing the cooling in the top of the atmosphere. Whereas when nitrate is more scattering kind of aerosols. So what we can see is that it cooling all the regions of atmosphere, namely top of the atmosphere and surface, but few exceptions are there. But we can see that the varying behaviors in the forcings can be expected due to the dominant presence of aerosols in the UTLS. So now let us pinpoint what is actually happening in the UTLS column from 12 to 20 kilometer. So this is the atmospheric forcing for that particular column dominated by anthropogenic nitrate and sulfate scenarios. What we can see is that as expected, the anthropogenic absorption is more than 10 times than the scattering type of aerosols present in the UTLS. And also, this contribution from the anthropogenic dominant UTLS would be around 3% towards the columnar atmospheric forcing, whatever we have seen in the previous slide. But the dominant contribution, if it is more scattering oriented, then we can see that this is less than 1% contribution towards the total columnar forcing. So to understand the actual strength, we can normalize this with the AOD of that particular UTLS region. So we have defined a term called aerosol absorption efficiency, so that we will divide that forcing values with respect to the 500 nanometer AOD for that particular column. So what we found here is that except few different cases, we can see that Gadangi and Hyderabad being in the edge of the Atal region, we can see the efficiencies or the strength of forcings are more or less similar in the UTLS. Whereas in Varanasi, we can see very high forcing efficiencies, or the strength of the radiative forcing is very high as we close to the center of the Atal region. So we can see that there is a large spatial heterogeneity in the strength of radiative forcing as we within the Atal region. So now comes to the aerosol heating rates. This is the mean aerosol heating rates we have observed over the three different locations. So you can see the anthropogenic component in the green line and nitrate and sulfate respectively blue and red colors. One surprising thing you might be noticing here is the very similar heating rate patterns we have obtained for the nitrate and sulfate. Even the difference, if you see, it is of the order 10⁻⁵ Kelvin per day. So what does it imply actually? Because we couldn't capture any much difference between the sulfate and nitrate. One of the possible reason, though we have calculated the shortwave radiative impacts, there exists a strong absorption band for the nitrate aerosols around 2.8 micrometer that we couldn't capture because we have the limited measurement up to 940 nanometer only. So we may need further spectrally resolved aerosol vertical distribution in the future observations. So to conclude, we have seen the enhanced UTLS aerosols over three different locations from the battle campaign. And the strength of the aerosol radiative forcing, what we have seen is varies within the Atal region. So there exists a large spatial heterogeneity, and according to the dominant contribution of the UTLS aerosols, we can expect more complex behaviors or patterns in the radiative forcing, and we need more vertically and spectrally resolved measurements, and also we need to consider the impacts of volcanic eruptions and intense wildfires. What types of aerosols they are populating in the UTLS, that we need to consider, and we may need to segregate them into different components, and we need to see more realistic forcing values in the future. This is what to conclude from this study. So I would like to acknowledge the ISRO NASA team who have extensively conducted this particular campaign, and NARL and Department of Space for providing the financial support, and NASA's Earth Data team for maintaining the data archive, and personally Dr. S.T. Agilraj of Indian Meteorological Department for his valuable suggestions. Thank you for your attention.
Yeah, thank you. Thank you very much. Yeah. So now we'll move on to the next presentation by Nabarun Poddar from SPL VSSC. So his presentation is on understanding the stratosphere troposphere exchange processes over central Himalayan region using ST radar. So you have maybe 8 minutes. Can you finish it? Yeah, thank you.
Hello, am I audible? Yes. So good afternoon, everybody. I'm going to talk on understanding stratosphere-troposphere exchange processes through the direct measurements of vertical air motion over the central Himalayan region, that is using the 206.5 megahertz stratosphere-troposphere radar. So actually my work has been, it has been made easy by two of our previous speakers, Dr. Siddharth Sankat Das and Dr. Manish Naja, by giving us a good overview of what is happening around this region. So to central Himalayan region, we know that it is a very important part of the Asian summer monsoon total region, and the ASMA is active between some 15 degree to 45 degree north and 20 degree to 120 degree east during the months of June, July, August, September. And this is facilitated by the thermal contrast that gets to the Tibetan Plateau region and is driven by the diabatic heating due to the persistent deep convection going on in the South Asian monsoon region. Here is a schematic figure that we can see that this region is also, the mid-latitude regions around these regions are also prone to tropopause folding, and thus it is prone to stratosphere-troposphere exchange processes. Now, the basic motivation for the study is that there has been a huge and good data set of balloon-borne measurements over Nainital. It is in the central Himalayan region, and it is very special because it lies just directly under the ASMA during the June, July, August, September seasons, and it also faces gets the subtropical jet around the winter time, which is very strong circulation pattern. And what happens is that, like, we have extensive studies on this region, but there were no good vertical velocity measurements before the radar came up. Even when the radar came up, we have very good studies that are case-based studies that have been done, and you can see one in the poster presented by Dr. Aditya Jaiswal. But what we want to do is we want to utilize this long-term data that we have good quality data set from 2021 onwards, very regular data that will be showing to understand the average, the climatological feature of this vertical velocity that is quite important to understand the total processes of stratosphere-troposphere interactions in the longer run. But there is one problem with that because of this very exciting topography of this region that you can see here. The location of the ST radar straddled among the hills, it is on basically on a peak. So with that comes some few challenges related to the mountain, the effect of side effect of the mountains. So this is a general overview of the region. We see there is this over this Indian region, the vertical velocity distribution that has been plotted all using the ERA 5 reanalysis data. And these are the zonal meridional vertical velocities that generally climatologically we see around the year as captured by ERA 5 and reanalysis data over Nainital region. And we can see also see the zonal and zonal wind distribution. This is Nainital location. We can see that this reversal wind taking place around this level. So this is basically the 206.5 megahertz ST radar. It's a very robust wind profiler that has been set up there. But we can also see here that the presence of the mountain peak can cause this side lobes of the radar beam to get cause clutter from this mountain peak, and we can get that in a signal. So this is basically towards the north side, as has been encapsulated by Bhattacharya et al. In 2020 about the challenges that comes with it. So what we want to do is we want to characterize the data and try to make it the best, get the best signal possible out of it by using some of our techniques. This is on an average a representative data set for year 2023. So we have almost more than 20 days of data for almost all the months. This red is the one that I'll be presenting today here. June, July, August, and September of 2023. Similar data is present for 2021 and 22 too for this thing. So these are the basic data analysis steps. So this is the very preliminary data analysis steps that we generally do for any wind profiler data that our signal comes in I and Q channel, and these are the online processes that go on. But this is a very important step here. There is the spectral cleaning. As we can see the spectra on the right side, this is for a east beam. We can see the presence of very strong zero interference here due to the mountain that is actually happening due to the mountain clutter, presence of the mountain there. And the system is not getting the signal properly. So when we try to trace the Doppler peaks, this signal won't come up. But we have used our own algorithms to somewhat clean it. And now we can see that we have plotted till 14 kilometers. Actually, for many cases, we get maybe up to 22 kilometers also. This is a case where we can show that the signal is actually becoming a bit cleaner. And this is actually going. So when we trace this, we can actually trace this signal and get this right Doppler profile. So this is basically some of the things that we are doing for this is a 15-degree east beam. So so this is with before it is cleaned. We see the zero interference is there. So naturally, if we run a program or any other software, it will catch this peak. But once we suppress the zero interference somewhat, it will take this, and so we'll get a right Doppler value. Similarly, this is a bit more sensitive case because zenith beam is more that for getting the vertical velocity. Zenith beam is more sensitive to the zero error because the signal will be very close to the zero line. But this is a case that is it is at somewhat distant region from here. Like there is a very small gap, but we can still clean this. If it is inside this limits and we are not able to detect the signal, we are totally rejecting it. Even for our climatology, we have also actually not taken cases that are very high convective cases, that is cases with vertical velocity exceeding more than 0.8 meter per second. So I'll be presenting some of the results. This is a very preliminary vertical velocity profiles that we can show for June, July, and August at 3 times of the day. That is 10 hours in local time, 1300 hours and 1600 hours, because the radar is operated from between 9 to 1800 hours generally. So we have taken that time span. So this is one of the means that basic vertical profiles that we can show is that this is a contoured frequency altitude diagram that we can show the spread of the percentage occurrence of the vertical velocities across this 4 months of the season. So here all the hours of all the profiles for a single month have been averaged here, and we can see this is there is a very high percentage of occurrence in June, so the spread is very less. And the spread is somewhat increases in July and August, and September it again shows some trend that it's like reducing. We can also see in the mean profile, there is a very peculiar occurrence here that we have observed for all the 4 seasons, that there is a strong downdraft here, and there is also another downdraft that is quite persistent here around 10 to 11 kilometers, and there is updraft above this level. So this has been done with averaging all the hours together for 4 months separately. And this is what we have taken is that we have taken all the 4 months together and we have analyzed it hour by hour. So we have taken a period of 3 hours, that is from 9 to 12, 12 to 1500, and then 1500 to 1800 local time. So we see that in the early afternoon hours, early morning and early afternoon hours, this spread of this vertical velocity occurrence is more. And this black line is actually the 5% bound. For 1200 to 1500 hours, we see that this is actually reducing. Again, to 1500 to 1800 hours, it is somewhat, again, it's spreading out. So we see that the velocities, the variation of velocities will be less, and it will be more consistent during this 1200 to 1500 hours here. Similar case characteristics are seen, that is the downdraft strength below 6 kilometers is quite high here. We can see if we do hour by hour analysis, this peak is also showing up, and we can see a consistent updraft here. So this is what we have characterized as of now. So, but this is only done for 2023. And to understand stratosphere troposphere processes, as Dr. Mandisanath already mentioned, we can see this was one of the initial cases that actually motivated us to do this. One of the first detected cases, initial cases. I have shown only two of the plots. Actually, you can see this is for the same period of time. This is for 16th of August 2023. This was a diurnal run. So we can show around, and we had an ozone sonde launch due to a campaign that day. So we can see that there is an enhancement of ozone from that normal, this 5-year mean value that has been taken from the ozone sonde launches over Nainital. So we can see an enhancement here. We can also see around this time, this is around 1:30 at local time, is midnight, and this is around 2 o'clock, this early average. We can see a strong downdraft almost at the same level. And we have also seen the relative humidity values and also the values for the potential vorticity we have plotted, and we have checked that around this time there is great reduction in the relative humidity in this region of in this layer, and we can also see that the potential vorticity at some distance away from that, it has crossed the 2 PV mark, and so we have concluded that the intrusion took place somewhere, and because our observation is limited to this time, so we observed this intrusion case here. Actually, this might not show up in the longer run because it is a case-by-case thing. To conclude, we can tell that we have started doing this work to make this climatology of the vertical velocity. We have long-term data from 2021 to 23, and it is going on. This is only one season. So what we can do is, what we can see is that we can see some general characteristics that are consistent over all the 4 months. But another important thing is that we can see from the profiles that the preliminary movement of the air parcel from the lower troposphere to the upper troposphere and to the UTLS region is actually similar to a two-step process, because it's not consistent updrafts that's going up. Similar case have been proposed previously for the tropical region by Rao et al. In 2008 for 2 other locations that are also somewhat bounded by hills. Similar characteristics have been seen, although not totally same. And our further plan is that we will continue doing this work. We will be analyzing all the data season by season and year by year to create long-term climatology. And also that besides that, we will be trying to compare that similar results with the spaceborne observations from satellites for ozone, water vapor, and also use the balloon-borne measurements for the same. So this is the current state of the work. So this is a very initial.
Thank you. So we'll move on to the last presentation by Venus Venugopal from SPL. So her presentation is on a composite study on the effect of SSW and QBO on stratospheric meridional circulation and implications on ozone and water vapor. So you have 8 minutes, okay?
Okay, thank you. Good afternoon, all. So my presentation will be on the effect on the BDC, the Bureau circulation, the impact by the SSW, sudden stratospheric warming, and quasi-binary oscillation. So the meridional transport, transport from tropical parcels to the high latitudes. So over the tropical region, we have the main variability, that is the quasi-binary oscillation. And over the polar region, we have the sudden stratospheric warming events. So these variabilities, which on the quasi-binary oscillation has a almost 28 months away period, and whereas SSW occurs within a time span of few days. So to start with the effect of QBO on BDC, we'll start with the method, the metrics, the BDC metrics on different phases of QBO and the stratospheric changes. So the method we have adopted is, this is the QBO cycles. So we have taken the minimum wind periods of QBO, and based on that westward wind maximum, we have composited the profiles. So based on this, like this, we have composited the BDC metrics as well as the wind profiles of the period from 1979 to 2021. So this is the wind composite that we are observing. This is over latitude, and the minimum we have taken at index 12, and both sides we have taken 12 months to avoid oversampling. So as yesterday Dr. Sridharan mentioned, we have observing more transport over the where the QBO is on the westward face, and during the eastward face the BDC is weaker. So to analyze, apart from the QBO secondary transport, to analyze the circulation's effect, we have plotted the EP flux divergence, the wave divergence over 30° north to 60° north. You can see over the westward period, when the QBO is on the westward phase, much more wave breaking is observed. Whereas during the eastward phase, the wave breaking is, compared to westward phase, it is much lesser. And also corresponding to that much more wave breaking, we can also see enhanced meridional velocity in the higher latitudes. And the stratospheric changes that follows, we can see during, we have taken the aura microwave limb sounder observations for temperature and ozone. So come on the where the QBO phase is in the westward phase, much more cooler atmosphere is observed in the lower stratosphere at 50 hectopascal. And ozone is also where negative anomaly will be showing in the ozone also. But the water vapor profile is not having a phase shift compared to temperature and ozone. Water vapor is showing a phase shift, which is because the water vapor profiles are much more controlled by the cold point tropopause temperature. So the signal is starting or affected by the CPT temperature, and the signal is, the QBO signal also can be observed in the 100 hectopascal level. From there, you can see the signal is propagating upwards to the stratosphere. And this is the concluding remarks of QBO's impact. And on SSW, sudden stratospheric warming events are occurring over the polar region, where during a few days of time, the polar region will be warming, and the wind also will be reversing. So from the 30 meter per second eastward wind, it will be in a few days of period, it will be suddenly going to minus 30 meter per second. So eastward wind will be suddenly transforming to a westward wind period in the westward wind in the sudden stratospheric warming events. So we have taken the composite of multiple major warmings. And here you can see the polar polar temperature profile. So this dashed black line shows the central date of SW. This is 15 days before, and this is 30 days after. So after the central date, the sudden warming, which goes up as high as 20 Kelvin, is observed over the stratosphere. And also the wind also, just after the central date, it is the eastward wind background is suddenly changing to westward wind over the polar stratospheric region. And this results in the wave transport to the stratosphere. So after the central date, here the much more wave driving is completely absent after the central date of SSW. This exactly follows the wave zonal wind pattern in the 45 to 60° north region, which can be seen over in the residual transport also. The transport is reduced after the central date of SSW, which you can see here. From 200 kilogram per meter per second, it is suddenly reducing to less than 100 kilogram per meter per second after the central date of SSW. So stratospheric changes, the SSW occurs over the polar region, but its effect can be seen over the tropics also. Just after the central date of SSW, much more cooling is observed in the upper stratosphere and lower stratospheric region also over the tropical region. So the effect of the polar extreme event is reflected in the tropical region. So around more than 3 Kelvin cooling is observed in the composite event. In the individual event, it can be even more. In the composite event also, you can see 3 Kelvin of cooling, and it also results in ozone mixing ratio anomalies in the tropical region. Much more upwelling will result in negative anomaly and positive anomaly over the upper stratosphere. And this is the temperature over poles that we have seen before. There also the ozone, breaking of the vortex and sudden downwelling will result in higher higher ozone mixing ratio over the lower stratosphere, over the polar region. And one more thing I would like to add, all the results we have seen for major warming, and for minor warming, there will not be a wind reversal over the polar region for minor warming. So in the minor warming, we will not see that much wave reduction after the central date, like as we observed in the major warming. But there also the residual transport is reduced after the central date. But for major warming, the reduction will be much more intense compared to minor warmings. This is the conclusion. And thank you for listening. Thank you for your time.
Thank you. This we will conclude, and we once again thank all the speakers of this session for their wonderful presentations, and which covered all the observational aspects of UTLS region. It's really a very wonderful session it is. And we also thank audience for the very active interactions. And then
Hello. Yeah. Thank you, everyone. So now we would like to felicitate our speakers. I request the chair of this session, Dr. Bernd Henoy, so to come to the stage and yeah, please. Hello. Yeah. So Dr. M. Venkatratnam. Dr. Ren Smith. Dr. Jean Paul Vernier. Dr. Manish Naja. Thank you, Dr. Bund. Now I request the session co-chair to present the mementos to the remaining speakers. No, come. Yeah. So Dr. Amit Kumar Pandit. Dr. Sunil Kumar SV. Dr. VN Santosh. Dr. Nabankur Poddar. Dr. Venus Venugopal, please. To Dr. Mark Von Hoff. So the role reverses now. Please be here. So you have to felicitate our session chairs and co-chairs. Yeah, to Dr. Bund. Dr. Padma. Thank you. Yeah. Yeah. So before we leave for lunch, we have a few announcements. So participants and delegates from abroad, we require to collect copy of your visa page for our administrative purposes. Please consider this as urgent now. You could do this by visiting our registration desk, where our team will be helping you for taking a copy of that. And yeah, and then the contributors for the next session are requested to kindly upload your presentation here. And we will resume back here at 2 p.m. local time. And yeah, so now we can break for the lunch. Thank you.
afternoon. Welcome back. So we'll be starting with our session 4, which is interconnections of Asian summer monsoon with large-scale atmospheric patterns such as Brio-Dobson circulation, QBO, and ENSO, and SSW. This session will be chaired by Dr. Manish Naza from Aries, Nainital. Over to you, sir.
Welcome to this afternoon session. And of course, I say after the lunch, the session is slightly difficult, but yeah, okay. So in this session, we have the 6th talk. And as you know, we are already running late in the session. So I would like to request all the speakers to keep the time. And the first speaker is Suvarna Farnavis, and she will be talking on association of aerosol in the Asian summer monsoon anticyclone with the Indian summer monsoon rainfall. So, Suvarna.
Good afternoon to all. Today I will talk on association of aerosols in the Asian summer monsoon anticyclone with Indian summer monsoon rainfall. This is based on our few past papers, and although I am presenting, it is our group effort, and these are collaborators. So just a small outline. I will talk on association of anthropogenic aerosol with Indian summer monsoon rainfall, volcanic aerosol, its association with Indian summer monsoon rainfall, and what happens to the aerosol once they reach into the monsoon anticyclone. What are their transport pathways from there? So brief introduction. We know that during monsoon season, anticyclone form in the upper troposphere. There are two modes, Iranian mode and Tibetan mode, and I will be mostly focusing on Tibetan mode. So we perform number of simulations based on ECAM6 Hammond's chemistry climate model to understand the association of this aerosol in the upper troposphere with the Asian summer monsoon rainfall. Our model simulation shows that transport of aerosol from the boundary layer to the monsoon anticyclone over Tibetan mode may mostly occur from the South Asia and East Asia. There are two branches which are shown here in this figure. Aerosols, once they reach into the upper troposphere, they form a layer, and this layer is named as Asian tropopause aerosol layer et al. By Vernier et al. He defined it in the paper 2011, I hope. And this is figure from his paper 2015, which shows et al. From the Calypso measurement over 15 to 17 kilometer in the monsoon 2016. So aerosols, once they reach into the upper troposphere in the anticyclone, they get confined in the anticyclone. Our model show confinement of aerosols in the anticyclone. Here I have shown black carbon aerosol. This et al, which is seen in Calypso and other satellite measurements, are also evident in balloon measurements. These are measurements at Nainital that we have taken under STATOCLIC campaign. These are distribution of aerosol extinction simulated by ECAM model. And we see that this figure is from 15 kilometer above. So once they reach into the et al, they slowly lifted up in the lower stratosphere, equatorward and downward into the southern hemisphere. This is also seen in SAGE and HALO extinction measurements. So we have studied the variability of et al for normal year and El Nino year. Here I have shown two typical cases, El Nino 2015 and normal year 2016. These are scattering ratio from Calypso, and these are simulated by the ECAM6 Hammond's model. Interestingly, we see that during El Nino year, this et al is sitting over the South Asian region. This is Calypso for the year 2015. And for the normal year, this et al is well spread in the anticyclone. So this feature high over the South Asian region is also simulated in our model, and normal year it is well spread within the anticyclone, and we see that these scattering ratios are overestimated in our model. So yes, considering this bias, we move further ahead
and see their association with the Indian summer monsoon rainfall. So as I said, there are two branches. So our control simulation shows that during normal year, there is a South Asian branch and East Asian branch transporting aerosol into the anticyclone. In El Nino, because of subsidence over South Asia, this branch becomes weak and aerosol transport mostly occurs by the East Asian branch. And we have seen that mostly this is dominated by sulfate aerosol. So when we take a difference between El Nino minus control, we see that this is South Asian region. There is a layer of aerosol in the troposphere from boundary layer to the around 300 hectopascal mid-troposphere. And in the upper troposphere, we have Achar. So there are two layers. One is forming a lid above, and there is an aerosol layer in the troposphere. So this aerosol, they scatter back the solar radiation and cause inhibition of solar radiation reaching surface. These are the anomalies from aerosol on simulation, El Nino minus control. And we see that this aerosol layer has caused cooling. This is seen in the surface temperature in the model simulation over North Indian region. There is negative anomalies of solar flux at the surface over South Asian region. This aerosol layer, which I have shown in the troposphere, caused increased the stability of the troposphere and caused tropospheric cooling because of lead in the upper troposphere. So every monsoon year, there is a lead. Atoll is there. But what happened in El Nino, this lead is somewhat thicker and cause more inhibition of solar radiation reaching the surface. So there is more cooling in the troposphere. And we note that cool troposphere weakens the monsoon hadley circulation. So further we analyze the impact on the rainfall. So these are the simulations from when there are no aerosols in the model. Means aerosol are not interacting with the radiative forcing clouds and doesn't affect the precipitation. So these are anomaly for El Nino minus control where aerosols are switched off. So we see that El Nino itself produces negative rainfall over the Indian region. And when we switch off the aerosol in the model, it further reduces rainfall. Our model estimate that this reduction is 17%. So this is the schematic where we describe the processes. So I will not go the detail on that. So further we see the impact of volcanic aerosol with the Indian summer monsoon rainfall. We analyzed volcano. We bifurcated into two parts, tropical volcano and extratropical volcano. We considered all volcanoes occurring between 1871 to 2016, almost 145 years of data. Here, red dots indicate the tropical volcano, location of tropical volcano, and blue triangles indicate the location of extratropical volcano. We see that this Indian region is vicinity to tropical volcano, and further we analyze the impact of both the volcanoes. So we have considered rainfall anomalies. These are the rainfall departures expressed in percentage from India Meteorology rain gauge data for this period 1871 to 2016. Here, black bar indicates the normal rainfall for the normal year, blue for La Nina year, and pink for El Nino year. And here, red stars indicate the tropical volcano. Similar time series is also prepared for extratropical volcano, which is given in the paper. We have considered all volcanoes having emissivity index greater than 3, means all moderate and large volcano. We then apply a probability distribution function on this rainfall time series. Here I show the PDF distribution. Rainfall time series then segregated into two parts. We have considered the years when there are no volcanic eruption. This distribution of rainfall is positively skewed, which is this is black curve. We show that when there are no volcano, there is positive, means more rainfall over the Indian region. This blue curve is when there are tropical volcanoes. We see that rainfall distribution is negatively skewed, indicating that tropical volcanoes reduces the rainfall over the Indian region, which is not the case for extratropical volcano. This is green color curve, which is positively skewed. Further, we see that tropical volcano reduces in rainfall. So what happens if they associated with El Nino or La Nina? So this black curve is for a tropical volcano, rainfall distribution associated with tropical volcano. And this pink is for tropical volcanoes when accompanied with El Nino, we see that it further reduces the rainfall, while La Nina signal is very dominant and it produces, although it accompanied with the volcano, but it produces more rainfall over the Indian region. So to understand this mechanism, we erupted Nabro volcano in IITM 6 HAMOS model along with MPI ESM. Why we chose a Nabro? Because it's a tropical volcano, and we made 10-member simulation from 1st to 10 January 2011. We took it for 2 years. Generally, volcanoes impacts are there for 2 years. So from previous papers, we injected 1.5 teragram of SO2. This we took from the satellite, this amount. We injected it at the location of Nabro, 42 degree east and 30 degree north on 12 June 2011. Our model simulation in agreement with satellite showed that this Nabro aerosol entered into the anticyclone around 26 June, and then these aerosols confined into the monsoon anticyclone. These are the scattering ratio plot averaged over the Indian region. And we see that this is from 15 kilometer and starting from July, because aerosol entered into the anticyclone at the end of June. So we see that there is a thick layer of aerosol over the Indian region in monsoon 2011, and slowly with propagation of time, this aerosol move upward into the stratosphere quite deep. So in the next monsoon 2012, we have Achal here, and there is aerosol layer above. So this kind of distribution we have seen in Calypso. So thick aerosol layer in monsoon 2011, and in 12 there is Achal and volcanic aerosol above. MIPAS also show aerosol here, and there is no data because MIPAS stopped later. So our analysis show that this thick layer of aerosol in the monsoon anticyclone inhibited the solar radiation and caused tropospheric cooling. So this tropospheric cooling has produced a Kelvin wave. There is a clear signature of Kelvin wave in wind stress anomaly. Dr. Krishnan sir also showed similar results from his paper. So our model simulation also shows that they generate Kelvin wave. We can see here that eastward propagating Kelvin wave in central Pacific in the zonal wind stress anomaly. Further, we see that this downwelling Kelvin wave generate a heating in the central Pacific. We see we plot the anomalies from SST, and we see that there is an increase in temperature in Nino 3.4 and Nino 3.0 region in winter and monsoon 2011. But this heating in the central Pacific is more in the next year than the year of volcanic eruption, that is in 2012. There is more heating. So our analysis shows that this aerosol layer in the monsoon anticyclone caused tropospheric cooling and reduced the rainfall. And there is El Nino like warming in the central Pacific, which is higher in the next year than the volcanic eruption itself. So we analyze the rainfall distribution from our ESM simulation. This is our rainfall anomaly simulated by our Earth system model, and we see that this volcanic Nabro volcanic eruption has reduced the rainfall over the Indian region, which is also evident in GPCP and IMD rain gauge data. So this is for the year 2011, and this is for 2012. Rainfall reduction in the volcanic eruption year is higher than the next year. This is because of thick layer of aerosol, which has reduced more rainfall. While in the next year, aerosol moved up higher into the stratosphere, and impact of El Nino has dominated in this year. So this came to my mind that Simon has yesterday talked about if we inject the aerosol at the higher height, then the rainfall reduction is less, maybe less, and which is also seen in our model. And in 2011, aerosols are near the tropopause in the UTLS, and there is more reduction of rainfall. This is also seen in IMD weekly rainfall departures. So using this schematic, we explain the process. This is normal year. There is a monsoon Hadley circulation and rainfall. When there is volcanic eruption, plume form, it radiates back the solar radiation, tropospheric cooling, and causes reversal of monsoon Hadley circulation, reduces rainfall, generate Kelvin wave. Kelvin wave dissipation is higher in the next year and reduces the rainfall over the Indian region. So impact of volcanoes are seen for 2 years. So further we see that, okay, these aerosols, volcanic or anthropogenic, they enter into the anticyclone. What is their further transport pathway? So we have seen there are two branches, one South Asian branch and East Asian branch. So we made simulation with South Asian emission of aerosols on and off. So in control, we have all aerosols, and in SAS0 simulation, we switch off the aerosol over South Asia, and another simulation, we switch off the aerosol over East Asia. This is distribution of black carbon, and these two are for organic carbon. In the monsoon anticyclone region, we see that there are more aerosol from the South Asian branch as compared to East Asian branch in the monsoon anticyclone. Our simulation also shows that lifting of aerosol from South Asia is stronger and higher because of the Himalayan orography and convection occurring at the southern slopes of Himalaya, while outflow of aerosols from the East Asian simulation shows at a lower level. This is at 380 K potential surface, and in the paper we have shown that black carbon distribution from East Asian simulation is high at the 340 K potential temperature. Further, we analyze its transport pathway. So this is distribution of, I have shown only one figure here, distribution of black carbon aerosol averaged over the ASMA region, and this is from South Asia and this is from East Asia. And we see that their aerosols are lifted up. This is black line is tropopause, above the tropopause, and then they are isentropically transported to the Arctic. So we have found out what is transport pathway for this such a long distance transport of aerosol from Asian region to the Arctic. We saw that biodopsin circulation plays an important role. These aerosols get entered into the shallow branch of biodopsin circulation, and then they are further transported to the Arctic. Those figures are there in the paper. I have not added here because of limited time. So both from South Asia and East Asia, aerosols are transported to the Arctic. Further, we estimate the radiative forcing, and we see that radiative forcing estimated from the aerosols at the Arctic. This is radiative forcing at the Arctic, and this is for South Asia, and this is from East Asia. We see that South Asian aerosol produces positive radiative forcing at the Arctic, while from East Asian aerosols, they produce negative radiative forcing. We see that transport of aerosol which are transported to the Arctic from South Asia are dominated by black carbon aerosol, which are responsible for producing positive radiative forcing, while aerosol which are transported from East Asia to the Arctic are dominated by sulfate, which produces a negative radiative forcing at the TOA at the Arctic. And at the surface, both South Asian and East Asian aerosol produce cooling. So our model simulation showed that surface cooling produced by East Asian aerosol is higher, that is minus 0.56 K, while from the South Asia, it is 0.043 Kelvin, it is very less. Here I stop. So this is a figure schematic. Here we show that aerosols are transported into the monsoon anticyclone. They enter into the biodopsin circulation, shallow branch, which are then isentropically transported to the Arctic and cause cooling at the surface. So results are the same. There are two branches, transport of aerosol, South Asia and East Asia. Both anthropogenic and volcanic aerosol reduces rainfall over the Indian region. So aerosols, once they enter into the anticyclone, they are further transported to the Arctic and cause Arctic cooling for East Asian aerosol, while cooling caused by South Asian aerosol is comparatively less. So I stop here. Thank you. And I can take some questions, very quick question, if there is time.
Yeah.
I know we are running.
But if suppose some very pressing one question, otherwise you will save the time. Okay, I don't see anything. We will skip and then take all the at the end. So now we have the next talk by Dr. Kishore from SPL, and he will be talking on the QBO and its modulation with the monsoon headley circulation.
Very good afternoon. I'm Kishore Kumar from Space Physics Laboratory, Vikram Sarabhai Space Center, and I'll be talking about does quasi-binary oscillation modulate monsoon Hadley cell. So just a background. So we get more insolation for the equator as compared to the poles due to the sphericity of the Earth. So the maximum insolation for the equator is distributed by two processes. One is oceanic circulation, another is from atmosphere. In atmosphere, this task is accomplished by Hadley cell, which has a rising branch at the equator. At the tropopause, we have a poleward movement in the either hemispheres, and there will be descending motions near the subtropics around 30° north. Then there is a equatorial flow and from the both the hemisphere, which forms the trade winds, and we have a ITCZ also at the convergence zones. This is the Hadley cell, and the recent study shows that this Hadley cell is expanding at a rate of almost 1 degree per decade. So it has a lot of concerns. One of the things is you can see most of the deserts and semi-deserts are present at the descending branches of the Hadley cell, and it is expanding toward the poles. The desertification will also be expanding toward the poles. This is one of the important consequences of Hadley cell expansion. Not only this one, actually it dictates the weather and climate over the tropics. You can see the formation of the clouds, tall clouds like deep convection forms over the equator. And because of the descending motions, most of the clouds tops will be restricted to the lower troposphere, such as stratocumulus, and the shallow cumulus only will be found near the descending branches of the Hadley cell. So Hadley cell, as for the dynamics, is very, very important. It not only controls day-to-day weather and long-term climate also. So the objective of this particular study is to see whether we can really have a metric to extract the regional Hadley cells using some kind of a technique, and whether this quasi-binary oscillation, which is a stratospheric, equatorial stratospheric process, has any implications in controlling or modulating the monsoon Hadley cell. So traditionally, this monsoon Hadley cell has been characterized by the meridional wind taking a 200 HPA and 800 HPA, because the usual metric which we use for estimating the Hadley cell boundaries as well as intensities called mass stream functions. So here for using this mass stream function, we use error data and rainfall data for characterizing the monsoon, and radio sound observation over Singapore for characterizing the QBO. And as I said, we'll be using a technique called Helmholtz transformation to have a regional Hadley cells. I'll be just showing some illustration how we are going to do that one. So as I said, traditionally, we have a function called mass stream function, which is used for calculating the boundaries and intensity of the Hadley cell. But one of the limitation of this metric is we have to have a zonal mean, because mass should be conserved in the zonal direction. We just average zonally to get this. There is a typical Hadley cell during December, January, February. The mass stream function, the pressure level, you can see here. During the winter, boreal winter, the monsoon, not monsoon, this was a Hadley cell. The center of the Hadley cell will be around -5 degree, because ITCZ will be in the southern hemisphere. You can see one branch towards the polar region, North Pole, and one more very weak branch toward the South Pole. This is, we can using this mass stream function, we can characterize not only the intensity, we can see the boundaries also, where is the edge of the Hadley cell, center of the Hadley cell, and maximum and minimum intensity of the Hadley cell. As I said, this is a traditional method to do this one. But there is a thing that we need zonally resolved one. So before going that one, this is one of the results from our earlier studies, which shows that Hadley cell is expanding toward the poles. What is shown here is the anomaly in the total width of the Hadley cell. Using 4 reanalysis data, all the reanalysis data show approximately 1 degree per decade of expansion toward the polar region. So this is again zonal mean Hadley cell. So now we get a very new technique to zonally resolve this Hadley cell. You feed the zonal wind and meridional wind to a Helmholtz decomposition. Then we can put a rotational part and divergent part. Both these parts will be having rotational component and divergent component, and use only this meridional divergent component to estimate the mass stream function. Then we can have a regional Hadley cells. So this is just taking a horizontal wind, observed wind, and dividing into divergent part and curl part. This is how we are doing it. So after doing this, this is the first climatology we got for 4 seasons. What is shown is the mass stream function at 500 HPA, and this boundary is identified from the MSF function. You can see this both thing gives the ascending region of the Hadley cell, and this one, and this shows the descending regions of the Hadley cell. So we can exactly characterize this Hadley cell zonally resolved. So how to validate what are the boundaries we have identified is we took vertical velocities and we overlaid the boundaries on the vertical velocity for the 4 season. You can see the ascending region comprises of the ascending motions. All the blue part shows the upward motions and the red part shows the descending motion from ERA reanalysis data. Exactly, it could capture the ascending and descending regions. So this is how we have characterized this thing. Further, one more thing we have carried out is we have from IB tracks data, we have something called latitude of maximum intensity of cyclones. Where the exactly cyclone maximizes that latitude for 2 seasons we have just spotted, just to see what are the boundaries we have got is exactly matching with this one. Most of these things are matching with ascending region Hadley cell. What we have observed is most of the this one cyclones are maximizing near the edges of the ascending region of the Hadley cell in both the seasons. Further, we have seen that this Hadley cell is expanding, whether it has any impact on tropical cyclone formation latitude. So we can see we have done trend analysis of both 4. One is two of the things are from the Hadley cell. One is ascending region boundary and descending region boundary, and these 2 things are latitude of formation of the cyclones and latitude of maximum intensity of the cyclones. All are showing the expansion toward the poles. And we have proposed a method how it exactly operates, where Hadley cell is moving toward the pole, the cyclone formation latitude is also moving toward the poles. So now coming to the exact what we are looking for in this study is characterizing the quasi-binary oscillation in the stratosphere. So by seeing this figure, we can ask who says that atmosphere is chaos. Very systematic pattern we can see in the stratospheric winds from the radio sandy derived from the radio sandy observations. This is up to 1950 to 2013. But recent decade, if you see, there's the 2 events. We can see here, these are called QBO disruptions. And there are a lot of analysis has been gone to really, but none of the models could predict these 2 disruptions. But the hindcast only people can do. We also had proposed some kind of long period planetary wave enhancement during these 2 disruption event. And we know that quasi-binary is nothing but a wave mean flow interaction, which is primarily driven by the Kelvin waves, Rossby gravity waves, and gravity waves. So now what we did is, we have first calculated zonal mean Hadley cell during the June, July, August, September, during the monsoon period. This is a total zonally averaged. This is only over the Indian region during the monsoon. You can see without further any estimation, you can see a very strong cell over the Indian region. Further, we divided the total observation into eastward phase and westward phase of the quasi-binary oscillation. So you can see here, this is the eastward phase and this is the westward phase, and the difference between the 2. We can have during the westward phase, we have a very strong Hadley cell. This is the absolute value, absolute difference. Very, very strong winter cell. And here also you can get very weak summer cell. You can see here. Here itself, it is very, very important. You can see here that summer cell is very strong here compared to the here. So similarly, here QBO we have defined at 20 HPA. So at 10 HPA also similar kind of a pattern you can see, the eastward phase, westward phase, and the difference between these 2 things. So what we see is toward the westward phase, we have a very strong winter cell, very weak summer cell. So how it interacts with the monsoon is, if you see earlier, most of the studies has taken monsoon Hadley cell index. It is nothing but the meridional wind at 850 and 200 HPA. Just subtract it and take the anomaly. We'll find this one. This is called as MHI, a monsoon Hadley cell index. It has a very good correlation with the Indian summer monsoon precipitation. This is a standardized anomaly. You can see it goes hand in hand, almost like 0.71 correlation with 95% significant level. So this is how this intensity of the Hadley cell and the ISMR is connected. So coming to this one, now we have a zonally resolved Hadley cell intensity over the Indian region. So just we wanted to see how it connects with the Indian summer monsoon rainfall, you can see northern hemispheric intensity versus standard precipitation. You can see the go hand in hand. This says that there is a interlink between the Indian summer monsoon rainfall and the intensity of the thing. And intensity is modulated again by the quasi-biennial oscillation, where we have seen that westward phase of the quasi-biennial oscillation has a strong winter cell and a weak summer cell. So now we proposed a pathway through which this modulation takes place. You know that this is the Hadley cell, and we have a Brewer-Dobson circulation in the stratosphere. And this Brewer-Dobson circulation is modulated by quasi-biennial oscillation. There are a lot of reports in the literature. So this thing which goes to the higher latitude, this downwelling branch of Brewer-Dobson circulation reaches up to the surface. And the compensation of this stratosphere air coming to the troposphere is done through your Hadley cell from troposphere to the stratosphere, the mass conservation. So this is how Brewer-Dobson circulation imprinted on the QBO, and that compensating motion toward the low latitude is having a couple. This is the one pathway. We are working on the any similar anything like a ENSO, QBO, and Hadley cell interaction also. Let's stop here. This is a summary. Yeah.
If any very quick question, you can take only here. Yes.
Yeah. Yeah.
That's zonally resolved.
Yeah.
There is some paper by Schwendijk et al.
Yeah.
In 2014.
Yes,
15.
yes,
So,
same.
is it
Yeah,
the
same
approach?
equations. Yeah. Yes, sir.
Okay, thank you, Dr. Kishore.
Yes.
So now next talk is by Dr. Uma Das from IIT. And she will be talking on tidal variability and its effects in stratosphere using the satellite model and reanalysis data. So, Dr. Das.
Good afternoon, one and all. I'll use this mic, otherwise I'll not be visible to half the audience. So I am Uma Das from IIT Kalyani. So some of this work is done by my student Shubhajit Devnath and along with the team. So I'll be talking about tidal variability and aliasing effects from contemporaneous satellite model and reanalysis data in the stratosphere. I'll skip most of this slide, but what I'll be talking mostly about are the non-migrating tides, the ones which are either moving faster or slower than the sun. And I'll be concentrating upon how they are produced. Is it via nonlinear interactions or not? And whatever we see from the satellite results, are they truly geophysical, or if they are caused by any aliasing effects? So these are the entire study is based on these three objectives. However, I'll be talking mostly about the aliasing effects, possible aliasing effects, and if they're real, if they're being generated by the nonlinear interactions. So the importance of these satellite versus ground-based measurements, I'll take a second. So if you look at the gray contour in the background, this is a diurnal tide in the universal time and longitude space. So from a satellite, if you see along the satellite path, for this particular wave, you're actually sampling the wave along the same phase line. So basically, you're not getting any information, and hence you need a ground-based measurement, which gives you sampling of all the phases. So this is how it is. You get all the phase points from a ground-based measurement and the same phase for the satellite for this particular wave. Just an example. If it is some other wave, if it's a stationary wave, on the other hand, you will have all the phases sampled by the satellite, but the ground-based instrument would be sampling only one phase. Hence, it's always a good idea to look at satellite and ground-based measurements to get a perfect picture of the tidal variability or wave variability for that matter. So in this work, we have used two satellite data sets. One is SABRE, onboard the time satellite, and the other is COSMIC 1 mission. And then we use the CMAM 30 model and also data from the ERA interim. We used both temperature and wind data sets. This is the same thing, phases being sampled by different satellites. So here, all of us know that when we are working with SABRE data, we need to take 60 days of data so that we get the correct tidal variability. The reason being that as the satellite is slowly processing, it will be sampling, it will be taking measurements over the same location 15 to 20 minutes earlier. So to get the entire 24-hour local time coverage, you need 60 days of measurements. Hence, we have to combine all that for SABRE. This is how it looks like. So in the background, you have a variety of diurnal tides. And so we'll have to consider all these dots are the measurements of the satellite. But in case of cosmic is very interesting. It's the measurements and the sampling are not regular because we are having a low Earth orbit satellite and GPS in the geostationary orbit. And whenever an occultation is possible, you are getting a profile. And so it's very haphazard in nature, which actually is the plus point for reducing tidal variability, because then you don't need really 60 days of data. You can get shorter term tidal variability. Like for example, if you take 11 days, you're sampling all the different phases of the different diurnal tides. But whereas in SABRE, you're only sampling some of the phases, and so it becomes insufficient in case of SABRE. And in this way, cosmic is actually useful. So we use the standard method of least square fitting to derive the parameters. So these are the tides, and these are the stationary planetary waves. So these are some results from the cosmic temperature. I'll just move forward. So here what we have done is to address this aliasing problem, because see, we are having the satellite measurements either from SABRE or from cosmic. And so we are doing a least square fitting. We are trying to, extract all the parameters simultaneously. But to see if something is being aliased or not, what we have done is we have conducted some numerical experiments where for the given latitude, longitude, and time of those measurements, we have assumed just one single wave. And we have created an atmosphere using, these are all the different cases where we assume only a constant temperature, or this is we are assuming only a stationary planetary wave, which is slowly varying, etc. We have 10 such cases listed in this table. And when we apply this least square fitting method, so if there was only one wave, that is the only wave that should be coming out as output. But this is not the case. When we are considering stationary planetary waves and tides, things are reasonably good. These are for the cosmic sampling. But here, when the mean temperature is varying, it is slowly varying, you see that all these components are coming up. These are basically due to the aliasing. And even cosmic, it is coming up in the high latitude region, but in the near the equator and the tropical region, this is not there. So with cosmic sampling, we are getting good tidal variability features in the lower latitudes. So these are the results. We see the DS0, which is the diurnal stationary wave. We have maximum over the equator during the summer season, and DW2 during the winter season. So now this DS0 during the summer and DW2 during the winter, I missed, I think, a point when going in a hurry. So DS0 and DW2, these two are the diurnal, non-migrating diurnal tides, which are believed to be generated due to nonlinear interactions of what are called as the stationary planetary wave and the migrating diurnal tide, right? So if these were indeed caused by those nonlinear interactions, then what would happen is the variabilities would be similar to these stationary planetary waves. So when we see it in the cosmic data, we have, let's go back a second. So we see these non-migrating tides in good features over the equatorial region. This is from cosmic, and also some features in the high latitude regions. But when we look at the CMAM model temperature and the ERA temperature, these high latitude features, they're all missing. Actually, we see only the equator tropical features are visible. So what we understand is, like I said in the numerical experiments part, these high latitude features could be due to aliasing. And to confirm that, what we did is we took the model, the CMAM 30 model, as a real atmosphere, let the satellite fly through that atmosphere and take the samples of, as though the Sabre was sampling it or as though Cosmic was sampling it, create new data sets from these models, and then apply these regular methods that we have been doing and check with the original results of the model whether the sampling, the satellite sampling, is affecting the analysis. And this is what we found. Found that these are the original era results. And you see that from the Cosmic, when we take a 21-day window, it really is good. Even for a 61-day window, it is good. But when it comes to Sabre, since we are taking a 61-day window, these things are all the, we infer that these all could be due to the aliasing part. So if we look at the time and latitude structure also, so these are ERA results, which are we see only over the low latitude regions. From the Cosmic, we see that these are coming up, but in the very high latitudes, if we go beyond 50 degrees, again, we are seeing the spurious cases, and anyway, Sabre does not give us the results beyond 50. So what we infer is, Dr. Naja is standing up. So what we infer is, we do have the non-migrating tides being produced in the lower atmosphere. They could be traveling upwards, but there is no generation of these non-migrating tides in the upper atmosphere. So whatever DS0, DW2 tides are seen in the high latitude stratosphere, these are basically due to aliasing effects, and the nonlinear interactions are not important here. I could not cover this part, but we do have results showing that the nonlinear interactions are important over the mesosphere, in the mesosphere region. You see SPW1 at 10 hectopascal in the high latitude region. This variability matches with the DW2 in the mesopause region over the equator. So the stationary planetary waves are moving from the high latitude region towards the equator. There the nonlinear interactions are happening, but they are not happening in the high latitude stratosphere. There, whatever is happening, whatever we are seeing from Sabre is basically due to aliasing. So that's the result. And yeah, I'll stop there. Thank you.
Yeah, thank you, Dr. Das.
Thank you.
Only one question, if any. I don't see. Okay, thank you.
Thank you.
And I would like to check if the online presenters, Chirag Dhara, is there.
Oh, yes, I am.
Yeah, hello, Chirag.
Hello. Hi, good afternoon.
Hello.
Hi, can you hear me?
Yes, yes, we can hear you, and I hope you can hear us also.
Perfectly.
Yeah, so try to make your presentation in 10 minutes.
I'll try.
Yeah, this talk is on basically impact of the rapid reduction in the regional aerosol and then on the South Asian monsoon. So, Chirag. Yeah.
Thank you so much. Just try to. I'm unable to share my screen. Can you please enable it?
Yeah. Screen. Yeah, I think you try again. Yeah, screen sharing. It is enabled.
Not yet.
Yeah, yeah. Okay. Just maybe 10 seconds, 5 seconds.
Sure. Okay.
Yeah. Okay, good. So maybe you can come the first slide. Oh, I'm seeing a lot of slide. You have 39. So try. Yeah, wind up.
Backup slides.
Yeah, yeah. Okay, yeah, okay.
Okay. I hope my screen is there.
Yeah, okay. You can see.
Yeah. Okay. Thanks all very much, and thanks to the organizers for inviting me to give this talk. I'll just get right into it. So I'm talking about the impact of aerosols on near-term precipitation. So lots of studies have focused on the effects of anthropogenic aerosol pollution on the South Asian monsoon. These are, of course, just a sampling of the many, many studies that now exist. Historically, rainfall has declined by about 5% over the Indian region, 1950 to 2015. This was assessed both in the Indian Regional Assessment Report, and this has been partly attributed to aerosols. In terms of the future, this is a significant question for this region, but significant uncertainties remain in our understanding and projections. And therefore, in this study, we are performing certain sensitivity experiments with the IITM Earth System model to study how the monsoon response may be with future aerosol reductions. So to set up what experiments we do, we have basically performed 3 equilibrium experiments. So that's AER 245, AER 119, and a reference experiment. And the way these experiments are prescribed are as follows. With the first experiment, we are prescribing aerosols as under the usual SSP 245 for the year 2040, and also the CO2 in the year 2040 under SSP 245, which amounts to 475 parts per million. And we perform 50 years, simulation of 50 years with these fixed boundary conditions. So it's an equilibrium experiment. Now, the next experiment differs from this one only in their aerosols, which is prescribed as those under SSP 119 for the year 2040. And the reference that we take is aerosols and CO2 for the year 2005. So aerosols under 2005 and CO2, which was 379 ppm in that year. So we basically look at the anomalies of these 2 experiments against the reference climatology. So in summary, we are using the IITM Earth System model. We do 50-year runs with fixed boundary conditions. And we are taking the JJAS climatology to study the South Asian summer monsoon. And we take the mean of climatology over the last 45 years. So let's first look into how the aerosol optical depth looks, the difference between these 2 experiments. So when we look at this, the top panel represents the first experiment, which is 245, and the bottom panel is under 119. You can see that over most of the northern hemisphere, there's a decline in AOD, except over the South Asian region, and a smaller increase over the Central African region. In contrast, under the aerosol 119 experiment, you see a reduction in most parts of the planet, including the South Asian region, and only a small rise over this part of Africa. So specifically, I would like to draw your attention to this dipole-like structure in AOD, where there's a decrease in AOD over East Asia, but a significant rise over South Asia. Whereas when you look at the other experiment, there is a reduction everywhere, including the South Asian region. So there is a flip in the sign of the AOD between the 2 experiments. And this is what we study, how this changes the monsoon response. So of course, we expect the AOD, changes in AOD to impact the radiation budget. And so we look at, the clear sky surface net radiation. So the one on the left is the one with increased aerosols over South Asia, and the one on the right is where aerosols decrease everywhere, the 119 experiment. So as we saw with the dipole structure in the AOD, that dipole structure is also reflected in the clear sky net radiation at the surface, where you have, because of the increase in aerosols over South Asia, you have this decrease, those are the blues, in surface net radiation over the same region. And on the other hand, you have this excess energy over East Asia. And as we expect then, with the other experiment, we have an increase, an energy excess over the entire Asian region in the other experiment. Now, with this change in radiative energy, we would also expect a change in temperature. So specifically that temperature rise is, we would expect that it would be muted over the South Asian region, as indeed in the observed period, the temperature rise over India is only about 0.7 degrees, substantially less than the global mean, and partly that's because of aerosol cooling in the past. So we would expect that also in the future with these kind of changes. And specifically, I would like to draw your attention to the SST change, because we see a signature even over there. So as you can see with these reduced aerosols, even over for the SSTs, we find this larger increase in SSTs in the North Indian Ocean compared to the other experiment. And indeed, when we look at the temperature gradient, so we are looking at 40 south to 40 north in both experiments, and we are averaging over 60 to 120 east, so the South Asia to East Asia region. We find that the temperature gradient increases much more in the second experiment with reduced aerosols compared to the first one. So this implies changes in circulation, which is what we look at over here. So there are two things being plotted here. First, we look at the arrows, which represent the moisture transport, vertically integrated. Now we find that moisture transport has increased to some degree even in the first experiment, but much more so in the second experiment. The increase in the first experiment may be understood in terms of the changes in remote aerosols, because as you know, as we saw, the aerosols over the Indian region has increased, but the aerosols over the northern hemisphere mid-latitudes has decreased. And that could have an impact on the South Asian monsoon through large-scale changes in the ITCZ. The signature of this larger increase in the moisture transport is clearer with the regionally reduced aerosols over the South Asian region. Now the shading here is the outgoing long-wave radiation, which is a proxy for convection. And so with these increased positive OLR anomalies over the Indian region, that indicates suppressed convection, whereas you can see this negative OLR anomalies over the Indian South Asian region and the North Indian Ocean, which indicates enhanced convection over this whole region, over this large region. In association with that is moisture convergence, where we see this with increased in association with increased moisture transport. We see this moisture convergence over this larger region, which causes ascending motion. Over here, there is a more mixed signal, but generally smaller rise in some localized regions, but over the larger region, a decline. And that brings us to the precipitation response. And as we expect, with enhanced convection and enhanced moisture convergence in this region, we find this precipitation increase over this larger region. Whereas there is a declining signal in the other experiment with increased localized aerosols. The last thing, and I'll close with that, is to show that the spatial patterns of precipitation in these two experiments are explained by the dynamical contributions. So to see that, we do this approximation of the change in precipitation into two terms. Here, Q represents it stands for the surface specific humidity, and omega is, of course, the vertical velocity at 500 hectopascal. The first term denotes the dynamical contribution, and the second one denotes the thermodynamic contribution. So we look at what these two terms look like. When we look at the thermodynamic contribution to precipitation change for the two experiments, the magnitudes and the spatial patterns are largely similar for the two experiments. Whereas when we look at the dynamical contribution, we see that there are more spatial differences. And in fact, when we add up the dynamical and thermodynamical contributions, we in fact reproduce the spatial patterns of precipitation. So what we conclude is that the spatial patterns are in precipitation are largely coming from these dynamical changes and much less from the thermodynamic contributions. So to summarize and conclude, we have done these experiments with the IITM Earth System model, and we find that there is enhanced convergence and deep convection over the South Asian region with reduced aerosols, and the spatial patterns of changes in precipitation are shaped by changes in circulation. So from a more policy-like perspective, our choices of technology and therefore the changes in air pollution, their implications for air pollution in the future, can have a significant bearing on future rainfall change. So with that, I'll stop. Thank you.
Yeah, thank you, Dr. Chirag, for keeping the time. I think we'll take up the next talk to maintain the time now. So next speaker is Prashant Chauhan, and he will be talking on impact of volcanic aerosol on the tropical stratosphere and disturbance on the QBO.
Yes. So good afternoon, all of you. I am Prashant Chauhan, working here in IITM. So I will be talking about the impact of volcanic aerosol on the tropical stratosphere and disruption of the QBO. So there are a lot of motivation to undertake this study. For example, for all we know that volcanic aerosol can directly inject the SO2 gas into the stratosphere, and oxidation of SO2 gas can convert into the sulfate aerosol, and they increase the sulfate aerosol loading in the stratosphere. And this sulfate aerosol can lead to cool the surface and top of atmosphere. And while the sulfate aerosol can absorb the air radiation and that heat the stratosphere, and that associated heating in the stratosphere need to undertake. And on the other hand, some geoengineering study shows in the past, like when we inject the sulfate aerosol in the stratosphere, there is a significant perturbation happens in the perturbation happen and disrupt the QBO. And there may be like a prolongation of the QBO for more than 3 years. And in extreme case, it is shut down. If there is a more injection of sulfate aerosol, for example, more than 60 teragram, so sulfate aerosol can shut down. But since we do have a volcano as a natural source of sulfate aerosol, we need to understand what will be the happen. So here I have tried to understand the things. So for that, we simulate the experiment using ECAM6 Hammer's chemistry climate model. There are two emission sensitivity experiment for where all the aerosol, including volcanic emission, were kept on, and all volcanic aerosol emission are switched off during 2001 to 2013. And we analyze the difference between base and world zero simulation during the 2001 to 2016. And this is the list of volcanoes. So there are 20 volcanoes during this study period, 2001 to 2013. 10 are in the tropics, 8 in the northern tropics, and 2 in the southern extratropics. So this is a figure shows the global mean stratospheric AOD during 2001 to 2013 from the model simulation. So red line shows the global mean AOD, and the blue line shows the AOD in the tropics. So we can see there is a significant enhancement in AOD, and there is a peak in AOD during 2006, 2009, and 2011 due to these volcanoes. And there is a less enhancement AOD due to the, since this period is come under the volcano quotient period. Moving to the next, so this is the radiative forcing at the top of atmosphere and associated heating rate for the global mean. We can see there is a reduction, significant reduction in here radiative forcing at the top of atmosphere and heating rate. There is enhancement in heating rate, but this figure shows the radiative forcing and the heating rate in the tropical region. 20 degrees south and 20 degree north. So we can see that this suggests that the volcanic aerosol lead to pronounced warming effect, particularly within the tropical region. And this figure shows the less. Here we can see there is a less enhancement in this figure is the time series of volcanic sulfate aerosol anomaly from base minus world zero simulation, average door 0 to 360, 20 degrees south and 20 degree north from model simulation, and figure B is the heating rate. So we can see there is a less enhancement in the sulfate aerosol in the stratosphere due to this is quotient volcanic quotient time period, and we can see there is a enhancement in the sulfate aerosol due to series of moderate and large volcanic eruption. And this is the associated heating rate. We can see there is a less heating rate, and after that there is a heating rate is enhanced. In the stratosphere, you can see there is a 200 to 5 HP, there is a more heating. But it is very interesting to see the substantial increase in heating rate due to stratospheric volcanic aerosol can induce the remarkable alteration in quasi-binary oscillation. So this is a wind QBO from base simulation averaged over 0 to 5 degree north. We can see easterly is completing one oscillation, easterly and westerly completing one oscillation within 24 to 26 months. But after the volcanic effect, there is a prolongation of easterly and westerly for some month. For example, like easterly is prolongation by 12 to 20 months, and westerly is prolongation by 16 to 24 months. And this is the impact of volcanic aerosol on the quasi-binary oscillation amplitude. We can see wind QB amplitude from base simulation, and when we see the impact of volcanic aerosol, there is a strengthening of QBO around that height 10 HPA, and we can see there is a strengthening of amplitude. And this is the conclusion of my study. The volcanic aerosol enter in the tropical pipe. The enhanced DOD in the tropical pipe, and the cooling that's cooling at the surface, cooling at the TO, and that leads to enhanced heating rate in the tropical pipe. That leads to prolonged easterly and westerly and strengthen the QB amplitude. Thank you.
Thank you, Chant. If any, Chant, you can take one. Yeah. It's a nice talk. Could you able to simulate the 2015 disruption on QBO?
Yes, sir, we can.
But you have not shown that.
Yes, we have not shown it.
Okay, so last talk for this session, which was left out on yesterday by Dr. Vasha, and he will be talking on disturbing the middle stratospheric balance, the enduring impact of Honga Tonga volcano.
First of all, I thank organizers for giving me this opportunity. And myself, Gauss Basha and Venkat Ratnam, we are from NARL. Today, I am going to discuss a few aspects, how this Honga Tonga volcanic eruption disturbed the middle atmospheric balance. Coming to brief history, this Honga Tonga volcanic eruption is located in the southern western portion of the Pacific Ocean. And this specific Honga Tonga volcanic eruption occurred on 15th January at 4 UTC 2022. Within few hours of time, this eruption, these plumes of this eruption reached to upper troposphere. And later studies showed that these plumes reached to almost nearly stratospheric altitudes within few days. You can see here. And its debris reached to nearly the uppermost part of the stratospheric region. This figure is from this Van et al. And nearly the bulk of this plume, that means the plume lingered for several days in the stratospheric altitudes, nearly 18 to 30 kilometers for several months. The basic motivation for this, our study is, previously most of the nearly on this Honga Tonga volcanic eruption, more than 50 articles was published, but mostly on aerosol characteristics, atmospheric circulation, transport, and other things. But here our interest is to understand how the stratospheric water vapor is impacting the middle atmospheric balance and its relation to temperature and ozone. Here we have used microwave limb sounder data for long-term data sets like water vapor, temperature, and ozone data, and MERA2 wind data sets. This is the profiles of water vapor and temperature immediately after the volcanic eruption. This is January 14 to 18, 2022. We can see that clearly after the volcanic eruption, we can see a huge amount of water vapor has been transported to these altitudes in stratospheric levels, upper tropospheric levels. Even the monthly mean, that means the water vapor which was injected by this volcanic eruption, it was stayed for several months here. This is the monthly mean figure and difference. And coming to temperature, initially we have seen that there is an increase in temperature immediately after the volcanic eruption. And later, the temperature has decreased drastically, nearly 5 Kelvin in the stratospheric levels. This is the daily mean climatology from 2005 to 2001 and daily mean this is after the volcanic eruption, January to 2 years of data. And this is the difference in water vapor, temperature, and ozone. We can clearly see that the imprints of this Honga Tonga volcanic eruption and water vapor. We can see before initial days of January 2022, there is nothing is there. Almost the water vapor is nearly zero. Okay. And then after that, after injection of water vapor, we can see its tracers. And it is for several months, almost like from January 15, 2022 to November 22, water vapor presence is there nearly. And later, the water vapor has been transported to the higher altitudes. Okay. Similarly, initially the temperature was increased. Later, the temperature decreased with periodic episodes. In case of ozone, we can see at nearly 10 HPA, we can see that the decrease in ozone is observed. That means the increase in water vapor can lead to the decrease in temperature and ozone. This is the preliminary observation. What we have observed is, for further observations, this is the meridional variation, and this is latitude and day-wise. And this is the background is the wind vectors from MERA data sets in water vapor, temperature, and ozone. Here, in case of water vapor, we can see that the water vapor has been dispersing towards the southern hemisphere with respect to time. From almost like nearly November on mid of the November, one branch is transported to the northern hemisphere. That means the water vapor is circulating towards the southern hemisphere and towards the northern hemisphere. But in case of temperature, we can see that we're during almost like from July 2022 to November, we can see the temperature has been decreased drastically. This decrease in temperature mainly is due to the water vapor because of IR cooling due to the water vapor. In case of ozone, similar observations, we can see that the decrease in ozone is clearly observed in the regions where the water vapor has been increased. And this is this figure shows that this is pressure and latitude variation of water vapor variations only. Normally in January 22, the water vapor has been ejected by the volcanic eruption. We can see clearly around 31 to 21 HPA. And with respect to time, this is for different months, the dispersion started. We can see that its dispersion started towards vertically and towards the northern hemisphere also. This is the spatial mean difference in water vapor, spatial mean difference in water vapor mixing ratio for different months and at different altitude levels. We can see during January 2022, the water vapor has been injected by this volcanic eruption at lower altitudes. And after 6 months, the water vapor has been dispersed toward the southern hemisphere at lower levels. And when it is coming after 1 year, the water vapor has been transported to the higher altitudes in January 2023, July, and January 2024. That means the water vapor from it has been transported towards like vertically, even up to the lower mesospheric levels. But in case of temperature, we can see that initially the increase in temperature is observed. later we can see the drastic decrease in temperature in the regions where the water vapor has been increased. But with respect to time, we can see that the decrease in temperature are also similar as that of water vapor with respect to time and with respect to altitude. From here, we can see that the temperature was decreased nearly 5 Kelvin. And then the cooling, whatever we observed here, is due to the IR cooling of water vapor due to radiative cooling. And mostly the water vapor which was injected by this eruption caused a hydration in the stratosphere, resulting in intense and long-lived stratospheric cooling. And the cooling which was observed here, it is in agreement with the temporal evolution of the water vapor plume. And this is the ozone variability. Initially, we can see that at lower levels, the ozone was decreased at the levels where water vapor has been increased. Similarly, after 6 months also, that in compared to temperature in ozone, we can't able to see that much variability. But here what we have observed is initial days of volcanic eruption, we can see that the variability, the relationship between temperature, water vapor and ozone is very clear. With respect to time, the physics is completely different here. And coming to summary and conclusions, these Honga Tonga volcanic eruptions, which was injected a huge amount of water vapor, even after 2 years of this eruption, the values didn't come to its normal values. That means the values of water vapor is still above the background values. And the most notable characteristics of this volcanic eruption is that height of injection of water vapor. That means when it is compared to previous volcanic eruption, the height of ejection is very high in Honga Tonga volcanic eruption. And in spatial transport, we can see that the water vapor transported from the lower to higher altitudes. Even maybe in January 2024, we can see that the water vapor reached to the lower mesospheric altitudes. And we can see that the water vapor increase causes a decrease in temperature due to IR radiative cooling, and decrease is nearly 5 Kelvin. And even we can see that whatever the values we observed in water vapor temperature and ozone, even after 2 years, this value didn't reach to the background values. That means the impact is very high by this volcanic eruption compared to the other volcanoes. That means this Honga Tonga volcanic eruption provides a natural test bed with how the increased water vapor in stratosphere can impact throughout the middle atmospheric region. Thank you.
Yeah, thank you, Dr. Basha. Any one quick question, query? I don't see anyone. Okay, thank you. Let me thank all the 6 speakers of this session. And with this, we conclude this session and move to the next one.
Yeah, we request the session chair, Dr. Manish Naja, to kindly felicitate the different speakers of this session. Dr. Kishore Kumar from SPL. Dr. Uma Das. Dr. Prashant Chavan. Thank you, sir. So we'll now be starting with our public talk by Professor V. Ramaswamy, Director of GFDL NOAA and Atmospheric and Oceanic Sciences Program, Princeton University, Princeton at New Jersey. He is a leading climate scientist whose work is focused on radiative transfer models and hydrological cycle. He has actively supported the development of supercomputing approaches that enable researchers to develop higher resolution and greater complexity in climate models. He is one of the members of IITM Research Advisory Committee and a recipient of a number of prestigious awards. To name a few: American Meteorological Society Henry G. Houghton Award in 1994, three-time winner and co-winner of the World Meteorological Organization's Norbert Gerbier MUMM International Award in 1998, 2003, and 2013. He was the member of the IPCC team that was co-awarded the 2007 Nobel Peace Prize, American Meteorological Society Carl Gustav Rossby Research Medal in 2022. Today, he would be talking on 21st century Earth energy imbalance and climate change. I request Dr. Michael Hofner to kindly chair this session. Thank you.
Dr. Ramaswamy, can you hear us? No? Please come. I thought he's online. That's good.
I will utilize this time to make few announcements. Yeah, participants and delegates who are yet to provide the copy of your visa, kindly do so at earliest. We need it. So you can do this by visiting our registration desk where our team will be helping you. And after the talk of Professor Ramaswamy, we request the poster judges to kindly evaluate the posters that are there in the adjacent pandal. And that would be followed by a tea break, sorry. And also the participants who are presenting their posters. So after that poster session ends, you can take your posters back with you so that the space is created for the next round of posters that would be getting displayed from tomorrow. Yeah, so thank you.
Okay, Dr. Ramaswamy, so you are really here? The stage is yours.
You will take that.
Hello, testing. Okay. So is it loaded? A pointer. So I suppose I can begin. Okay. Good afternoon, everyone. And thank you to the organizing committee for inviting me to give this lecture. And thanks in particular to Dr. Krishnan, who has been very enthusiastic in having me here. And it's lovely to come back again to IITM. I've been here before. I think many of you know that. So it's a delight to meet with old friends, new friends, and colleagues. In trying to pick a topic, I try to choose a rather general one, but I think you'll see it has linkages to many of the things that have actually gone on in the sessions before. So I'm going to talk about the 21st century imbalance in the Earth's energy. And of course, that's related to climate change. And I want to acknowledge here that I'm drawing upon a lot of work done at GFDL by a lot of colleagues and scientists there. So it's owed to the entire lab. So in terms of an outline, I'm going to talk about the origin of climate modeling and current status of it at GFDL, the aspect of radiative forcing, the heating imbalance and climate change, observations of the Earth's energy imbalance, which is kind of where it really gets interesting because it's not just models, but also drawing upon observations. And then I'm going to touch upon a topic which I may not have time to do full justice, is the energy-water nexus in the climate problem. So the imbalance energy is related to the water imbalance. And I want to touch in particular upon greenhouse gases and aerosols as being two sort of very interesting radiative forcers, and which leads me to the changes in the hydrologic cycle and precipitation in the 20th century, in the 21st century, what's the 20th century. And I'm going to draw upon climate models and observations in going through this lecture. So I want to get to actually build upon what Tim Palmer was talking about yesterday about NWP modeling and how there's a history to it. So I'm going to actually talk, and this was not arranged with Tim. I had my slides also to say along the same vein. I'm going to talk about the climate modeling part of it. So it goes back to the history of GFDL, and how it started was, and Tim mentioned John von Neumann yesterday, that von Neumann, after the first 24-hour forecasts started to come into being and were proven to be successful, he wrote a letter in 1955, July of 1955, to the then US Weather Bureau, which was kind of the forerunner of the National Weather Service in the US. And that's what he wrote in his letter. It's a long letter, 3 pages. It's still there. It was typed, so you can see all the markings that one used to have when you are using a typewriter. Many of you probably don't know what it is, but there was a gadget like that. We used to use it, typewriter. And John von Neumann basically wrote this, that, hey, we got a 24-hour, 48-hour forecast due to the equations. So what happens if you do it infinitely? What happens if you run it he was a mathematician. So he was thinking like a mathematician, and he said, what happens if you run it infinitely? He wasn't thinking of the climate problem or climate change problem. He was just thinking of, let's do the integration and let's see when the atmosphere equilibrates to something. So he called it the infinite forecast or the general circulation pattern. And the US Weather Bureau accepted to do that. In those days, funding for really initiatives like these were not a problem. And Joe Smagorinsky, and Tim mentioned Joe Smagorinsky yesterday, who was actually working with John von Neumann in the Institute for Advanced Study at Princeton, was asked to be the director of this lab called it was called General Circulation Lab set up in Washington, D.C. And Joe Smagorinsky became the first director. He was the founding director and was a director for 28 years. And then this lab moved to Princeton to be on the campus of Princeton University in 1968. And so the history continues after that. And so this was a interesting experiment. And, this is now the 69th year of the lab. And it's been, I have to say, remarkably successful. And Joe, obviously started to pick people to do the so-called infinite forecast or climate model. And here's a picture of two young stalwarts at that time who Joe Smagorinsky recruited, Suki Manabe, whom you see standing, and Kirk Bryan. And these two were pioneers in many ways. And Joe gave them complete freedom to actually do modeling. And basically what they did was, very simple things. You have conservation laws, physics-based conservation laws, which have to be obeyed. So it includes mass, momentum, water, and there has to be continuity across the interface. So this is like the governing processing in atmosphere and surface. And then the next slide is one on oceans. So a very simple model that they started out with, just a mixed layer ocean at first, and then, added deep ocean, and then there's exchange of momentum, heat, water across the interface. And then you have sort of the radiation coming in and coming out, going out, a continent and an ocean. That's kind of the simplest model that they formulated. It was simple, but they really, really went a long distance towards establishing the first coupled climate model. And basically, it was just, this is sort of a more modern version, but basically you have an atmosphere, you have ice, you have ocean, you have land. So basically you have atmosphere, ocean, biosphere, and cryosphere. And increasingly now, of course, you have ecosystem along with that. And then there's interaction between all these reservoirs, and that then constitutes climate processes. And of course, Suki Manabe went on to win the Nobel Prize in 2021 with the physics prize, and which shared with Klaus Hasselmann for the physical modeling of Earth's climate and reliably predicting global warming. And basically, the first model that Suki Manabe built was a 1D radioconvective model in 1967. The paper was 1967. And that really started a trend towards not going beyond 1D to 3D. And the first 3D model was in the mid-70s that he did with Kirk Bryan doing the ocean. So what some people don't know is that Suki actually, that was the second Nobel Prize he got, because the first Nobel Prize was the Peace Prize in 2007, where Suki was one of the people recognized along with the rest of IPCC who were awarded the prize, which was awarded to IPCC and Al Gore. So Suki has the distinction of really being the recipient of two Nobel Prizes. And just last year, Kirk Bryan won a very prestigious award, which is the Alexander Agassiz Medal from the National Academy of Sciences in the US for pioneering ocean and climate science. And this is a prize which is given only once every 5 years. So, it's really a tribute to these guys who set the whole pace. And we are just dotting the I's and crossing the T's now, so to speak. So this is kind of how things originate. Oh, and one more thing. This is actually a results from a model, that's the top, from 1989, I believe, yeah, that's a paper in 1989 that Suki did, which was actually the first projection calculation with a fully coupled model where they ran 2 times CO2 and 4 times CO2 to equilibrium. They ran it for, I believe, 500 years so that there was equilibrium. It was the first such long run for a climate model. And the top, and it was a model which had a resolution of 10 degrees latitude by 10 degrees longitude. So you can see very cold. So there's a warming due to, I think, this 4 times CO2. So you see sort of a large warming in the polar regions, not much in the southern oceans, and then sort of distributed warming along the northern hemisphere. What is remarkable is that in this paper, which Ron Stauffer and Suki wrote in 2017, they compared with observations of the current time period. And you know what is just marvelous is that you see the three features of warming clearly emerging. The polar amplification in the observations, lack of warming in the Southern Ocean, and you see the land warming faster than the ocean. Something which, is every model now does. But back at that time, with a 10-degree latitude, 10-degree longitude model to produce that, and then to really have it robustly compared to observations 30 years later is just something. It's really remarkable. All right, where we are now is, yesterday Tim was talking about the kilometer scale models. This is now an atmosphere 3-kilometer resolution model, which we are running now, and it runs very slowly, but we've actually run now 100 years with this model and analyzing its results, including we have been doing simulations with forced SST changes like 2 degrees Kelvin everywhere, 4 degrees Kelvin. It's not yet coupled to an ocean model. That's going to take some time, but we are there, and it's producing some very nice features, although it has also, as my question to Tim indicated yesterday, also producing some disagreeable features which we have to look into. And on the ocean side, so that's kind of mainly on the atmosphere side, but what is interesting about the high resolution model like this is that you can actually get to things like tornadic vortices, you can get to hurricanes, and you can get to things like dust aerosols caught up in the tropical jets and then flowing across from Africa towards the US. So you can actually get all these features with high resolution. So it's a very, very good temptation to actually try high resolution, even though, as Tim warned yesterday, that there's a lot of physics to be still uncovered. And then on the ocean side, so on the ocean side, we can now go to MOM. So this is ocean model version 6. I believe what you're using at IITM is MOM 3 or MOM 4. MOM 6, you've gone to 18 degree, which is about 20 kilometers. And what you're seeing is really currents here. But, and then, these are the ocean processes which are captured going from global to regional to local. And obviously there's now a great interest in interactions involving the oceans, coasts, and cryosphere. And one sort of initiative I'm going to just refer to here is how a regional MOM 6 now along the various regions of the US coasts is being used to study the effect of near coast physics and science for use in fisheries and coastal ecosystems, particularly for adaptation. And this is actually proving to be very successful. This is a sort of showing the, Gulf Stream here, and this is a resolution of 5 kilometers, whereas the ocean model is 20 kilometers in the global, but you can actually drive regional MOM 6 at 5 kilometers. And then there are a couple of other regions which have also got regional models, such as the West Coast and then the Arctic. And then there's also something now which is being cooked up with Japan and Korea, South Korea on Kuroshio area, because that's kind of very, very much prone to climate change signals. And then this is kind of where we are now, long way from Suki and Kirk's model, but now really combining atmosphere, oceans, land, ice ecosystems. And, the whole sort of picture of the Earth system is this now, and studying the interactions between the various components. All right, let me move on to some actual science that I want to try to explain here. So I want to talk about the forcing of climate change, which is kind of where what the title of my lecture was going to be. And this is actually from AR6. So I think a lot of you must have seen this, are familiar with it. I want to put this up only to kind of draw your attention to the fact that the positive forcers are all these, the well-mixed greenhouse gases, so all sort of positive. Then you have slight negative from land use, but not going to be considered in this talk. And then you have very large negative from aerosol radiation, aerosol cloud interactions. So there are two components to aerosols. One is direct interactions with solar radiation. The other one is interactions through clouds. And it has sort of a high amplitude, but it's got also a large uncertainty If you contrast that with the greenhouse gases, it's much larger. So the net anthropogenic forcing over the pre-industrial to present day period is a large positive, but has large uncertainties because of the aerosols. So with using something like this, IPCC AR6 models produced this, where on the left-hand side, you see the warming, surface warming, global surface temperature changes over the last 2,000 years, basically kind of showing that, the Earth is now, compared to the present, warming pretty rapidly over the last 150, 200 years. And then these are the observations being compared to by model simulations involving only natural forcings, solar and volcanic, do not reproduce this sort of black curve, which is the rapid rise in warming over the last 50 years. And only when you invoke human and natural forcings, you start to reproduce that, although there's some amplitude of uncertainty because of different models producing different results. But overall, the model mean is actually capturing that's the particular trajectory in the observations. Well, it's not just the global surface temperature only, but you have all other parameters that you'd expect to change along with warming, also registering changes. So this is actually from AR5, but it just shows how various things are going along with warming of sea surface temperature. So air temperature over ocean is increasing, humidity is increasing, temperature of the lower atmosphere is increasing, air temperature over land is also increasing. And along with that, you're having ocean heat content increase, Arctic sea ice decrease, snow decreasing, glaciers decreasing, mostly in the northern hemisphere, and then the global sea level also increasing. So it's a picture of a warming world. And this is kind of one of the really telling plots, which has, I believe, succeeded in refuting all claims of denialism on climate change, and that is due to anthropogenic activity. One sort of another snippet I'll show is sort of it's an older, a little bit outdated calculation, but because this was a workshop on the stratosphere, I thought I would show this curve, this plot, which is a change in temperature at different heights in a simulation where you are forcing with all anthropogenic factors. It goes up to 2000, and then you see sort of the gradual warming in the surface. And this is done with the couple model which we had at that time, which is about circa 2010. And so you see the warming in the troposphere, but you also see this cooling in the stratosphere. And this part is largely due to the ozone depletion. But what is interesting is you started cooling the stratosphere. All this is cooling right from 1860 onwards with increase in CO2. It's not that much. And then these sort of cage-like thing that you see, hatch things, is actually statistically significant results against internal variability. So, if you had measurements in the stratosphere going from, let's say, 1900 onwards, we would have sort of said the stratosphere is cooling first and has experienced the climate change first before even the troposphere, because the CO2 was already cooling the global stratosphere quite substantially to beat the noise, to beat the internal climate variability. Okay, so coming to energy imbalance. Climate system is out of energy balance. Given the last few plots I showed, it should convince you that the climate system is not in energy balance. A stable climate would have the net incoming solar balanced by the net outgoing long wave, but that's not happening. You have incoming energy, so from the solar, but less outgoing energy due to absorption of greenhouse gases. And then the excess energy is being accumulated mostly in the ocean, 91% in the ocean. So let's now talk about energy imbalance. So unfortunately, we don't have satellite measurements going back to 1900 or even 1950 or even 1970 or 1979 when satellites started to monitor the weather. But we do have the radiation budget observed over the last 20 years. So that's 2020 to present, it's ongoing. And along with a student of mine, Priyam Raghuraman, who's now at University of Illinois at Urbana-Champaign, we did this study which revealed a lot of things about what you can really make out from these satellite data sets. So, this is just a sort of a picture of what the amounts are in terms of watts per square meter. 340 watts coming in, 100 reflected approximately, so 240 is the net coming in. So in ideal sense, you'd have to have 240 as the thermal outgoing at the top of the atmosphere, but instead it's 239 with a 1 watt per square meter being trapped, and this is pre-industrial to present. And there's something happening at the surface, I'll come to that later, but just focusing on the top of the atmosphere, this is what the satellite observed trend in the Earth's energy imbalances over the last 20 years from series observations. And, you know, obviously a lot of wiggles here, but if you draw a straight line through that, you get about, over the 20 years, you get about 0.8 watts per square meter. That's considerable, 0.8 watts per square meter. Remember, this is not just forcing, it's actually capturing the entire picture of forcing and feedbacks and any variability. So, but it's 0.8 watts per square meter that the Earth is in imbalance over the last 20 years. And so, you know, in terms of how to kind of go about delving into this, this has got to be due to radiative forcing, which is the ERF term, plus a feedback term involving the feedback parameter lambda and multiplied by the change in surface temperature, and an epsilon, which denotes the internal variability. So I'm not going to go into the long story here, but it's in that paper, Nature paper. And this is kind of what we went about doing: effective radiative forcing, radiative feedback, internal variability, feeding into the observed change. So the long and short story of it was, and I'm going to focus only on the short wave because the long wave actually is very slowly increasing and is very small. The major term has been the large decrease in reflected sunlight. And this has involved forcing from aerosols, but also feedbacks. And you see now that the curve in the short wave is decreasing, which means that the Earth is reflecting less sunlight. And the red line, the blue line, no, sorry, the red line you see is the forcing, and then the blue line is expressing the feedback. And I'm sorry, the blue line is not the yeah, it is a feedback. And then the black line is what you get from the observations, and the red line is the one that is expressing the effect of the forcings and the sea surface temperature effect. So the red line is what is the best possible explanation from the models, from the GFDL model in this case, and should be the closest to the black line. So it's also decreasing, and when you analyze that, you find that most of this decrease, and so this is the observed decrease, the small bar here. This is a model decrease, which is slightly larger in terms of the mean. And the amplitude is coming about because of the expression of uncertainties due to forcing factors, as well as due to how you compute this in a model, and also internal variability. So most of this is coming from the northern extratropics. And what this is coming about due to is the clean air laws in US, Europe, and China have resulted in less aerosols, light reflecting particles. And also cloud liquid water path has decreased, which is then manifesting in shortwave, in reflected sunlight, in shortwave decreasing. So this is kind of something that the satellite record is telling us. And it's very nicely mapping into all the theories we have about radiative forcing and feedbacks. There is another satellite, which I actually mentioned in a talk earlier today, the AIRS infrared satellite. So this actually measures the infrared spectrum in different channels, which is an even better one than just looking at the total long wave, which was what the series does. And one of the really interesting things is that channel, there are channels in CO2 bands, 710 to 720 wave numbers, and also in methane N2O bands, 1270 to 1280 wave numbers. And you see the CO2, this is from the satellite. So the straight line is just a line through the satellite observations and shows clearly the decrease that you would get because of the increase in CO2 over these 20 years, from here, 2020. And then this is the methane and N2O. So you see a decrease because the gas are absorbing the radiation passing through, and so you don't get you get the greenhouse effect. You don't get the radiation at the top matching that at the surface. It is less than what it is at the surface. So clearly the trace gas signatures are clearly discernible in the air's spectral signal. And this is actually leading to an interesting concept that you can actually now monitor the Earth's energy imbalance from satellites, provided, the satellites keep going. We can actually monitor the energy imbalance, and you can even monitor the watts per square meter contributed by the greenhouse gases over this period, which means you can convert from ppmv and ppbv to watts per square meter. Where this gets interesting is when you start thinking of reductions in CO2 emissions or near carbon neutral trajectories, you can actually check through satellites as to whether the world is committing to it or not. You can even go to individual regions and see which nations are not contributing to any pledges, example to the Paris Agreement and so on. So it's a very useful tool now to monitor, besides just the measurements of the gases, which is kind of conventional now. Okay, so I'm getting to sort of the last part of this, which is the climate change and energy and water cycle nexus. So now, again, I go back to the same plot. We were seeing the top of the atmosphere then. Now let's see the bottom. So at the bottom, this is all global annual mean. The net shortwave is about 160 watts per square meter from this kind of Wild et al. Figure. The net long wave, which means the Earth sort of in the net, Earth's surface gets some energy from the atmosphere in long wave, but also radiates back. So it's minus 56, so the energy is being lost from the surface. And so it has to be balanced. This balance has to be achieved by sensible heat and latent heat. So that contributes 103 watts per square meter in the sort of normal sense. And in this sort of category, if you look at global mean, the latent heat dominates. It's kind of 4 times sensible heat. And you all have seen maps like this of the hydrologic cycle, where there's evaporation and then there's precipitation, and there are other things happening like stream flow and flow of water down hills and so on. I'm going to just focus on evaporation and precipitation in this talk, in this part of the talk. And I'm going to sort of dwell on this tale of the 2 significant forcing agents. It's like a tale of 2 cities. Impacts on the global hydrologic cycle. And part of this, by the way, also gets back to Chirag's talk, which you heard earlier, the many similarities between this work and what he presented. So first of all, I'm going to take this model CM4, which is our 4th version of couple model at GFTL. And this was the model which went into CMEP6 and AR6. And of course, you know that with numerical models, you can pretend as if the Earth was being forced by CO2 only, or the Earth was being forced by CO2, methane, ozone, or forced by aerosols only, and so on. So you can do all those tricks with a numerical model to understand why something is happening. So here is the temperature change from this model from 1860 pre-industrial to about 2015. And the different curves. So the pink curve is what you would get if you had only increases in well-mixed greenhouse gases. And by the way, the black line here is the observed change. So obviously, the greenhouse gas only curve is rising too fast to match the observation. On the other hand, if you had an Earth driven only by anthropogenic tropospheric aerosol, you get the green curve. And that also, of course, is going the opposite direction to the observed. And then you have other things. So I mentioned other, I'm not going to dwell on them, but they're actually substantial. They're not small, which includes land use, volcano, and solar. That actually has a slight bit of negative trend. And then the all forcing, which is everything combined together, is a blue curve, which of course doesn't match exactly the observed, but it's kind of having the same rate almost of change since 1970 compared to the observations. And what is important, or what I want to focus on, is the fact that the greenhouse gas induced temperature change is 1.5 degrees Kelvin over this period. Aerosol is minus 0.5. So, in terms of magnitude, it's a factor of 3 greater effect of greenhouse gases. That is temperature, global mean. This is now global mean precipitation. And here, the black line here is the observation. It's sort of a reconstruction. It's not GPCP. It's a NOAA's precip reconstruction. And the observations do have a lot of uncertainties because they are not there globally. It's kind of filling in manually, so to speak, of the data set. But you see, if you have any greenhouse gas increases, you'd get this pink curve. And this is well known from theory back from Manabe's early days, that you would have an increase of the hydrologic cycle with greenhouse gases. Aerosols, on the other hand, and we'll get to this reason later on, is a negative, which means there'll be a decrease in precipitation. And so the net forcing is kind of, barely anything. Maybe in the last 50 years, it's actually showing a little bit of an increase. But basically, it's over the 20th century, it's been either decreasing or pretty much staying static. But here the change between greenhouse gas and aerosols is very telling. It's the same gases, same aerosols, but now greenhouse gas is giving you about 2 watts per square meter. I'm converting the precipitation rate to energy. So 2 watts per square meter, aerosol is almost completely offsetting it in this model. So aerosols have really got a very more potent effect in terms of the hydrologic cycle than they do on temperature. Okay, so parsing into this a little bit, if you take the well-mixed greenhouse gases and you take the different regions, including global, which is in red, they all show an increase. With the aerosol, they all show a decrease. And notice that Asia has the biggest decrease in the model. And so the all forcing is global is just a compensation of these 2 reds, so basically 0. And over Asia, the overall result is a bit of a decrease in the precipitation. And why does this come about? At least in a sort of a global mean sense, you can try to examine that very simply. But before that, this is from IPCC AR6. So this is actually Northern Hemisphere summertime. The top panel is showing short-wave radiation anomalies. And you sort of look at the black curve, which is the measurements. And you see kind of this decrease in the short-wave radiation till about 1990s, and then sort of back to an increase. And then you see the precipitation. Now there are 2 sort of reconstructions. One is GPCC, one is the CRU, and both actually tracking each other very well. Very much commensurate, the decrease is very much commensurate with what the decrease was in the shortwave, almost sort of a direct correlation. Now the models featured in this are not, they're all the CMF6 models. They're only actually the only 5 or 6 models available during this analysis. So they all kind of come out looking weaker compared to observations, whether it's in the short-wave radiation anomaly simulation or the summertime precip simulation. But the important thing is this decrease. If you had only greenhouse gas increases, you should not be seeing a decrease unless there's internal variability. But, we don't have any evidence that that decadal variability is going to kind of put you down in a sort of a ramp down slope like this. So this is actually very interesting from the observations that you don't see any evidence of a dominance by greenhouse gases over this period. Now, in terms, you can actually go into the surface energy budget balance, even though it's global mean. And what you get for well-mixed greenhouse gases is in terms of the short wave, long wave, latent heat, and sensible heat. If you look at the long wave is a positive because the atmosphere is warming, there's more water vapor there, and it's giving more long wave radiation. Short wave is a small negative because increase in CO2 and increase in water vapor they have infrared absorption bands, so they reduce the radiation to the surface. And so to balance that, there has to be a loss of latent heat from the surface in terms of increased evaporation. And that's what contributes to increased precipitation because you have increased evaporation. And so this red bar is just sort of as giving you the latent heat release. And then this is residual. And sensible heat is a small term, which kind of, as I said, in the global mean, it turns out to be a small term. In case of aerosol only, you have the biggest change in the short wave in terms of radiation. Long wave is very small because the long wave effects of aerosols, even with feedbacks, are quite small. And now here, the latent heat switches sign because the loss of radiation to the surface means less evaporation. Less evaporation means there's less latent heat lost from the surface. So surface actually, in contrast to the well-mixed greenhouse gas case, preserves the latent heat. And there's a sensible heat, again, is a small term. So when you look at the all forcing, you have these sort of 2 big bars going in opposite directions. The long wave at the surface due to greenhouse gases and the short wave decrease due to the aerosols. And so in the context of this model, this results in a very, very small net, basically nothing. So what happens in the 21st century? And this is kind of where all the hypotheses and theories will be put to test. You have these two things happening: well-mixed greenhouse gas increasing and aerosols decreasing. In fact, Chirag showed some results due to these scenarios. So, if everything was linear and there was no sort of hysteresis in the system, you would have a reversal of these effects. So what you would see then is something like this for precipitation, where here we are in the present. What you saw before was, all these curves to the left. And now, if you look to the right, that's kind of where we are going to march towards 2100. And what you have, for example, for the greenhouse gas only case, this was the green curve from the past to the present. And in the future, of course, with increase in greenhouse gases, that particular component will continue to increase. The aerosol one was a decrease, but now with aerosols coming out of the atmosphere, that itself is going to result in an increase in precipitation. So now you're going to have a double whammy. Instead of the pink curve was the all forcing. So instead of something which was, negligible and then began a decrease over this period here, is now actually going to start seeing an increase, where the increase is going to be much more than whatever we have seen before, because of the fact that, the two things are going in the same direction. And, this raises a picture of something like this, where in the early part of the 20th century, maybe up to 1950 or so, you had greenhouse gas increasing, but basically none of the forcing agents were very large. So maybe that's why the precipitation, which sort of the observation, well, there's no observation here, sorry. This is just the model. So the model doesn't reflect any increase or decrease in precipitation due to changes in the forcings, which is more largely greenhouse gases. There was not even a volcanic activity going on there. And then this period is an interesting one where these are different curves here showing northern and southern hemisphere. Southern hemisphere doesn't really see much effect because the aerosols are not there. The northern hemisphere, that's the dotted line, is showing an effect. And these are actually two different versions of the model, CM3 and CM4. CM3, just sort of for reference sake, had a stronger aerosol forcing than CM4. So CM4 actually has a little bit less effect due to aerosols than the CM4 did. But anyway, all these curves sort of in the northern hemisphere have this decrease and then starts an increase, which is just, should be going on and on, unless there's some other things happening or there's some physics that we missed out on. And in terms of, again, the surface heat balance, very simple now. You have the net short wave. But, so this is the change with respect to 2000, year 2000, so 2100 minus 2000. You have the net short wave increasing now because aerosols have gone out of the atmosphere. Net long wave continues to increase at the surface because of increased greenhouse gases. And now latent heat is going to be driven by both the things in the same direction. So there's increased loss of latent heat, which means increased evaporation, and therefore the increased precipitation that you saw on the previous curve. Then, on the same simulation for CM4, I thought I would show you some changes in this model that happened over India. So all forcing is the top left panel, greenhouse gas only is the top right panel, and then aerosol forcing is top bottom left, and all the other forcing is bottom right. This is surface temperature change in the last half of the 20th century. Warming, I mean, the yellow and reds are warming, so big warming due to greenhouse gases, kind of almost neutral effect due to aerosols, but around India, there's a big cooling due to aerosols, and then the sort of warming that's going on in the last half of the 20th century. And then if you look at what happens 2050 minus 2000, which is 50 years now, I mean, we've already done half of that. So a big warming. Now, because of these two effects going in the same direction, greenhouse gases continuing to warm, aerosol continues to not cool, sorry. And, this must be statistically insignificant because actually I haven't done statistical significance for these. And then the other forcing. So basically, this is kind of increased warming of over this 2050 to 2000 of about 1 to 1.5 degrees. And then in terms of precipitation, you see sort of this decrease. I think a lot of people have talked about it. With greenhouse gas only, you see an increase in precipitation. The blues are decrease in precipitation, and then that's coming out mostly because of the aerosol effect, which was again discussed in Chirag's talk. And then looking to the future, I'm sorry, I think I'm not. Yeah, okay. So this is an increase. The reds are increase. So now looking to the 2050 minus 2000, you see a big increase in the precip pattern, which is consistent with just the global mean increase in the intensity of the hydrologic cycle. Basically, it's more vigorous now, increased evaporation, increased precipitation. This is actually a prediction model. So it's actually built off CM4, but has a prediction system. And so this is being driven by, no, this is all just the climatology. And then this is being driven by the SSP2 4.5 scenario. So this is not the entire century, 2081 to 2100 average minus 81 to 2000. And this model which is kind of a little bit of an update to our CM4, is also showing the same result, namely the increase in precip over almost all of India. So I'm going to start concluding now. So that was over India. In terms of where we are going with this, we actually want to now try to understand the various climate extremes. And one of them is due to the excess or deficit of water, and how much is traceable to the increase in the vigor of the hydrologic cycle. And to this extent, I'll just give you sort of two quick examples. One is heat waves in North America. And it turns out that using the SPEAR model, which I'll tell you this acronym sometime later, it stands for Earth System Research Model. There are sort of three components that we find are components that can be used to predict the summertime heat waves for North America. One is a component which is just due to the secular trend. So it's just the warming that's going on due to the forcings. Another component is actually coming about because of temperatures in the North Atlantic and North Pacific. And the third one is a classic El Nino La Nina dipole. And we've actually tried to do predictability experiments to understand how much these are predictable. So it turns out that the secular component is very highly predictable. You get sort of 0.5, 0.6 predictability versus lead months. You can up to even 10 months, you have a sort of a 0.6 predictability skill, which is pretty impressive. The component 2, which is the North Atlantic, North Pacific, is not so strong. It's only 2 months that you can do a predictability of 0.5. And then the El Nino La Nina signal is not even that strong. It's only about 1 month or so. But this is the kind of now what's the latest in terms of going from these global projections to actually starting to do predictions. And this is my sort of final slide where looking at atmospheric rivers. So this is kind of, what atmospheric rivers, that's become a fashionable word, but basically it means sort of long strings of portions of atmosphere which are just containing lots and lots of water vapor and liquid water. And one of the notable things is, first of all, of course, there is a significant projected increase in atmospheric river activity, which is not, which is very intuitive coming if you follow the fact that hydrologic cycle is going to become intensive. But what is interesting is they all lie in the storm track regions, or the conventional storm track regions are the ones which are seeing the largest increase in atmospheric rivers. And so, prediction models should be able to track these to kind of figure out where they're going to dump the water. All right, so I come to my summary slide, conclusion slide. The anthropogenic aerosols have strongly offset the precipitation impact of GHGs in 20th century, with the largest effects being the Asian region. And this raises a question that, we struggle to find an attribution to precipitation. Temperature is becoming very easy, at least in the global annual mean. IPCC has now regularly done that over the last 3 or 4 assessments. Temperature attribution, pretty cool, pretty hot actually, but it happens. But precipitation, you don't see it. I mean, none of the IPC assessments has ever produced because now for natural reasons. I mean, you just can't do it. So is it because the aerosols actually have suppressed a signal? That, you know, if you're trying to look for a greenhouse gas signal, you probably won't find it because the aerosols are just wiped it away. Of course, that's not going to be true in the 21st century. And subtle observations are really becoming very important in terms of revealing the signatures of changes in atmospheric composition and its influence on the heat imbalance. And this is interesting because of this can be used for monitoring how the world tracks towards any policy on reduction of carbon emissions or methane emissions, and also for any carbon neutral trajectories. Recovery from aerosol effects in 21st century, we're going to start seeing increased hydrologic cycle vigor related to the 20th. And then the impact of increasing water vapor in the atmosphere. So this is something that has not been, I think, very deeply analyzed. That it's a very obvious one. I mean, it goes back almost to, again, Manabe's days, you know, that water vapor is driving the feedback. But water vapor in the atmosphere is an amplifier of climate change. And then it has other effects on the atmospheric circulation patterns because of latent heating release in the atmosphere. And so, you know, this is something that needs more attention, especially as we look towards extremes on the regional scale, because that's kind of where water vapor, CO2 may have driven all the water vapor up from the ground, but the water vapor in the atmosphere and what it does to circulation is, I think going to be very important, particularly as there's a demand to know how the extremes are caused, where are they going to occur, how severe they're going to be, how long they'll be. So that's all I have, and thank you very much for your attention.
So yeah, thanks very much for this really great talk. Yeah, are there questions? Yeah.
It's a very nice, excellent overview of many things happened. So I have one suggestion or comment. Are you taking the feedback mechanisms while you are projecting any future simulation? For example, if ozone recovers totally.
Yes.
So how does that is going to affect offset your what you have observed in the precipitation patterns or or any trend of that for that matter?
So yeah, feedback effects, to the extent we can actually represent them, are being taken into account. There's a sort of a chemistry system in the model. Ozone doesn't have that much of an effect, you know, either in the loss so far on the surface in terms of precipitation or recovery compared to other agents, compared to greenhouse gas. And by the way, the greenhouse gas actually does include ozone too. So it includes the ozone loss till whatever time, and it actually includes recovery also because of the chemistry in the model. But compared to aerosols and the other greenhouse gases, it's much less of an effect. I mean, you can see that from the radiative forcing diagram. It's a smaller term than even nitrous oxide.
Suppose if several countries are implementing the clean air policies, you have seen, already witnessed over China, that lot of changes in the last century. And India is also going to implement, and where that hotspots of aerosols are present. So whether those clean air actions are going to change other greenhouse gases, because there is feedback. If you reduce the aerosol, then it has impact in the other greenhouse gases. So that feedback, whether it has entered here? So
to the extent we can, it does feedback on tropospheric ozone. So that there is an effect on tropospheric ozone because of the change in aerosol. I don't know how much that effect of that is there in the model. And obviously the chemistry and physics has to be updated as and when more knowledge comes into being. So definitely tropospheric ozone will get an impact due to changing aerosols, especially sulfur aerosols and reactions to OH.
Thank you very much. That was an excellent talk. I really enjoyed, right, from the overview of how GFDL started and the latest IPCC AR6. I had one question in the last slide, this one you have made. Did aerosol suppress the GHG-induced precipitation? Was one of the comment that you...
We can't go back.
The previous one.
I don't seem to be able to go back. This one?
This, okay, this I will come later on in my next question.
Okay.
Yeah. So you are saying that in the all forcing experiment, rainfall is increasing much more than globally than the GHG experiment.
Oh, yeah, because the GHG one is just GHG effect.
Yeah.
It does
Now
not.
you are decreasing the aerosols as well.
No, not in the GHG only experiment. The GHG only experiment is just GHGs only.
Yeah.
This
But
one.
in yeah. Yeah. But I was thinking, but
So this is actually the pink curve is just the sum of the green and the blue. The delta is just the sum.
so I thought in the future there will be many areas that will be getting drier also, like
Oh,
South America and
This is global.
This is global.
This is global. So
Yeah, so many areas in South America and also Mediterranean, I think they'll be getting drier.
yeah, I
So
mean,
I was little surprised when I see that purple line.
yeah, the whole globe is, the oceans are warming. So you get the evaporation from the oceans, but doesn't mean the land areas, some are going to get desiccated. I mean, if I go back to this curve here, you know, all these are going to switch signs in the, no, sorry, no, it's not the balanced one. This one. I mean, the latent heat, no, sorry, I actually want to go back to the other one because we're talking about the areas. Yeah, so, you know, Asia, parts of Asia would be drier and parts of it are going to be wetter. But the amplitude of this would shrink. The blue curve in the aerosol only case would shrink from whatever is shown here. It would, in fact, it might just flip even to the other direction. It might because of the precipitation increase. So the global precipitation should not be taken as a sort of a proxy for circulation effects over land areas, because the global changes are coming mainly from the oceans. And it's mainly the Pacific, you know, that's kind of where the largest contribution for the evaporation is coming on the tropical Pacific. And then all the tropical Indian, the tropical Atlantic, they are the ones contributing the most to the evaporation. But the precipitation is going to fall differently, you know. And I think that's the way I look at it.
Maybe in the polar regions and all, you may be getting much more precipitation.
Yes, yes. There's also going to be poleward moisture transport. So, you know, you're going to have more so in a global sense, the land areas in the mid latitudes are going to get drier. But the northernmost part of the mid latitudes out to high latitudes are going to actually see an increase in precipitation.
And your last slide, that is more of a comment.
This one?
No, next, the last summary slide.
This one or
next? In the very last. There's no figure. You just made some conclusion. Yeah, this is the one. Did aerosol suppress GHG-induced precipitation signal delay? We said that in the chapter 8 of IPCC.
Yeah.
We said that it suppressed.
I think so. I'm just raising a question here because I think, you know, the one thing that I want to be careful about is the land use changes. What has that done? I don't think this model really captured all the land use change effects because it didn't have a dynamic vegetation land. So what does that do to, I just wonder whether that's going to do something.
And also you showed that that radiation and precipitation, the GBA data set.
Yeah.
So so
this one?
No. This one. This also from what chapter?
Yep, AR6.
Yeah. The one thing is the GHG and all forcing experiment, the bottom panel, the precipitation is decreasing, but you're not getting that variability, that big.
Well, not only that, you're not even getting the amplitude.
Amplitude also is not, and also that multi-decadal variability, you're not getting.
So that actually raises an interesting question. You know, was aerosol forcing actually more than what the models used, even though the other evidence is that the models probably exaggerated the aerosol forcing due to the cloud interaction. But this one would suggest something else. But I think there's also a cloud feedback involved because the GBA measures total sky radiation. So it's not just aerosol effect, it might be a cloud change effect also. Although with Priyam, we've done now a paper, which is in Journal of Climate, where we show that the 20 years record actually shows a net zero cloud feedback. There is a positive long wave feedback and negative short wave feedback. The two cancel. So net cloud feedback is zero within uncertainties.
Thank you.
Okay, more questions? There was a question over there. First, in the back.
Hello, it is a very nice talk. And I just want to mention, yesterday there was a discussion after Team's talk about the mechanism. Many mechanisms are missed in the models. We had some discussions. And on that basis, I'd like to draw the attention. You showed the IPCC map for radiation budget. And there solar forcing, there is no uncertainty, and so nominal solar forcing was shown there. Whereas anthropogenic, very strong positive, and volcano, very strong negative, with large uncertainty. But solar forcing, there was no uncertainty, and very small amount of solar forcing was shown there. And another thing is that for decadal signature, how the model represent the decadal signature in the models. Is it matching with the observation? If it is not matching with the observation, are we not underestimating solar and volcanic direct and not only direct, indirect influence a lot? What is your opinion?
So
and another point you mentioned here.
I would like to go back to the slide,
yeah.
but I think there is actually an error bar around the solar forcing.
Very small, very minute.
But it's a very small amplitude. And if you take the actual magnitude, it's actually 50%, but it's 50% of a small magnitude.
Yeah.
That the solar forcing, I think, is actually quite good in my opinion. Because
sun is the prime driver of the energy of the Earth system. And in the IPCC, it is completely nominal, what is shown here.
Yeah, it's completely small.
Yeah, that is the major uncertainties arising from that.
Well, the solar forcing has been now looked at in so many different ways from, when IPCC started, that, there were a lot of initially speculation and theories that it would be not small, but, different ways of looking at it through proxies, through looking at other sun-like stars, it is actually very small. And then the last 30 years of satellite observations just show no variability, very little. I mean, the solar minimum varies, but so the solar forcing that is depicted on the radiative forcing diagram in the IPCC is probably quite right.
Many indirect effects are completely neglected. And another part you mentioned here.
So indirect effects are actually taken into account because there is UV activity, which acts on the chemistry. But it turns out in these climate models, it tends to be a very, very small effect.
Yeah, and you mentioned about ozone. Tropospheric ozone, you only focus, but stratospheric ozone is playing a huge role. And sun and volcano together, they're making a lots of influence in stratospheric ozone. And that part model, most of the cases, uncertainty could be arising from that areas also.
But stratospheric ozone is not ignored here. It's very much a part of the model.
Yeah, but
the chemistry might be simple, but it's very much part of the model. So it's not ignored. And some of the models, not this one, but they actually, like WACM, for example, I know, deals with it much more explicitly. So it is taken into account. There might be uncertainties.
This is a statement, and all the community will discuss with that and think about it.
No, thank you. Thank you for raising the point. It's important.
Thank you. I wanted to come back to the question that you raised right at the end about attribution of global precipitation changes. And I wonder if you have any predictions about how long until we can start to do that. And maybe to dig a little bit further, do we need more physical understanding before we can do that?
Oh, last question is very easy. We always need more physical understanding. I mean, because you cannot, especially these things are starting to play a role in policy matters. And for policy matters, I feel as scientists, we really have to keep giving the best state of the science information. And I think, anyone would admit that there are a lot of uncertainties right now in these estimates. Sorry, I missed your first question.
Or how long until we can do formal attribution of precipitation change?
That's interesting. I mean, I think now, instead of sort of working with these DEX-N models, we think now we're going to have to start looking at seasonal decadal seasonal decadal changes and predictions. And that's why, one of the reasons we started doing predictions with the same model that's being used for projections is to examine whether, like in the next decade or the next 2 decades, are we going to actually see a big signals in just excess or deficit of water? Because now, of course, I mean, look, it's like, people are now anticipating that by 2100, you're going to have a change in climate, the way we are going with emissions and so on. But what the public wants to know is they don't want to wait till 2100. None of us will be there in 2100. They want to know next 30 years what's going to happen to our lives. And that's where the prediction thing comes in. And one of the things we are looking at is the atmospheric rivers. That is already becoming very strong, at least, in terms of what we're looking at, the rivers coming from the Pacific into the Western US is already a very, very strong signal, but it's very variable right now. One season it comes, another season it doesn't. When it comes, California mountains get 11 feet of snow. It doesn't come, there's no water in California. So I think that's going to happen soon. So you asked me to go on a limb and speculate. I will go on a limb and say that the next 2-3 decades, we are going to start seeing signals unless we start throwing more aerosols. Then again, we are throwing ourselves into a corner.
From the audience? Thanks. So I just start with this previous comment which you just made. A lot of people start talking about atmospheric rivers in Indian context also. And I'm seeing also some publications also coming out of it. So how we are going to distinguish this with the monsoons, this atmospheric rivers, because it's almost, they have the same signals.
Well, that's why I actually do not like the term atmospheric rivers. Unfortunately, it's kind of being now scripted into the psyche that you kind of, at a short form of referring anything to where some body of atmosphere has a lot of water, you start referring to the atmospheric rivers. I mean, if monsoons start to become more intense, that's actually a manifestation of increased atmospheric rivers of a different kind, perhaps, than what occurs in the Pacific and the Atlantic. But it is very well the same thing. I don't see a difference. I mean, wherever you have this accumulation of moisture, which never happened before, and now it's happening, or it happens now to a degree which is 2 or 3 times more, like in the storm tracks, you have to sort of say that that is really all the same. There's no difference between them.
And there is one question from in the chat. Speaking of land use changes, what about dust? Models still struggle to represent dust emissions, never mind potential feedbacks of dust emissions to climate change. Would you expect this to change the projections?
I don't, maybe change is a strong word, but I expect dust to play a significant part. We've already experienced that with our Earth system model, not this one, that model I was showing, but the Earth system model, which has biogeochemistry, carbon cycle linked into the physical system. The one thing we saw between the difference between the climate model we had and the Earth system model that we had was the climate sensitivity, which is basically, temperature change due to doubling of CO2. The CM4 got a very high not very high, but moderately high climate sensitivity up in the upper tier of the models in AR6. But the Earth system model got a climate sensitivity, which was a good, 1 degree less, 0.8 degrees less than the climate sensitivity of CM4. And the reason was, there were 2 reasons. One was dust. So basically, wherever global warming created aridity, you have less precipitation, you have loss of vegetation, which creates bare soil, and then you have strong westerlies are going stronger. So northern hemisphere land areas start to emit more dust. And that's natural. I mean, that's dust which is on the surface, but it is dust which is being kicked up because of anthropogenic emissions. So that's a feedback. It's a pretty strong feedback because most dust is reflecting more than absorbing. So it creates a negative feedback to the amplification due to CO2 and other gases. The other aerosol which played a role was sea salt. Normally, sea salt has not been thought of as something which can kick in a feedback. But now that the Earth system models are including that, basically, sea salt generation is a function of temperature and wind speed. What happens in the southern hemisphere is, as the southern oceans get warmer, temperature increases, wind speed increases, and there's more sea salt in the atmosphere, which, sea salt itself is reflecting, and then it forms clouds, low clouds, which is again reflecting. So it's again negative feedback. something that you wouldn't have anticipated from running a physical model. So the answer to the question is these two aerosols have to be looked at more carefully for their negative feedback effects.
Okay, so I would thank you a lot, and thanks a lot for all the questions.
Thank you. Thank you for the questions.
Okay, and I think there are some announcements.
Yeah, I request Dr. Hoffner to kindly felicitate our speaker. And also Dr. Ghosh Bhasha, you are here. Yeah, sir, Dr. Hoffner. Yeah, be here. Yeah, we have one more speaker from the previous session. Thank you. Yeah, it's now time for the poster session. We request the poster judges to kindly evaluate the posters during this session. Let us enjoy this poster session with tea and possibly some thunder showers outside. Thank you.